Hello, good evening to all of you, and welcome to Unacademy. Welcome to the special session where we are going to carry out a complete coverage of physical geography in one shot and in one video. The aim that each of you should have is that by the end of this session, you should not be requiring to revise physical geography from any other place anymore. Because here we are going to go ahead with a comprehensive coverage of all the facets of physical geography, geomorphology, that is climatology, and oceanography, along with the discussion of the relevant PYQs as well, so that you know whether you have understood it or not. So, in case we have just started the preparation or just started the revision of geography, this is a video that should be your final solution and one step solution. Now, how are we going to proceed ahead with the session? So, first of all, we are going to have a discussion for all the three facets of physical geography. And this session is only for physical geography. We will have a separate session of Indian geography in the second week of March as well. So, right now, only for physical geography. So, you will have geomorphology, morphology, right? So in this, once we are going to cover the topics, with each topic we are going to discuss the PYQ. Then comes the important aspects of climatology and oceanography. Now, few of you might have the doubt regarding or might have some difficulty regarding the coverage of the portions associated with maps. So as to how to cover those mapping areas. Now, this is not a particular video associated with your mapping proficiency. This is for the basic concepts and those high frequency topics which are asked in the prelims exam. In order to help you achieve greater proficiency in maps, we have come up with a series of special classes free of cost, which will be on the platform, right? And that will be held on Monday, Wednesday, and Friday at 5 p.m. Okay, so every Monday, Wednesday, and Friday at 5 p.m., just take a look at these special classes. You can find that on the app, on the platform. It is free of cost, and ensure that your mapping revision is also carried out. The link for that particular special session will be found in the description as well. Now, having said that, what are the topics of geomorphology that we are going to cover today? So, today we are going to start with the basics associated with the interior of Earth, the different types of rock systems that we have. What are the different types of metamorphism, for example, because UPSC has been interested in rocks and rock cycles since 2022. So, you had a question associated with permeability and porosity as well. So, that is also something that we are going to have a quick revision of. Origin of continents and oceans. With the help of this, we are going to revise the portion associated with continental drift theory, the convection current theory, seafloor spreading theory, as well as the plate tectonics theory. Okay. Then you have seismicity and volcanoes, weathering, the different forms of weathering, what is hydrolysis, what is oxidation, what is carbonation, and the portion associated with landforms. So that is the portion associated with geomorphology that we are going to cover. Now, ideally, we will give frequent breaks so that you guys are also refreshed. So at around 2 hours and 2.5 hours duration, from now, that is around 6:15, we are going to have a break. And after that, again, after the break, we are going to continue. Okay. So that is going to be the overall modus operandi. Okay. Origin of universe, we are not going to discuss in this because origin of universe, frankly speaking, not very important for your prelims examination as well. Big Bang theory is something that you can brush upon, but UPSC has not been asking a lot of questions associated with that. These are the areas where UPSC has been focusing upon year after year. Okay. Now, starting with first of all, the interior of planet Earth. Now, when we talk about interior of planet Earth, now it is as diverse as it can be. What we see on the surface is very different from what we feel underground. Now, mankind, or in general humans, now they were always curious about what the earth is made up of. But it was only the development of sciences in the 20th century, that is in the 1900s, which helped us have a greater idea about what lied in the interior. Prior to that, you had geographers like the Austrian geographer Edward Suess, who had suggested that Earth is made up of distinct layers. But then, what layers are they and what is their overall property? That is something that was actually known to us much later. Now, how do we know about the interior of planet Earth? So, when we talk about the interior, you have different sources of information for the interior. So, you basically have the case of direct sources, and you also have indirect sources for the information. Okay. And the name in itself tells us direct sources means first hand information is provided about what lies in the interior. Okay. Indirect sources, you have some data, some points, and from that you draw the inference that it might be possible that here the density is high, density of materials is low, and so on. Now, there are two direct sources which are present. Which are those direct sources? So, here, first of all, the direct source is the case of mining and drilling. Mining and drilling. So, by digging out deeper mines, right? For example, in Kola Peninsula, we have one of the deeper mines around 10, 12 kilometers deep. So, when you dig deep mines, you get to know that, okay, what is the temperature change as one moves in the interior, or what is the compression of the rocks which can alter the materials as one goes into the interior. Now, this 10 to 12 kilometers is very close to the surface itself. Overall, planet Earth has got a radius of close to around 6370 kilometer, that is approximately 6400 kilometer. So it is still very much closer to the surface, but nonetheless, it tells us or indicates to us the behavior shown by the rocks and how that behavior tends to change. Then, after that, you also have the case of volcanic eruptions. Volcanic eruptions. Now, volcanic eruptions, they bring materials from the interior and that spreads onto the surface and immediately solidifies. Whenever that does happen, immediately you will find that the geologists, the chemists, all of them rush to the regions of these volcanic eruption sites or the volcanoes and they start collecting samples. Because the type of lava which comes out is also an indicator of from where the lava is coming out. Is the lava coming out from a shallow depth of 200 or 400 kilometers, or is it coming out from a greater depth associated with 2800 kilometers, that is the lower portion of mantle? All of that determines the chemical property of the lava. So that is why volcanic eruption will give you an idea about the mineral composition as you move into the interior of planet Earth. Then we also have the indirect sources. Now, what are these indirect sources? Indirect sources, basically, the most important and the most informative out of all of them is your seismic waves. Seismic waves are basically the energy waves which are released whenever an earthquake occurs. Now, these energy waves, they are known to travel in a certain manner. They move or propagate into the interior of planet Earth in a certain fixed pattern. Now, how do they travel? Where do they travel? What is the time taken for them to travel? That gives us an idea about the density of materials which are present in the interior. Then you have the case of the gravitational anomaly, gravitational and magnetic anomaly, indicated by planet Earth. What do we mean by this gravitational anomaly? So, when we talk about planet Earth is not a perfect sphere. It is an oblate spheroid or the shape which is also known as a geoid. And what does that shape actually mean to be? That shape basically means that the Earth is slightly flatter in the region of the poles and slightly elongated at the region of equator. Right? So that means if you were to draw, let's suppose, the distance from the center to the region of the poles and compare that to the equator, Let's suppose this is R1, this is R2. So R2 will be greater as compared to R1 because equator is slightly bulged, the poles are slightly flattened. Now, what that means is that as an individual, let's suppose you are standing here as an individual. Now, you will experience a gravitational pull. Now, let's suppose if someone else is standing at the region of equator, they will also experience a gravitational pull. Let's name this individual A and this individual B. Now, because A is closer to the center as compared to B, so gravitational pull at A is going to be greater than gravitational pull at B. Why? Because the force of gravitation is inversely proportional to the distance. So that is why you will always find that there is a gravitational anomaly when you compare it to the poles and to the equator. So that is again an indirect source. Then even the magnetic forces. Now we will discuss why Earth experiences magnetism. Now that is because of the property of outer core. So if the outer core would not have been in a molten state, Earth would not have experienced magnetism. So by judging and observing this magnetic field lines across planet Earth, one gets an idea about what is present in the region of outer core. Okay, so property of outer core. In fact, as we will discuss shortly, it is that difference in the property of outer core which ensures that life is present on planet Earth, but life cannot survive on planet Mars. Because had the outer core not been in a molten state across planet Earth, Earth would not have experienced magnetic property or magnetic field lines. Okay. Then, other than that, you also have the case of asteroids, asteroids and meteors. Okay. Now, these are celestial objects which move across the solar system and move around the sun. Now, when they keep on moving around, now these were the elements which were present in the earlier primitive solar system around 4.5 billion years ago. Now, around 4.5 billion years ago, it is a combination of multiple of these materials which collided, then they stuck together, they got welded together, they got molten together, and that is how the size kept on increasing. So that is why you will basically find that these asteroids and these meteors, they give you an idea about the elements which were present in the early solar system, which can enable us to understand which are the types of elements which are dominant in today's planet Earth as well. After all, when we talk about formation of planet Earth, now that is something which is explained by which theory? Formation of planet Earth is explained by the theory of accretion. Accretion means accumulation, means coming together. So various elements, they have come together, they have combined and then led to the formation of a large individual planet. So formation is associated with the theory of accretion. Okay, of accretion. That is coming together and accumulating. Okay, now when we talk about the early planet Earth, which was in a molten state at that point of time, you had various different phases of evolution of planet Earth. Planet Earth actually evolved from a hot molten ball of mass to the blue planet that we see today. So there were multiple different phases of evolution. Now, initially you had accretion or accumulation. That is, materials came together. Then you had a phase of stratification or arrangement in layered format, where the heaviest materials they sunk to the bottom and the lightest materials they floated to the top. That is why even today you'll find iron and nickel are dominant in the core of planet Earth, whereas the silicates of alumina, silicates of magnesium, they are something which are present closer to the surface of planet Earth. So that was during the phase of stratification or layering. I will write down these phases as well so that you have some idea what they are. So phase of stratification. Stratification means arrangement in layers. After that, while this was happening, by the way, while the planet was getting stratified, at that point of time, there was a massive collision which the planet experienced. And this was the collision with a giant Mars sized object named Theia. And that led to creation of and the formation of moon. Okay, so here after this you had collision with Theia, with Theia. That led to formation of moon, right? This is known as the giant impact hypothesis, the giant impact with Theia which led to the formation of moon. After that, you basically had the phase of degasification, where the gases which were trapped in the interior as the planet started to cool, all those gases escaped along with molten materials, leading to series of volcanic eruptions across the entirety of planet Earth. Okay, so this is where you had the phase of volcanic eruption or degasification. It is at that point of time when you had newer gases which were introduced into the atmosphere, because till that point of time planet Earth had primitive atmosphere largely dominated by two gases, hydrogen and helium. It was only after this phase of volcanic eruption that you had gases like ammonia, water vapor, carbon dioxide, methane, all of these were released. And that led to the enrichment of the atmosphere. It was this water vapor which led to the formation of clouds and accelerated the phase of rainfall. This is a question that UPSC has asked previously in the prelims in 2018. The question of multiple statement actually was that oxygen was present on planet Earth right since its formation. It is incorrect. Oxygen came or was actually introduced into the atmosphere only during the phase of degasification, not prior to that. Okay. After that, water vapor accumulated into the atmosphere led to the formation of clouds, dense clouds, and that is when you had the phase of torrential rain, heavy rainfall, or torrential rains. Okay. Now, this is how eventually you had the formation of a blue planet that we call as Earth today. Right? Now, when we talk about the layers of planet Earth, now broadly it is classified into three distinct layers. That is crust, which is thinnermost, then you have mantle, and then the innermost layer that is known as the core. Now, one general phenomena that you will observe is that as you move into the depth of planet Earth, the temperature keeps on increasing. Okay, so temperature increases with depth, and this is known as what? Increases with depth, and this is known as basically geothermal gradient of planet Earth. Geothermal gradient. Now, it is not uniform, by the way. It can vary from one region in the interior to another. It can always vary. Sometimes the geothermal gradient can be around 20 degrees Celsius per depth of kilometer. That is, if you go deeper by 1 kilometer, temperature can increase by 25 degree or 20 degree. Sometimes in the upper portion, it can be 16 degrees. Sometimes it can be 30 degree. So it tends to vary. But one thing which is consistent is that the temperature increases as you move into the depth of planet Earth. Now, the easiest analogy that you can have about the interior of planet Earth and the shape that planet Earth indicates is that of a coconut. So, when you consider a coconut, the ripened coconut that you have. Now, on the outer part, you have a brown shell. It appears to be hard, right? Brittle, but it is thin. So when you hit that coconut, I'm not talking about the outer coir of the or the outer shell of the coconut. I'm just talking about the coconut fruit. Now there, the brown outer part that you have, it breaks easily. It is brittle, right? It appears to be hard though. That is similar to the case of the crust. It is colder, it breaks easily, it is hard, but it does not have greater depth. It is very thin. Now, after you take out that brown layer of the coconut, you have the white flesh of coconut. Now that is in solid state. Now, similarly, mantle is also in solid state. Now, that white flesh of coconut, if you compress it with your fingers, does it break? No, it basically compresses itself or expands itself depending upon the forces that you put in that white flesh. Similar is the case of the mantle also. Mantle also, with the experience of various different kinds of forces, they can virtually expand, compress, they don't break. Crust breaks, mantle does not break easily. Why is that? There are two reasons for this. First, the kind of materials which make up for the mantle. You have high density elements like iron, magnesium, which make up the mantle. So they don't break easily. And secondly, the temperature is so high that if there is lot of pressure, materials will get deformed rather than breaking easily. For example, let's suppose if I keep a cold steel bar here, a very cold steel bar, and if I compress this, the steel bar will break from between. But if it is a hot, molten, almost molten steel bar, if I compress it, it can be compressed in any shape, a screw, a wedge, a ladder, anything that you want. Similar is the case of the mantle as well. You have immense forces which are acting in the mantle, which leads to the deformation of the mantle rather than the breakage. Now, just like the coconut, after you move through the brown layer, the thinner layer, then the white flesh, then you have water or liquid in the interior. Similarly, here also, you have molten material in the interior, which forms the core. Now, we discussed just now that in the early stage of formation of planet Earth, the heaviest material would get deposited at the bottom. That is the phase of stratification of planet Earth. Right. Now, when planet Earth was getting created at that point of time, the heaviest elements would be including iron, nickel, and so on. So that is why that iron and nickel are still dominant in the region of this molten core. However, there is a discrepancy. A discrepancy when you talk about the region of inner core. And this was not known to us for a long period of time till you had one individual scientist named Lehman who was actually studying the seismic waves as they pass through the interior of planet Earth. And Lehman, while he was studying the case of the seismic waves, he observed that one of these seismic waves, that is the P waves, their speed suddenly increased as they would pass through the center of planet Earth. That created a doubt that in the center of planet Earth, it must be something in a solid state. And that is where eventual findings told us that inner core is in a solid state. Now, why is it that inner core is in a solid state? And by the way, this name Lehman, this is important for you guys. Why? Because it is based on this discovery by Lehman that even today, the boundary between outer core and inner core is known as Lehman discontinuity. So that is why if you actually follow the logic of how it was found out, you will be able to retain it without rectifying it for a long period of time. Now, why is it that inner core is in a solid state? Understand the basic principle associated with any state of matter. So let's suppose we consider any state of matter here, which is in a solid state. Now, if I increase the temperature of this state of matter, it will melt, right? Now, when it will melt, will it retain the same shape? No. When it melts, it basically spreads like this. So I can say the volume has increased. The particles, they are free to move around, and that is why it has liquefied. But what if, let's suppose by some artificial means, I don't allow this material to expand from any side and I keep on raising the temperature? What will happen? Because this material is not getting any opportunity to expand anymore, it will not convert into liquid state. It will be in a superheated solid structure itself. It will not or never convert into molten state. Something similar is happening in the region of inner core. You have so much pressure from the overlying layers that inner core is not allowed to expand at all. And that is why, despite the high temperature, it stays in solid state. So, the reason in one sentence, excessive pressure, excessive pressure, not allowing it to expand. Okay. Now, here, many of you might have a doubt that why is it the case that only the inner core is feeling so much of pressure? Outer core is in a liquid state, but inner core, suddenly the pressure is so high that it is in a solid state. By this logic, even outer core should be in a solid state. The difference in pressure is huge when you consider the outer core's boundary and the inner core's boundary. Because even this outer core, which is in molten state, that is around 2000 kilometers thick. So 2000 kilometers thick. So imagine if you are on the surface of outer core, whatever pressure you are experiencing is only of that of crust and mantle. But when you come to the surface of inner core, you are experiencing that extra amount of pressure, right? Extra pressure of those 2000 kilometers of the high density molten material. And that is why the pressure keeps on increasing. That is why inner core remains in a solid state. Now, till now, what we have seen, mantle is solid, right? Outer core is molten, inner core is solid. But you have a variation within this as well. Where? When you come to a depth of around 200 kilometers, 160 to 200 kilometers from the surface of planet Earth, let's suppose you come to a depth of around 120 to 160 to 200 or 160 to 400 if you consider. Now, in this region, in the upper portion of mantle itself, you will find that you have the dominance of radioactive particles, right? Which radioactive particles? Here you have the dominance of uranium, and isotopes of potassium. Okay? Please do not confuse it with plutonium. I have seen many candidates because they think radioactivity means uranium and plutonium. So many of them have been writing in answers also plutonium. It is not plutonium which is dominant, it is the potassium element. Now, potassium is something that we consume on a daily basis. But why is it that here we are saying it is potassium which is radioactive? Not the normal elemental potassium that we are consuming. This is the isotope of potassium with a higher atomic weight. Okay, so isotopes of potassium. Okay, now these radioactive elements, they experience pressure from above and also high temperature, isn't it? They experience pressure and high temperature at the same time. Now, due to this high pressure and temperature, they go ahead with a decay. High pressure and temperature, they carry out a decay, and that produces heat. That produces heat. Now, this heat is sufficient to convert the materials present in that locality into a semi solid state. Semi solid, not a solid, not a complete liquid, a semi solid plasticky state. In order to relate to it, let's suppose you take a plastic ruler. You keep it on top of a flame in a candle. Now, the plastic won't melt like a liquid water flow. It will be very sticky. You expand it, it can get expanded. You compress it, it can get compressed. It will try to retain its shape form, but it is not solid. It is not a complete liquid. So that is the kind of material which is present at the depth of 160 to 400 kilometer. It is obviously very weak, present in the portion of upper mantle. So that is why this layer is what is known as asthenosphere. Astheno representing weak. That is the meaning of the term astheno, weak. So that is where you have asthenosphere. Okay? It is the semi-molten, semi-solid layer in the upper portion of the mantle. Okay? Now, after this, if you take a look at the overall aspect of each of these layers separately, we talk about the crust first. Now, crust is the lightest material across the entirety of the interior of planet Earth. Now, you might see mountains on the surface and you might wonder that how heavy or how dense they are, but they are not. In fact, these are some of the lightest materials that you will find across the interior. Now, this crust, obviously, why lighter materials? Because at the time of when the planet was getting solidified, the lighter materials floated to the top, heavier materials settled to the bottom, right? So that is where the lighter materials like the silicates of aluminium, etc., the oxides, they dominate the surface. Okay, so that is the portion of the crust. Now, ideally, the crustal thickness is different in the case of the oceans, is different in the case of the continents. And all those who have been reading NCRTs, this is where your NCRT has committed a mistake. So please keep your eyes and ears open. NCRT has mentioned it as incorrect. That is the density of crust. Okay, so we will discuss it right now. So basically, when we talk about this layer of the crust, so that layer of the crust here, you will have the case of the crustal thickness over continents and over oceans, underneath the oceans. Okay. Now, you will basically find that underneath the continents, the crustal layer is slightly thicker, around 35-40 kilometers thick. Underneath the oceans, it is around 5 to 20 kilometers thick. The nature of materials are also different. Underneath the continent, you have domination of low density materials. When I say low density materials, granitic rocks are dominant. Whereas underneath the oceans, you have basaltic rocks, which are rich in iron, magnesium, and so on. That is dominant underneath the oceanic crust. So that is why you have varying thickness and varying density. Oceanic crust is always going to be heavier as compared to the continental crust. Always remember that oceanic crust is always going to be much more denser and much more heavier. So for the oceanic crust, what we have is the density is roughly around 2.9 gram per centimeter cube. Whereas for the continental crust, it is roughly around 2.7 gram per centimeter cube. Okay, so that is where you have the difference per centimeter cube. So that is the difference between the oceanic and the continental crust. Let me summarize this here also. Oceanic crust, average thickness is how much? Roughly around 5 to 20 kilometers. Density is 2.9 to 3 gram per centimeter cube. Materials, mostly basaltic rocks. Okay, or mostly granite, basaltic rocks, correct? Right. Now, continental crust, Now this continental crust is, the thickness is roughly 35 kilometers. However, in certain areas where compression of the crust happens, for example, in the region like the Himalayas, where the crust gets compressed and folded, that is where it can get as thick as 70 kilometers in regions of folds, areas of folds. This basic data you should recall. Okay, this basic data you should recall. Rest of the areas I'm not asking you to retain the data. Okay, but this is very basic. Now here density is less. Density is 2.7 gram per centimeter cube, mostly made up of granitic rocks. Granitic rocks. Okay. Now, always remember this, that oceanic crust is going to be heavier. That is because of higher density, more materials per unit volume. That is why it is always going to be heavier, regardless of the thickness, it is going to be heavier than the continental crust. Okay. Now, after that, when we talk about the interior, now what is the nature of material that you find in the surface, that is the upper layer of the crust, as compared to what is the material that you find in the lower layer of the crust? There is a difference. And why is it so? For example, the ground that you are walking upon or living upon right now, the rocks on the ground, they are only facing the air pressure. That's it. No other pressure is being exerted. But when you go to a depth of, let's suppose, 30 kilometers or 40 kilometers, there is huge amount of compression. 30 kilometers thick rocks, they are actually exerting their weight. There is huge amount of compression. So as a consequence of that, you will find that in the lower layers, there is a difference in terms of the material arrangement, density, packaging, pressure, temperature, and so on. So there is that change in the property of the materials as you move from upper layer of the crust to the lower layer of the crust, from crust to mantle, from upper mantle to the lower mantle. Now these regions or zones where the difference is indicated, they are known as discontinuities. And in the case of the interior, you have various different discontinuities. So here, match the following kind of a question can be expected. So here, the discontinuity indicating the difference between the outer or the upper crust and the lower crust, that is known as the Conrad discontinuity. So Conrad discontinuity is the one between the upper and the lower crust. That is the case of the Conrad discontinuity. Then after that, between the crust and the mantle, that is known as the Mohorovic discontinuity, also known as simply the Moho or the Moho discontinuity, that is crust and the mantle. Then the upper portion of mantle and lower portion of mantle, lower mantle is more dense, that is known as Repeti discontinuity. Okay. Then mantle and core, that is differentiated by Gutenberg discontinuity. And then outer and inner core we have discussed, that is your Lehman discontinuity. Now for general studies for your exam, what is important for you to concentrate upon is the case of Moho discontinuity, Gutenberg discontinuity, and the rest as much as you are able to retain. Moho, crust and the mantle, Gutenberg, mantle, and the core. Okay. Now, then another area that UPSC focuses upon and asks questions about is the case of the various different elements which are present in the interior and in what abundance they are present. So when you consider planet Earth as a whole, you will find that iron is the most dominant element in the across the entirety of planet Earth. That is from the surface to the lower portion of the crust to the mantle to the core, iron is the most dominant element. So that is where Across the entirety of planet Earth, iron is most dominant, followed by oxygen, then followed by silicon. Top two or three you can retain. That is iron, oxygen, silicon. Now, oxygen that you see here is not the oxygen in gaseous state. This particular oxygen is the oxides of various different compounds which are in existence. Okay, so that is the case of Earth as a whole. But when you consider only the crust of planet Earth, so in the case of only the crustal portion, you will find that this dominance actually changes. Oxygen is the most dominant, followed by silicon. So iron is simply removed. In this particular case, it comes fourth in the order. Okay, so Earth as a whole, iron, oxygen, silicon. Surface, oxygen, silicon, aluminium, and then comes iron. Okay, this is the basic thing that you can actually retain. Then we come to the concept, what is geomagnetism? What do we understand by geomagnetism and why do we experience this? So, planet Earth actually behaves like a bar magnet, right? It does extend magnetic field lines across itself. And that property of Earth behaving like a magnet, that is what is referred to as geomagnetism. Now, when we consider this geomagnetism, why is it experienced? And what is the overall impact of it? So basically, when you consider the entirety of planet Earth, now you have a distinct layer of outer core, which is in a solid state, which is in a molten state. Inner core is in a solid state, outer core is in a liquid state, isn't it? You have outer core is in molten state, liquid state, isn't it? Now, when the planet rotates on its axis, this liquid layer also tends to rotate, and this liquid layer has got very high temperature. So, whenever the liquid layer has got very high temperature, it is dominated with iron and nickel particles. So, you can actually expect that due to the high temperature in this layer and due to the movement, some of the iron molecules and atoms will be such that electrons will leave the orbit, or you have charged particles which can get created. Because of high temperature, oftentimes what happens is, this is the basic chemistry 101 or the general sciences that you would have studied, that in an atom you have the nucleus and you have the orbits of the electrons, isn't it? You have nucleus where you have protons and you have neutrons, and you have the electrons which move around in orbits, isn't it? When you increase the temperature, then it can happen that this electron can be independent. And if this electron leaves the orbit, that means now the atom is positively charged. So, in a nutshell, in simple form, high temperature can lead to the creation of charged particles in the interior, isn't it? So, here, this outer core in molten state can have charged particles of iron and nickel. Particles of iron and nickel. Now, these charged particles of iron and nickel, along with the rotation of planet Earth, they are also rotating in a circular or a spiral fashion. And as a consequence of that rotation, they are able to create magnetic field lines like this. Okay. That is how they are able to create a series of magnetic field lines. Now, the extent of this magnetic field line, which is created by the Earth, that is also known as Earth's magnetosphere. So, these charged particles rotate in a spiral manner, in a spiral, right? As they rotate in a spiral, as a consequence of that, generate magnetism. Magnetism. Now, here You can also expect, as a natural derivation of this, that whenever you have this kind of a rotation of this molten materials, obviously distribution of molten materials is not uniform across the outer core. Some portion of outer core will have more denser amount of iron and nickel concentration. Some portion of outer core will have lower density of iron and nickel. So it is non-uniform. It can happen that the distribution of materials that can change over a period of hundreds and thousands of years. That is why the magnetic field lines across planet Earth, they also keep on changing. The magnetic and north and the south pole, they also keep on changing. In fact, every 700,000 years, the magnetic field lines of planet Earth are known to reverse itself. What was the magnetic north becomes the magnetic south, and vice versa. Okay, so because of, due to the change in in distribution of molten materials, magnetic lines change. Now these magnetic poles also change. Lines and magnetic poles change. Okay, now this is known as magnetic declination. Every 700,000 years, 700,000 to 800,000 years, magnetic field lines reverse itself. Reverse itself. Okay, so that is basically the case of these geomagnetism. Now, why we experience geomagnetism? Because of the molten outer core, not because of the solid inner core, because of the molten outer core. Okay, now what is the benefit out of it? By the way, one other aspect of this kind of magnetic field lines is another important aspect that you have to understand, which is the derivation in environment ecology. That is, many of the migratory birds, for example, you have the Siberian cranes and so on. Now, it is suspected that they actually fly north to south or south to north based upon the magnetic field lines that the planet Earth has. Okay, so if a statement is framed that do species get impacted by the magnetic lines of planet Earth, the answer is yes, it is impacted by that also. Okay, now here, that is what we refer to as the magnetosphere. So, the magnetosphere, basically, you will observe that you have the Earth's magnetic field, which acts as a protective shield. The charged particles which are thrown away, which are emanated from the sun, so that is held or that is prevented by the Earth's magnetic field. Okay, so this is your magnetosphere. And these charged particles, they have very high amount of energy. So this charged particles, basically you will observe that as they move, as they tend to move, they basically are deflected by the Earth's magnetic field lines. Had the magnetic field lines not been there, then what would have happened? These charged particles would have bombarded the atmosphere, and as a consequence, the atmosphere is completely uprooted. That is something which has happened across or in the case of Mars. Mars was the one where you don't have the magnetic field lines because the outer core in Mars had solidified long time back, around 3.5 to 3.8 billion years ago. It is suspected that the outer core of Mars actually solidified. Now, once it solidified, means what? That it did not have any active magnetosphere anymore. So the charged particles from the sun would bombard the atmosphere of the Mars, and the entirety of the atmosphere of Mars was actually unraveled or was taken away. So that is the impact overall of the magnetosphere. This is important this year. It was asked in the mains previously. It can be asked in the prelims as well. Now, that is the case of geomagnetism that we have considered. Now we come to the case of rocks. Now, in the case of rocks, this is something that UPSC has been focusing upon since 2022. Again, earlier it was asking questions from rocks pre 2010, but after that there was no question. But again, recently you have had questions associated with rocks. Now, what do you need to understand or take a look into rocks when it comes to the prelims perspective? So for your prelims, you need to understand in the portion about the types and classification. Okay, types and classification. So for example, what are the different types of organic sedimentary rocks? What are the different classifications of metamorphic rocks? Okay, what is the difference between a plutonic igneous rock and a hypabyssal igneous rock? Both of them are intrusive, right? What do we understand by contact metamorphism? What do we understand by hydrothermal metamorphism, regional metamorphism, dynamic metamorphism? So these are the areas which you can explore in order to have a better idea and better preparation for your prelims also. Okay, just knowing that there is igneous, sedimentary, and metamorphic, that should not suffice. You should go into the depth also. And we will also talk about the case of the porosity and the case of permeability of the rocks as well. Now, when we talk about these rocks, so basically, here the broader classification is of three types. You have the igneous, then you have sedimentary, sedimentary, and metamorphic. Okay, this is the broader classification. Now within this, you have the sub classification as well. What is the sub classification? In igneous, based upon the formation, you have intrusive and extrusive, intrusive and extrusive. And then you also have, based upon the chemical property of this, what are the minerals which are dominant in these igneous rocks, you basically have the classification as mafic, felsic, and ultramafic. Okay, you have felsic, feldspar and silica, mafic, and ultramafic. Okay, that is the classification. Then in sedimentary, what is the classification that you have? In sedimentary, the classification is you have clastic sedimentary, chemical sedimentary, and organic sedimentary. And then you have the subclassification of organic sedimentary as well, that is siliceous, carbonaceous, and so on. So let us take a look at all of this in a broader criteria and let us understand them. So igneous rocks are formed why and how? By the solidification of the molten materials. Now, that solidification of the molten materials can happen in the interior of Earth's surface or can happen on the exterior of the Earth's surface. Now, and listen to this very carefully. If these molten materials, imagine you have a lot of molten materials which are present in the interior. If they start solidifying in the interior itself, and compare that to lava which is on the surface and then it starts solidifying, there will be difference in the process and the speed of solidification. That is, the material which is present in the interior and there itself, if it starts to solidify, it will be a slow cooling process. Slowly and steadily it will lose its heat. But when the lava erupts on the surface, it solidifies almost instantaneously, right? So that is basically a difference that you experience. And why are we concerned with that? Why should we be concerned that whether the solidification is happening quickly or whether the solidification is taking some time? Because that impacts the size of the crystals and the size of the particles in each of these rocks. And that is the difference, basic difference between your intrusive and the extrusive rocks that you have. Okay. So here, when we take a look at these igneous rocks, so basically, when they solidify, that is when the particles they attach with each other and they start the formation of these crystals and the crystalline formation. So basic classification we have discussed on the basis of formation. This is a quick revision and recap for all of you. On the basis of formation, you have intrusive and you have extrusive. Extrusive. Intrusive, further classified as plutonic and hypabyssal. Hypabyssal. Right? Then, on the basis of chemical property, you have the classification as felsic, mafic, and ultramafic. Okay. Now here, felsic means what? Felsic means it is dominated by feldspar and silica. Does not mean that iron and magnesium is not present. Iron and magnesium is present, but is present in very little concentration. Okay, but iron and magnesium, they are present even in the felsic rocks. Okay, then mafic, they are dominated with iron and magnesium. And here, largest proportion of iron and magnesium. Okay, so that is the basic classification of the igneous rocks that you can have based upon the formation, the region of formation, and based upon the chemical property as well. Now, overall, when you consider the difference between the intrusive and the extrusive rocks, so in the case of intrusive rocks, you will find that the rate of cooling is very slow. Now, when the rate of cooling is low, that means the crystal formation takes ample amount of time and you have proper crystalline formation and you have a coarse grain texture, a larger grain size, right? Because slow cooling means the grains are able to form multiple bonds with respect to each other. So you have a larger crystal size in this. Whereas when you talk about the extrusive rocks, the lava which spreads on the surface and cools down, you have fast cooling, immediate cooling, now cannot crystallize properly, and that is why the rocks are very fine grained. So that is the difference between the case of extrusive and intrusive. Okay, extrusive and intrusive, right? Now, then after that, when we talk about the case of the interior, so within the interior also, you have different rock formations, plutonic and hypabyssal. Okay, now one is formed at a greater depth, one is formed closer to the surface. That is the difference between plutonic and hypabyssal. Both are formed in the interior, but one which is formed at a greater depth, that is plutonic, and closer to the surface, you have hypabyssal rocks. That is the basic difference. Okay. Now, when they solidify in the interior itself, they solidify themselves in various different types of shapes, various different types of patterns. And this different shape and pattern, based upon how they have solidified, that is also what are known as intrusive volcanic landforms. for example, batholith, laccolith, lopulith, facholith, sills, dikes, all this that we will take a look into it later as well. All of this are nothing but your intrusive igneous rocks. And it is classified purely based upon the shape in which solidification has happened. If solidification has happened where the entire molten material of the magma chamber in itself has solidified, it is a batholith. If it has solidified in vertical columns while it was trying to come out, it is dike. If it has solidified in a dome like structure away from the magma chamber, it is the case of a laccolith and a lopolith also. So, like that, you have the various classification. Okay. Now, after this, some of the basic characteristics of igneous rocks: crystalline in nature, very hard rocks with poor permeability. Okay, they don't allow lot of water or materials to pass through them, right? So that is why even in the case of underground reservoirs of water or petroleum reserves, you will find that the lower bed is made out of igneous rocks, which holds them together. They do not have layers like that in sedimentary rocks, and they do not contain any fossil remains because obviously they have been created due to solidification of lava or magma. Now, based upon the mineral composition, we have seen you have felsic, mafic, and also ultramafic. What are felsic? So, here, larger proportion of feldspar and silica. Okay, so for example, quartz is one of those, feldspar is one of those. Now, these are of the lowest density of all the three types of chemical types that we have seen of the igneous rocks. Felsic rocks are of lowest density. They are light colored in texture also, and that is where they are always lighter in weight also. Many of the continental rocks are actually the felsic rocks. The rocks that you see on the surface in the various landforms, most of them are felsic rocks. Then we have what are known as your mafic rocks. Mafic rocks, they are rich in iron and magnesium. So, iron and magnesium and ferrum. So, these are dark colored, greater in density, higher in density. And then you have the ultramafic. They appear very dark green in color. Dunite, for example, certain types of olivine also, they are ultramafic. That is where the proportion of magnesium and iron is very high, proportion of silica is very, very low. Then we have the case of sedimentary rocks. Okay, sedimentary rocks. Now, how are they created first of all? So, sedimentary rocks, they are created by the solidification of deposits. Okay, you have various different deposits in a region, right? And these deposits, they eventually will solidify. Okay, so initially, what tends to happen is that first process in this, if you consider the process of formation of sedimentary rock, so the process, first of all, is deposition, right? You have deposition of materials. After deposition, what happens? These materials, they compress each other, right? And that is when it becomes a bit more compact. So that is when you have the phase what is known as compaction. Okay. After compaction, the materials, they bind together with each other. For example, let's suppose you consider a flowering pot with soil and you keep it outside, right? And you leave it outside for a few days. After, let's suppose, 2 or 3 months, automatically you will find that the soil has hardened. It has become rock type. So that is because all the various different particles, they have combined together. Now that is the final phase. That is what is known as cementation. Okay. So you have these three processes which are followed. And this is what is also known as the process of lithification. What is lithification? Lith refers to rocks. So lithification, the formation of a rock. Formation of rock. Okay. Always remember that lith represents the case of rocks. That is why lithosphere, that is the solid portion of crust and upper mantle, then batholith, laccolith, lopolith, phaccolith, all of this, lith is common. Lith is representative of the rocks. Okay, so that is the case of the entire process of the formation of sedimentary rocks. Now, because they are formed out of multiple deposits and layers and different non-uniform materials coming together, that is why they will have lot of weaker points in the various different regions. So they can break easily. These sedimentary rocks, they are considered to be softer rocks because they can break easily. Okay. Now, when we say they can break easily, that means they can easily crack from the various different joints that they have. And because you have layers, that also means it will have deposits of fossils, fossils of animals, plants, all of them. Now, how do we classify the sedimentary rocks? Now, in the formation of sedimentary rocks, what will be present in the sedimentary rock? A very important stage is the stage of deposition. So the classification of sedimentary rock is actually based upon how this and why this deposition has happened. Okay, so based on the deposition cycle, if let's suppose an igneous rock has actually broken down and various materials from the igneous rocks have been deposited, and then you have compaction cementation, so that is a kind of mechanical weathering leading to deposition, right? Or let's suppose there's a chemical action in a water body somewhere which has led to deposits of materials underneath the water body. That also is a form of deposition, right? So based upon that, you have the classification as clastic, chemical, and organic sedimentary rocks. What are clastic rocks? For example, let's suppose you have a large igneous rock, right? Due to rain, river water, glacial action, etc., this larger rock has been disintegrated and various materials have been deposited. And these materials then solidify, forms a sedimentary rock. But then this deposition has been created how? Because of the mechanical weathering of this larger rock, isn't it? So that is the case of the clastic sedimentary rock, that is formed from mechanical weathering debris. Example, sandstone, siltstone, etc. It is this sandstone which dominates the Mughal architecture that you observe. For example, the Agra fort, then you observe Akbar's tomb in Sikandra, then you observe the Red Fort, all of them made out of sandstone, because it would be very easy to carve various architectural designs in these softer sandstones. Okay. Then you have the chemical sedimentary rock. Chemical means you have a chemical action. Now, that chemical action has led to deposition. For example, let's suppose you consider a layer of water in a shallow sea, right? Now, in this water, you have dissolved iron particles, which are dissolved in the water. Okay, it is not deposited. Very small, tiny particles dissolved. Now, let's suppose you have underwater plants. Now, these plants will carry out photosynthesis, isn't it? And these plants will end up producing oxygen as a result. Now, this iron and oxygen will react and will form iron oxide, which is solid, and this will create deposits. And that is how deposits of iron ore can be found in many areas. Okay, so that is basically where you have this iron ore which gets deposited. Okay, so that is a chemical reaction between dissolved iron and oxygen which was released. That chemical action has led to the formation. So that is chemical sedimentary rock. Example, iron ore, even limestone that you have. Even in limestone, you will observe that you have calcium carbonate, which basically gets deposited, and that is where you have the formation of limestone. That also tells you that wherever limestone is to be found, that region historically would have been underwater. That is one of the evidences to indicate that Himalayas at one point of time were actually underwater regions of the Tethys Sea. Even Rajasthan, where you have the presence of limestone and marbles, the presence of limestone indicates that it had a geological past where it was underwater. Then you have the organic sedimentary rocks, where the deposition has happened by the organic process. Let's suppose the deposit of marine animals, deposit of vegetation. Now, deposit of marine animals leads to the formation of crude oil, petroleum. Deposition of vegetation leads to the formation of coal, right? So, all these are the cases of organic sedimentary rocks. But you have further subclassification as well. What is the further subclassification of this organic sedimentary rock? So here you have the classification as calcareous, siliceous, and carbonaceous. What is the difference? So when we talk about calcareous rocks, so sediments derived from the skeletons of the uh, organisms like fish, for example. So very, very rich in calcium compound. Example, calcite, right? Many small microbes and their skeletons, they can concretize almost. So that is calcite. Then, other than that, when we talk about carbonaceous, so here you have the deposit of marine animals or dead vegetation leading to the formation of crude oil. That is why even today, wherever you have oil, that means that region is either underwater today or was underwater historically, because oil is largely formed because of deposition of marine organisms. That is why, as I told you, in Rajasthan you had history of water encroachment and shallow sea formation in Rajasthan. That is why in Rajasthan you will be able to find oil, natural gas, limestone, and even marble, which is created because of metamorphism of limestone. So, if you know the geological history of any particular place, automatic deduction you can make of the various mineral compounds to be found in that area also. Then you have siliceous rocks. Now, siliceous rocks, basically the microorganisms which are found in the oceans. For example, you have radiolarian compounds or you have globigerina, all of them. Now, the diatoms, the sponges, all of them, they aggregate, they come together, and compaction of microcrystalline quartz. So that is what leads to formation of siliceous rocks. Then you have metamorphic rocks. What are these metamorphic rocks? Metamorphic means change in the basic nature. So, any kind of rock, when it is exposed to high temperature or high pressure, it can get converted into metamorphic rocks. High temperature or high pressure or high pressure. Okay. Now, here the classification is based upon certain criteria. The classification of metamorphic rock can be done, first of all, based upon appearance. Based upon appearance, it can be classified into layered or foliated, where they appear to be layered, and non foliated. Okay, foliated and non foliated, right? Then, after that, based upon formation. Formation. Okay. So you basically have, for example, regional metamorphism, hydrothermal metamorphism, contact metamorphism, dynamic metamorphism. So that is based upon the process of formation. Okay. So when we talk about foliated, non foliated, it is basically what kind of materials were present and how they are being compressed. So, foliated in that you have a distinct layered structure which becomes very apparent, which is very visible. So, you have that distinct layered formation in the foliated rocks. Non foliated, you don't have the layered formation, it appears to be uniform. But overall, the type of rocks which are created due to metamorphism and their property, that is something which is determined and dependent upon. For example, any rock, what is the amount of fluid which it has? Right. Now, how that will determine the property of the rock? If greater amount of fluid, upon compression, you will have greater heat produced, fluid can get converted into steam, and that can alter the rocks to a great degree. Right. So amount of fluid present also impacts the type of metamorphic rocks created. Then what is the time duration for which the materials are exposed to the heat? Other than that, what is the overall time duration for which they are exposed to pressure? So time, that is temperature, time for pressure, and the fluid content. These factors determine the nature of the rocks. Now, the types of metamorphism based upon the formation type, you have contact metamorphism, regional metamorphism, and hydrothermal metamorphism. Now, let me give you just a brief about it. I will give you the written portion also. Contact. Contact means what? Apply your logic that it is getting in contact with something which is making metamorphism possible. Any rock is getting in contact with something or some place due to which it is converting into metamorphic. So, just by contact, can it be a determinant or induced by pressure? No. Contact means only when you have very high temperature. So, when let's suppose a rock in the interior gets in touch with high depth temperature magma, molten material, immediately it continues and starts to metamorphose. So, here in contact metamorphism, temperature is dominant factor, is a dominant factor. Okay. Then you have regional metamorphism. Regional. Now, here there is no mention of contact, by the way. So, here in a particular area, let's suppose the plates are moving with respect to each other. Now, Indian plate and the Eurasian plate, they are converging, they are colliding. There is subsidence which is happening, subduction which is happening. Now, in that particular case, the pressure exerted on the layer which is undergoing subduction is huge. And immediately, what that would mean is that metamorphism would happen due to high pressure. Right? So, here you have two categories: dynamic metamorphism, dynamic, and you have static. In this, pressure is a dominant factor. Is a dominant factor. Okay. So when we say dynamic, for example, let's suppose metamorphism due to plate movement, subduction, etc. When we say static, let's suppose a layer of rock is present at a depth of 50 kilometers, 100 kilometers in the lower portion of the crust. Now, the already existent weight is so high, it will get converted into metamorphic rocks. Example I will give you. Northern Indian plains. Now, when we talk about North Indian plains, that is the Indo-Gangetic plains, depth of sediment is estimated in certain areas to be 2 kilometers to 3 kilometers. Particularly in the region of Western UP, that is where the estimated depth is 2 kilometers to 3 kilometers. Why do we say estimated depth is 2 kilometers to 3 kilometers? Why are we not saying exactly 2,500 meters or 2,350 meters? Or why don't we have the exact figure of that? Because what lies underneath those sediments are metamorphic rocks. and we are not certain whether that metamorphism has happened owing to the pressure of the sediments or the metamorphism has happened owing to the already existent igneous rocks. What that tells you is that even the pressure of 3-kilometer deposit of sediments can lead to metamorphism, and that is static metamorphism, that you have a region on top of which pressure is exerted, it will metamorphose. So here, overlying pressure, overlying pressure. Okay. So that is the case of regional metamorphism. Then you have what is known as hydrothermal metamorphism. What is hydrothermal? That is very heated water or steam coming out from the interior. Now that exposes the rocks to very high temperature, and that can also lead to metamorphism. Right? Even in Himalayas, in certain areas, you have hot springs and geysers, for example. Now, why do geysers and hot springs exist in Himalayas? I hope we are aware about regions like Manikaran and various other warm pool regions in the area of Himalayas. But why do they exist in Himalayas? After all, you don't have volcanic eruption in Himalayas. But where is it and why is it that you have these hot pools which are in existence? The reason is because of compression. When the rocks get compressed beyond a certain proportion, they produce heat, what is known as heat of compaction. Right? Now, that heat which is produced, that tends to vaporize the groundwater which gets in contact with that heated rock. And that is why you basically have the formation of this steam. So many of you, when you think about it, that basically it is due to the contact with the inner molten material, etc. It is not the case. Imagine if this is a rock, if I were to compress it with great amount of energy, it will get hotter. When it gets hotter, water in contact gets converted into steam, and that will tend to metamorphose the rocks surrounding it. So that is your hydrothermal metamorphism. So this is the three different types of metamorphism. Contact, when magma intrudes into deep crustal rock, there also, just by the virtue of contact with high temperature, metamorphism can occur. Temperature is the main factor. Pressure comparatively is a minor factor in this. Then regional metamorphism. Now here, the rocks, their shape, their characteristics are changed because of the impact of pressure. Okay. Here, temperature is the minor factor. Now, two types you have: dynamic and static regional metamorphism. These are the two types that you have. Dynamic, so that is plate movement; static, due to the overall pressure which is in existence. Hydrothermal, because of hot water, pressure of the water mass, then hot gases and water vapor, they circulate through the cracks. That leads to hydrothermal metamorphism. Example: hot springs in Yellowstone. Now they will alter the shape or the characteristic, the coloration of the rocks, because various compounds like sulfur, various hot water vapor, they get in contact and they will alter the characteristic. Now, one particular area from where UPSC has been asking couple of questions, now it has started focusing about that in the prelims now, is the concept of porosity and permeability. What is the difference and what is the meaning of this porosity and permeability? So when we consider any material to be porous, what does it mean? And when we consider permeable, what does it mean? So, permeable, what is the meaning of permeable and what is the meaning of porosity? Porosity, measure of the vacant spaces in the material. So, how easily it can absorb, that is rock, can absorb liquid like water, oil, etc. Okay. For example, take the case of clay. Now, clay is a material which can absorb lot of water, so it is porous. Okay. Then, what is permeability? Permeability is the case where it allows the water to pass through, right? Any material which allows the water to pass through, that is permeability, right? Allowing water or liquid to pass through. For example, consider chalk. When you consider chalk, now in chalk, you put in lot of water, it will absorb lot of water. You keep on putting in more water, water will start passing through as well. Right? So that is the case of permeability. Whereas in clay, you put in water, it will allow the water or it will absorb it, but it won't allow the water to pass through. That is why in your sealants, in various different places, you would have observed that you have a case of the clay lining, which is oftentimes done. Okay, so that is the case of porosity and permeability. Permeability is the measure or the ability of a material to transmit fluids, right? Now, a rock may be extremely porous, but if the pores are not connected with each other, it will not be permeable. Okay, it can have lot of pores, but if the pores are connected, only then water will be able to pass through. If they are not connected, it won't pass through. Then we come to the other topic, that is origin of continents and oceans. Okay, so origin of continents and oceans, this is relevant based upon the theories. Last year also you had a direct question asked about continental drift theory. So based upon the various theories, this is a portion which is very relevant for your examination. So here we are going to start with the continental drift theory, then the convection current theory, seafloor spreading theory, and eventually the plate tectonics theory. Now, starting first of all with the case of continental drift theory. Now, what is this continental drift theory about? Now, continental drift theory was proposed by Alfred Wagner. Okay, proposed by Alfred Wagner. Now, Alfred Wagner was a meteorologist by profession. Okay, he was a German meteorologist. Why it is important that you know he was a meteorologist? Because he did not have specialization in geomorphology or the surface of planet Earth. He had specialization in climate. And he would study about the changes that Earth's climate have experienced and that the Earth's climate is going through. So that is what Alfred Wagner was about. Now, based upon the various works which were already there. So, first, how the story goes is that Alfred Wagner was presented by his friend with a world map, the detailed world map. For the first time, when he took a look at the world map, he found increased similarities, for example, in the eastern region of South America, then western area of Africa. They have similar shape. Then you have the shape here and the shape of the Arabian Peninsula. Again, similar shape. So, like that, he found many areas which had similar shapes. So, that put a doubt in his mind that all of these could have been connected together. So, he started collecting evidences, various evidences from pictographic or the visual evidence of a jigsaw fit to the geological evidence to climatological evidence. All of them pointed to the fact that you basically had a creation or the existence of a supercontinent. That supercontinent was named as Pangea. That Pangea split, and then you have the present day shape of the continents and oceans. So that is your continental drift theory. So earlier, around 230 to 50 million years ago, you had one large supercontinent. That supercontinent would be referred to as Pangaea. That Pangaea eventually broke, disintegrated into two different parts. You had Laurasia and you had Gondwana land. Gondwana land. This then eventually broke. Now, at the time of Pangaea, you had a global ocean around Pangaea. You had one large ocean, which today is considered to be the ancestor of the Pacific Ocean. That was your Panthalassa. Panthalassa. Okay. And here you had an ocean in between. That would be your Tethys. Eventually, this would disintegrate into the present day shape of continents and oceans. Okay, this would disintegrate into the present day shape that you have of the various continents and oceans. Now, why do you have the shape of the continents and the oceans is something that the world had been trying to figure out for a very long period of time. And that is where the continental drift theory comes into prominence. Okay. So that is what the continental drift theory is, that the present day shape of the continents and the oceans that was initiated by Pangaea. Now this was supported by a series of evidences that Alfred Wagner had accumulated. Now what were these evidences? The evidences basically were of various categories. You had visualistic, that is, the continents appear to fit in the form of a larger jigsaw puzzle. What would be a jigsaw fit, a typical jigsaw fit? So all the continents would fit with each other. So that is the jigsaw fit. Okay. Then you had the geological evidence. Now, geological evidence, the nature of rocks in the region around Appalachian Mountains and those in the Scottish Highlands. They have the same rocks of the same time period and the same nature, which means at one point of time, these two would have been together and rock formation would have happened. Then, even the type of rock formation that you find in the Brazilian highlands and the region of the Western Africa, the rock types are same. So, you have similar rock types. Okay. But this is not the only one. You also have the evidence of placer deposits. Placer deposits, what they are, we will consider. That is, placer deposits from the region of Brazil to the region of West Africa. The gold deposits that you have in West Africa, that is actually created from the Brazilian highlands. Then after that, you have climatological evidence. Climatological evidence. Now, this climatological evidence is what? That is the glacial formation, glacial evidence, glacial deposit, glacial striation. All of this are dominant in regions of South America, southern part of Africa, peninsular India, Australia, and so on, indicating ancient glaciation in these areas. In the present day time and age, these areas don't experience glaciation, but historically, they have evidence of glaciation. For example, when you consider the Godavari river system. Now, in Godavari river system, uh, deposits of 200 million years ago to 10 to 20 million years ago, they indicate the coal formation. Godavari basin, even today, we extract coal. But if you dig beyond that depth, then you will find glacial deposits in the region of the Godavari basin. Now, that means historically that region has experienced glaciation. So, how is that possible? only possible if India was present closer to the South Pole. India was attached with Antarctica. Then you have the paleontological evidence. Paleontological evidence. That is the fossils that you have, right? The fossils of the various organisms and the species that you have. That is the paleontological evidence that we have, that these organisms, their fossils are found in multiple continents together. That could only have been possible if the continents would have been joined together. So these are the evidences, starting with the jigsaw fit of continents. So you have the case of South America and even Africa. So there, the shape is very, very similar. Then after that, you basically have the geological evidence. Geological evidence of various different types. Geological evidence. So in geological evidence, you have the case of similar rock structures of Appalachians and Scottish Highlands of various places. This was asked in last year's prelims examination. Appalachians and Scottish Highlands, and then Brazilian Highlands and West Africa. Highlands and West Africa. Okay. Then other than that, you have the role played by placer deposits. What are placers? So for example, let's suppose you have a rock structure, a mountain system. Now in this rock structure, let's suppose you have the presence of some material which is not soluble in water, like gold. Okay, which is not soluble in water. Because if it is soluble in water, then the water will carry it to the ocean and the sea. Now here, let's suppose a river is draining. It will erode this gold and it will be depositing the gold somewhere here, which is far away from the source rock, right? So these are known as your placers. Placer deposits. Okay, and this is your source rock. So the gold deposit of West Africa is actually from the source rock of Brazil. We have placers in India also. For example, from the Chota Nagpur Plateau or the Ranchi Highlands, you have a river that originates, that is river Subarnarekha. Now that Subarnarekha carries that some amount of, or used to carry some amount of gold to be found in the region and deposit it in the lower stretches. That is why the name of the river was also named as Subarnarekha. So that is where you have the placer, that is gold deposits which are created. Okay. Then glacial evidences. So wherever glaciers exist, the movement of glacier creates a kind of a linear marking or a linear shape. And these are known as the glacial striations. Okay. Other than that, wherever you have glacial movement, as a result of this glacial movement, you have deposition of sediments, glacial sediments. These are known as tillites. So tillite deposit is also the evidence of ancient glacial action. Now, where is it that you find these tillite deposits? So across the world, you find it in the southern part of South America, you found it in southern part of Africa, in central and southern India, in southern Australia. That is where you end up finding these stellite deposits. Now, presently, in these areas, glacial action does not take place. So, the only thing which can explain the glacial action is that all these continents would have been together and then they have disintegrated and have actually moved away. That is why you have the evidences of this glacial striation. Then you have the paleontological evidence. Paleontological evidence is what? That is, you have the fossils of species found across continents. For example, you have Mesosaurus. Now, Mesosaurus, a freshwater reptile. Now, the fossil of Mesosaurus would be found in South America as well as in Africa. Now, that would actually indicate that these regions would have been together. Otherwise, how is it that this freshwater reptile could have swarmed through these oceans, saline oceans? In case you are wondering, why can't we have these species in different continents simultaneously? They can originate simultaneously in different continents. It cannot happen because that defies the basic law of evolution, the origin of species as demarcated by Charles Darwin. It defies it, right? You cannot have simultaneous same species simultaneously evolving in different parts. You have the species getting modified and you have genetic variations. But if the same species skeleton is found in different regions, means those regions would have been connected together. Okay, so that is the case of paleontological evidences. So, which are the species? You have Mesosaurus, Cynognathus, Glossopteris. Glossopteris was in news recently because of the fossilized evidence of Glossopteris found in southern part of India. That is why it was in news recently. And you also had Listosaurus. So all these species, their fossils are found in different places. Now, the continental drift theory, we know that you had Pangaea. Pangaea broke into Laurasia, Gondwana land, and that is how you had the formation of the various different regions. Now, Wagner made certain assumptions. What were the assumptions made by Wagner? What were the various assumptions? So the assumption that was made was basically that continents are floating. Continents float on the oceans like boat on water. Like boat on water. Okay? And this water is the case of oceans, right? Now he said continents are basically represented of silica and aluminium, that is Sial, and oceans are dictated by silica and magnesium, that is Sima. So Sial would float over the oceans like a boat on water. Now anything which floats, it experiences an upward force. For example, let's suppose you have water, and on top of it, let's suppose you have a boat. So if the boat is floating, it will experience an upward force which will allow it to float and not sink. That is your force of buoyancy. Force of buoyancy. Okay. So here, as per this assumption, continents would experience a floating force, that is force of buoyancy. Okay, buoyancy. So that is something which Alfred Wagner had actually proposed, right? So these are the assumptions which were made, but he said that there are two forces which are responsible for the entire breakup of the continents. Why the continents actually broke up. So that is where he cited the reasons as two forces. but that would be to explain the two type of movements experienced by the continents. Which are the two types of movements experienced by the continents? First was basically a westward drift. By that, Wagner would be able to justify how North America and South America are moving away from Europe and Africa, respectively. Because remember, he said that Appalachians and Scottish Highlands have been formed at the same time, means they were together. Brazilian Highlands and the Ghana coast had similar properties, so they have moved together. Means North America and South America have moved away from Europe and Africa. So that is the westward drift of continents. That is one type of force or movement. The second basically would be that India, South America, Africa, Australia, Antarctica, all of them were present closer to the South Pole. Now, from there, South America has moved north, Africa has moved north, India has moved north, Australia has moved north, isn't it? So, that is flight away from the poles, movement away from poles. From poles. Right? Now, this westward drift of continents, the reason that he cited why this was happening was basically your tidal force or the force of gravitation which would exist between the sun, the moon, and the earth. That is tidal force or the force of gravitation. Of gravitation. Okay. And then movement away from the poles, he cited this as in German as Polflucht. Polflucht. And this basically was attributed to combination of force of buoyancy and centrifugal force. Okay, so basically you have two different forces explaining the different type of movement that you have. It is not associated with Coriolis force. It is associated with centrifugal force. Centrifugal force, any object which is moving in a circular fashion, in a circular direction, when it is pushed away from the center, that is the centrifugal force. So that is the aspect of the centrifugal force and the force of buoyancy. Both these were incorrect assumptions. Both these were incorrect assumptions. And that is why his theory was actually rejected. It was not accepted. The entire theory was rejected because of the reasons which were cited. Okay. Now, then came the convection current theory. Now, convection current theory was provided by Arthur Holmes. Arthur Holmes. Now, Arthur Holmes, a famous physicist who worked with Rutherford, he was well known for example, radiocarbon dating. That is, how do you calculate the age of older rocks, right? So that is where you carry out carbon dating. So Arthur Holmes was a renowned physicist who was well known for these activities. Now he became interested in geography and he started exploring the impact of radioactivity and heat in the case of the Earth's surface. So when we talk about Arthur Holmes, he talked about that how heat from the interior escapes to the surface, impacting the formation of different landforms on the surface. So heat from the interior, from interior, that is where? That is from the region of two places. That is Gutenberg discontinuity. What is Gutenberg discontinuity? That is the region between mantle and core. From there heat is produced, and asthenosphere. From these places, heat from the interior comes closer to the surface, right? Escapes to the surface in the form of convection current. In the form of convection currents. Okay. So that is the case of the convection current theory. Now, what is convection current? So basically, you have hotter materials rising up and spreading around. So that is the case of the entire convection current theory. So let's suppose you consider this to be the crust, and then you consider the mantle. So heat from this region would emerge, would escape, and it would then form a convective current or a convective cycle. Okay, that would be the convection current theory. Now, it could have impact on the surface. For example, in the region where the convection current is rising, it could lead to the land getting uplifted, that we are experiencing today in the region of Colorado Plateau in western part of North America. Again, a quick reminder for all of you who are slightly not very confident in where Colorado Plateau is, where Columbia Plateau is. Do attend the mapping sessions on Monday, Wednesday, and Friday at 5 p.m. 1 hour mapping session, Monday, Wednesday, and Friday. That will help you recall all these aspects very, very clearly. Okay, on special classes. Now, Colorado Plateau, you have the upliftment, which is because of this convection current. Then, after that, here, it could also lead to volcanic eruption. Okay, it could also lead to frequent volcanic eruption. Then, in these areas, the land could simply sink because materials underneath are sinking. So, you can have upliftment of land, you can have subsidence of land, you can have divergence of land. So, this loss of heat from the interior can bring changes to the landscape. That was the convection current theory. But tell me one thing, why do we have so much heat in the interior? Despite the fact that the planet has been cooling down for 4.5 billion years. So, what are the various sources of heat when we talk about the molten liquid outer core and so on? What are the sources of heat? So you have two major distinct sources of heat in the interior. Two reasons why heat level is very high. One is the case of residual heat, right? Residual heat, that is heat which is trapped since the time of formation of planet Earth. So you have residual heat. Okay. Then the other heat is very good, Devendra. It is basically the case of pressure, the compaction, the heat produced due to compaction. That also produces large amount of heat. Heat due to compaction. Compaction. Then after that, another reason is radioactivity, particularly in the region of asthenosphere. Right? These are the three reasons or the three sources of heat that you have. Okay, it is this heat which accumulates and this heat which starts to actually spread around. Okay, so this you should be clear about. Sources of heat. Okay, so that is the case of the convection current theory. It managed to explain how heat from the interior would escape eventually to the surface. Then we have the seafloor spreading theory. Seafloor spreading theory was postulated after the Second World War, right? So, post Second World War, why it was postulated and how it was postulated? Basically, during the Second World War, the Germans unleashed a new form of weaponry, that is the U-boats or the submarines. Now, these submarines, they would lie underwater and then they would suddenly emerge and carry out attacks on the ships, leading to huge amount of damages. Now, what would happen is that the various naval forces in US, France, all of them, they started working on the sonar systems, the underwater radar systems, so that they could detect these submarines. The war ended, but these systems remained. With the help of these systems, a naval expeditioner, American naval expeditioner named Harry Hess, he studied the seafloor. And based upon the study of the seafloor, Harry Hess came upon certain observations. First of all, he found out that the seafloor is very young. The continental crust can be as old as 3 billion years, 3.5 billion years. For example, the evidence of the Pilbara Craton in Australia, almost around 3.2 to 3.5 billion years old. But oceanic crust is no older than 200 million years. That means the oceanic crust has been created recently. Continental crust was created much earlier. Oceanic crust earlier would be considered flat, but Harry has found out that oceanic floor also has got mountains, plateaus, etc. How they are created. So, like that, he even found a zone of active volcanism in the region of the ridges, mid oceanic ridges. And that is where he found out that closer to the mid oceanic ridges, you would always find the presence of newer crust. And as you would move away from the mid oceanic ridges, you would find the presence of older crust. So, with the help of these observations, Harry has propounded what would be referred to as the seafloor spreading theory. Now, what is this seafloor spreading theory? It basically talks about the fact that newer crust is created at mid-oceanic ridges. Mid-oceanic ridges. Okay? That is where newer crust gets created due to volcanism, due to volcanic activities. Right? Now, once this newer crust is created, after that, what happens? It basically, then after that, the older crust is pushed aside. Crust is pushed aside. Okay? To the sides. And then at the boundary between the continent and the oceans, where you have the presence of these oceanic trenches, that is where the older crust gets consumed. But in the process, the sea expands, the ocean floor expands. So, ocean floor expands in the process. Okay? And as the ocean floor expands in the process, near the oceanic trenches, the sea floor is consumed. And then recycled by convection currents as newer crust. Newer crust. So that was basically the entire postulation of the seafloor spreading theory. It was based on the observations, and here you observe in this particular map the case of the age of the seafloor. The red color will indicate that it has been created recently, and the green, pink, purple color indicates that it has been created long time back. So if you observe the entire region of mid-Atlantic ridge, that is recent phenomena. Here you have active volcanism. Now, even here at the margins of the Atlantic, you will find that the seafloor is older, roughly around 160 to 180 million years old, which tells you that this particular entire Atlantic Ocean has been created around 160, 180 million years old. Okay, now then here you observe basically the case of this region in Pacific. Here you have the region of the Pacific Ocean, that is the Pacific plate. We will talk about plate dynamics shortly. And here you have the region of Nazca plate. This is the area where the expansion is amongst the fastest across the entirety of planet Earth. You have newer crust which gets created, and the seafloor is expanding at a rate of close to around 15 millimeter per year. So that is where it is actually expanding. And in these areas, it is getting consumed. The oceanic trenches, that is where it is getting consumed. Observe this one. That is the region of Aegean Sea. Aegean Sea, which is the eastward margin of the Mediterranean, that is one of the oldest oceanic floors that are in existence. Now, even that is going to be consumed due to the northward movement of Africa. But here, basically, it is close to around 260 to 280 million years old. And that is considered to be one of those remnants of the Tethys and even the ocean prior to that. So, this is where you have one of the oldest seafloors which are present or are prominent. Okay. Then coming to the case of plate tectonic theory. It is after this that we will be taking the PYQs. So, plate tectonic theory. So, all these factors that have been talked about, that is the continental drift theory, the convection current theory, the seafloor spreading theory, all of them indicated towards a similar outcome. That is, the land, the continents around us, they are moving, they are adjusting continuously. Okay. Now, how they are moving, why they are moving, where they are moving, that was not exactly bounded in one theory. That is something that plate tectonic theory did. Plate tectonic theory was provided by whom? There were multiple proponents of plate tectonic theory. You had various different people, like you had Tuzo Wilson, the one who is credited with the idea or the word tectonic. Tectonic is derived from the term tectonique with a K, indicating the act of building. So that is where Tuzo Wilson was one of the pioneers. Then you had Mackenzie, Parker, all of them were actually associated with this postulation of plate tectonic theory. What is this plate tectonic theory? Now, it talks about the fact that the lithosphere, what do we mean by lithosphere, by the way? That is your region of crust plus upper solid mantle. Solid mantle. That is the region of lithosphere. So, lithosphere is actually broken and subdivided into various different plates or various different parts. Okay. And then these tend to move over the region of asthenosphere and eventually create different landforms. So, across the globe, you have the plate boundaries. Now, based upon the size, they are classified into major and minor plates. So, which are the major plates? There are 7 major plates that can be relevant for your examination. So amongst the major plates, you'll find the North American, South American, right? South American. Then you have Eurasian, African, then Pacific, and then you have Indo-Australian. Australian. Okay, so these are your overall major plates which are in existence. All the major plates, barring Pacific, all of them have both continental as well as oceanic crust. It is only the Pacific, which is the major plate, which has got only oceanic crust which is present. Only major plate with oceanic crust, right? Major plate with oceanic crust. Right. So rest all of them will have both continental and oceanic crust. Now, how do we get to know what are the plate boundaries or where are the plate boundaries actually situated? That is something which is understood with the help of study of seismicity, earthquakes and volcanoes. Wherever you have frequent occurrences of earthquakes, that means the crust is weaker in those areas, and that is where you have the plate boundaries. Now, some of the minor plates are also important. For example, Nazca plate, right? Then you have the Cocos plate, Caribbean plate, Arabian plate, right? Yuan de Fuca plate, Filipino plate. These are some of the other minor plates that you can keep in mind. There are not 8 minor plates. There are endless number of minor plates. For example, the Burmese plate is a minor plate. The Amur plate is a minor plate. The case of Okhotsk plate is a minor plate. Then you have Anatolian plate, that is also a minor plate. So, like that, you have large number of minor plates out there. Okay, the Seafloor or Caroline Sea plate, that is also a minor plate. Scotia plate is a minor plate. So there are many, many minor plates out there. But largely in all the maps, in a broader map, all of them cannot be indicated. So that is why you are able to see only this kind of small portions of the minor plate. Okay, so these are the cases of the various different major plates. Major plates are important for your prelims examination. Some minor plates, if you have the idea where Nazca is situated, Nazca continues to remain in news. The reason being that Pacific and Nazca, they are expanding or moving away at a fastest rate as compared to anywhere in the world, right? And it is where the Andes also, they are an active geophysical feature. Recently, because of series of earthquakes which have occurred in the region of northwestern Pacific Ocean, that is around the Sea of Okhotsk, you have the Amur plate and the Okhotsk plate, which have also come in greater amount of news, right? So these areas which are in news, that is something you should take a look into. Okay. Now, why is it that the plates move? The plates are moving because of the convection current which is prevalent. The convection current which is in existence in the interior, heat from the interior is provided, is rising up, and that is why the plates tend to move. The plates can move towards each other or away from each other. Okhotsk plate and Amur plate, they are situated in the region of the Kamchatka Peninsula, that is in this area, in this region. Okay, it is in that area where you have the Okhotsk plate, you have the Okhotsk Sea, which is there, right? So that is where you have the Okhotsk plate also. Now the plates tend to move because of the convection current which is present in the interior, and that convection current, the horizontal component of the convection current, that tends to push or move the plates away from each other. So here you basically will observe a convection current in the region of the mantle, and that is where the plates they tend to move. Okay, so here that is where you have the mid-oceanic ridges as well. Okay, so first of all, what tends to this is something which has been in relevance because of the breakage of African continent as well. It is the convection current which is emerging in the region of Africa, due to which you have the breakage of Africa which is happening. So this convection current can happen underneath the oceans as well as underneath the continents. Okay, so when they happen underneath the oceans, volcanic eruption through the mid-oceanic ridges, seafloor spreading, leading to the formation of newer crust. But what if it happens underneath a continent like Africa? In that case, first of all, the heat from the interior will thin out the lithosphere in this region. Lithosphere will get thinned out. Just like how you heat a plastic scale, right? For example, the simple example for this or analogy for this can be considered to be a candle. And let's suppose you have a plastic scale here. Okay. Now, what will happen? Will the plastic melt immediately? No. It will get heated up, it will thin out, and then if you stretch it, it will be stretched as well. It will thin out further and further. Just like that, heat from the interior thins out the crust to such an extent that it forms a depression. Water from the surrounding can also easily come by. So for example, if you observe this, various different stages are explained. So in this, for example, when the convection current starts producing that upward heat, you observe that the land mass it starts to swell and the cracks they begin to develop. Example, the case of Colorado Plateau, right? You basically have the landmass which starts to crack, and you have the landmass which starts to get uplifted. Now, further, if the heat continues, that from those cracks there is subsidence which happens, and you have the formation of rift valley structures which are created. Example, the African rift valley that you find, Rio Grande rift valley as well. Where is river Rio Grande? Let me know. Those of you who have done the mapping sessions would be aware of that. Rio Grande is a transboundary river, right? Between which two countries? It is between US and Mexico. Okay, so that is something that we have discussed in the previous class. Now we are doing South America in the mapping sessions. In the previous session of North America, I hope you recall, we have discussed about River Rio Grande and River Colorado as well. So River Rio Grande, that also drains through the region of Rift Valley. So that is where you have the Rift Valley in Africa also, and in Rio Grande as well. Eventually, as the convection current will continue, there will be thinning of the crust, and you will have a shallow sea which gets created. Example, the Red Sea. Okay, Red Sea is the example of this. So Red Sea initially was not present, and you had the Arabian Peninsula, that is the region of Saudi Arabia, all of this. Now that was something which was attached to Africa, but then that split apart and Red Sea was created. So that is the continuation. Further, it will continue. A large ocean gets created with a mid-oceanic ridge. Example, the Atlantic Ocean. Okay. Now, all these plates, they have different types of movement, and based upon each of the type of movements, different landforms are created. So plates can move towards each other, known as the convergent plates. Plates can move away from each other, divergent plates, or the plates can move parallel to each other, known as transform plates. So when the plates they move towards each other, in that case there is some subduction, or one part of the plate gets destroyed. So that is why this is also known as destructive plate margin. destructive plate margin. Okay. When the plates, they move towards each other, that is destructive plate margin. When the plates move away from each other, that is when you have the creation and the formation of newer crust. And that is the case of constructive. Newer crust gets created. So constructive plate margin. Okay. Plate margin. Then after that, you basically have the case where the plates are moving parallel to each other, right? So parallel to each other means they are neither moving towards each other, neither a portion of the crust is destroyed, nor are they moving away, so no new crust is created. They are parallel to each other, so neither a creation of newer crust nor the destruction of the older crust. These are your conservative plate margins. Conservative plate margins. Okay. So that is basically your three types of plate margins that you come across. Okay. Now here we will take a look at the examples and each of them when we talk about what are convergent plates, what are divergent plates, and what are transform plates. Starting with the case of the convergent plates. Convergents, they basically move towards each other, one portion gets subducted. Always remember the heavier crust undergoes subduction or goes underneath due to the force of gravity in general, right? So undergoes subduction. Now, when we say heavier crust undergoes subduction, we have seen that as compared to oceanic and continental, you will observe that it is the oceanic crust which is heavier. So always in this case, oceanic crust undergoes subduction, right? Subduction. Now let's take a look at the examples of each one of these type of convergences. Now you have oceanic crust and continental crust, right? So three types of convergences can exist: oceanic continental, oceanic oceanic, and continental continental. These are the three types of convergences which can exist. So let's take a look at each one of them. Oceanic plate with a continental plate. Here you can have multiple examples. North American plate with Pacific plate, right? Or you can take the example of the Nazca plate and the South American plate. All these are examples where the oceanic and the continental plates are undergoing convergence. Let's take the example of Nazca plate and South American plate. And South American plate, right? Now, what are those? So, when we say an ocean plate, now oceanic plate is thin, high density, and continental plate is thick, low density. But when they will converge, the convergence won't be uniform, isn't it? Oceanic plate, because of the high density, will start to experience the sink. Whereas the continental crust, you will observe that will get deformed and you will have accumulation here. Okay, so you will observe here, let's suppose we draw the ocean, right? So here you will observe formation of oceanic trench, oceanic trenches. Example, the Peru-Chile Trench, which is on the western coast of South America. That is where you have the Peru-Chile Trench. Okay. Then here you have the formation of fold mountains. Example, Andes. Okay. Now, as the plate actually starts moving down, it experiences higher temperature, due to which there is partial melting. And the molten materials then they start rising up. Molten materials they start rising up and they create volcanic eruption. Right? So you have volcanoes in this case. Whenever there is an oceanic convergence, whenever there is an oceanic convergence, there will be a volcanic eruption which is associated. So, example, in South America, you have around in Ecuador, Mount Cotopaxi. Okay, Mount Cotopaxi in the region of South America. So that is basically the case of this oceanic continental convergence. These are seismic zones and volcanic areas. Then oceanic plate, in this case, which will undergo subduction. So always older oceanic plate is heavier. Oceanic plate is heavier and undergoes subduction. Okay. It is heavier and it undergoes subduction. The older oceanic plate. For example, you consider the Philippine Sea Plate and the Pacific Plate, the Caroline Sea Plate and the Pacific Plate. All these are examples. Pacific Plate is the older one that will undergo subduction. So, in this case, what actually tends to happen is you have one oceanic plate, another oceanic plate. The heavier one will undergo the subduction, the newer one will get deformed. But here you don't have the formation of a fold mountain. But in continental crust, you had fold mountain. Why? Because in this particular case, the oceanic crust is thin and highly dense. So it cannot get folded or accumulated here. So let's suppose this is the ocean. Now the materials will start melting. It will rise up, create underwater volcanoes. It can also create volcanic islands. Volcanic islands. Example, the region of Indonesia has been created like this. Indonesia. Here, it creates underwater mountains known as seamounts. It creates trenches. Example, Mariana Trench. That is created between the Philippine Sea Plate and the Pacific Plate. Mariana Trench. Okay. Then you have the case of continental convergence. Here, is the subduction completely absent? The answer is no. Subduction is not completely absent. Some amount of subduction does happen. Why are the oceanic plates heavier? Because of the nature of materials that they are made out of. Oceanic plates are made out of basaltic rocks, rich in iron and magnesium. That is why they are heavier as compared to continental crust. Now, in this, subduction does happen, but in very little amount. Small amount of subduction occurs, right? And that too of the heavier plate. For example, when we consider Indian plate and Eurasian plate, Indian plate is the one which undergoes slight amount of subduction. So let's suppose you have one plate that is the Indian plate, another plate that is the Eurasian plate. Both of them are light. But when they will undergo convergence or collision, fold mountain will be created like the Himalayas, Alps, they are also Ural. All these are fold mountains. Appalachians, these are example of fold mountains. And some portion, very little portion will undergo subduction. But overall, you have crustal thickening and metamorphosis. No volcanic eruption occurs in this. Only in oceanic convergence you have volcanic eruption. Why no volcanic eruption? Two reasons. First of all, crust is so thick, molten materials cannot come up. Second reason, very little amount of subduction does happen, not enough to produce high pressure to break through the surface. Okay. Now, in the case of divergent plate boundaries, the convection current pushes the plates away from each other. So, for example, North American plate is being pushed away from Eurasian plate. South American plate is being pushed away from African plate. Within Africa itself, you have the breakage which is happening. So, all that is divergent. It creates new crust. It always creates new crust, right? Newer crust through volcanic eruption. Volcanic eruptions. That is why it is known as a constructive plate margin, right? So, for example, observe the divergence in the region of the Arabian Peninsula. So, Arabian plate you observe. So, that is where the divergence is happening, creating the region of Red Sea. And presently, it is extending into Africa as well. So, presently, that divergence is extending here as well. And Africa is breaking. Okay, so Africa, as it is breaking, it is going to break into two plates, that is the Somali plate and the Nubian plate. It is breaking in the region of Ethiopia and Djibouti, Eritrea. That is where you have the Afar Triangle or also the Danakil Depression, which we have discussed under places in news. So that is something which we are experiencing across almost all the mid-oceanic ridges. Okay, that is divergence, right? Now, then this is your divergence, okay, across the entirety of the mid-Atlantic ridge. That is where divergence is happening. Okay, now then you have a kind of plate movement where the plates are moving parallel to each other. They are not moving towards each other or away from each other. They are moving parallel to each other. And that is known as the transform plate boundary. Now, transform plates, when you consider, they neither create a new crust nor they destroy an existing crust. What they can do, as they are trying to rub against each other, they create these cracks. They create these very large cracks. And as they create these cracks, these become centers of earthquakes and seismic activities. Continental divergence can happen anywhere. Wherever divergence will occur, eventually it can lead to formation of oceans. That is the entire cycle that I indicated. That convection current, when it is initiated, you can have the rise of the region like Colorado Plateau, then creation of Rift Valley like the African Rift Valley, then further a narrow sea like the Red Sea, and eventually it can create a large ocean like the Atlantic Ocean as well. Now, here, this can create large cracks or faults, which are known as transform faults. Now, observe one thing, guys. Example, San Andreas Fault in California. San Andreas Fault in California, which is the heart of seismic activities in this region. Now, observe one thing, guys. When we are considering the mid-oceanic ridges, I want you to observe this image very carefully, first of all. This is the region where the entire Atlantic Ocean is splitting, isn't it? Region of North America is moving away from Europe. South America is moving away from Africa. But this divergence which is happening, the rate of divergence, let's suppose in this area, And the rate of divergence in this area, can they be similar? No. These are places with a distance between them being tens of thousands of kilometers. So you cannot expect the same kind of divergence or the same speed of movement at all. So that is why when here also North American plate is moving and Eurasian plate is moving, and here South American and African plate is moving, they cannot move at the same speed. So Eurasian and African plate, despite moving in the similar directions, will have different speeds. So that means what? Can I say some portion of Eurasian plate and some portion of African plate here, they are moving in the same direction but at different speed. That leads to development of these parallel fault lines or transform faults. So mostly you will observe that transform faults are perpendicular to the divergent line. Observe here also. Here also you will observe that this is the case of the divergent line, right? Here also divergence is happening. Here also divergence is happening. Now, if I name this as 1, if I name this as 2, 1 and 2 are moving parallel to each other, but there is a fault line here. Okay, so that basically is a relevant statement for a multiple choice question, that transform faults lie perpendicular to zones of divergence. Okay, keep that in mind. This is a multiple statement question. So these are the major plates associated. This is something you should overall retain. Now there are some MCQs and PYQs that we will be discussing, but after we take a break, and we'll take a break right now. After around 20 minutes, we will get back and we will continue. So take a break for 20 minutes. Okay. And then we will be discussing the PYQ and the rest of geomorphology after that. Okay. Let's take a break. Okay, welcome back everyone. So, till now we have discussed about the interior of planet Earth. We have discussed about the various different theories associated with the origin and the formation of the continents and the oceans. And we have also discussed about the different types of rocks. Okay, so all these areas we have managed to discuss. So now, before we move ahead into seismicity, earthquakes, volcanoes, and even the case of landforms and weathering, let's take a look at some of the questions and the PYQs also. So let's take a look at this particular question. You have the discontinuity and you have to match them with where they are present. Now, do let me know what is the correct answer in this. Conrad discontinuity between the upper and the lower crust, Mohorovičić between the outer core and the inner core, Repeti between the upper mantle and the lower mantle, Gutenberg between the crust and the mantle. Which of the following is or are correctly matched? Let me know what is the correct answer for this. So in this, Conrad discontinuity, that is between the upper and the lower crust, that is correctly matched, right? Mohorovičić discontinuity is present between the crust and the mantle, not between the outer core and the inner core. So this has to be incorrectly matched, right? Repeti discontinuity between the upper mantle and the lower mantle. This is again correctly matched. Whereas Gutenberg discontinuity between the outer core and the inner core. So this is again incorrectly matched. So here the correct answer is going to be A, that is 1 and 3 only. Then, which of the following phenomena might have influenced the evolution of organisms? That is, how have the organisms evolved? So, when we talk about evolution of organisms, they are impacted by the climate change, the change in geography, and so on. So, in this, continental drift as well as the glacial cycles, that is, the ice ages, both of them are actually responsible for influencing the evolution of organisms. So, in this, correct, most of you are correct in this. The correct answer is going to be C, that is, both 1 and 2. Then, here, this is a generic question and a question that should not be very difficult. Which of the following pairs is or are correctly matched? You have the theory and the law. This is a PYQ. So, and the scientist associated who has given that. So, continental drift, expansion of universe, and photoelectric effect. So, continental drift given by Alfred Wagner. So, one is incorrectly matched. Obviously, 2 is also incorrectly matched. Alfred Wagner provided the continental drift theory. Expansion of universe was actually provided by Edwin Hubble, right? And this was then later on worked upon by Lemaitre and Gamow, and that is when you had the formulation of the Big Bang theory. Then photoelectric effect provided by Albert Einstein. Even if you did not know about photoelectric effect, if you know that only if you knew about continental drift theory, that automatically meant 1 and 2 were incorrect. So only one option satisfies this, and that is option B, that is 3 only. Then a simple question, a PYQ again. In the structure of planet Earth, below the mantle, core is mainly made up of which one of the following? So, core is dominated by which element? Core is dominated by iron and nickel. So, here the correct answer is going to be C, that is iron. Then, this was a question which was asked last year. Which of the following are the evidences of the phenomena of continental drift? The belt of ancient rocks from Brazil coast matches those from Western Africa. The gold deposits of Ghana are derived from the Brazil plateau when the two continents lay side by side. The Gondwana system of sediments from India is known to have its counterparts in 6 different land masses of the southern hemisphere. So, which is correct in this? So, in this, all 3 statements are actually correct. Belt of ancient rocks from Brazil coast matches those from the Western Africa. So the first statement is correct. The gold deposits of Ghana are derived from the Brazil plateau when the two continents they lay side by side. That is also correct. This is what we discussed under placer deposits. That is the example of placer deposit. And the Gondwana system of sediments from India is known to have its counterpart in six different land masses from the southern hemisphere. That is the entire region of Gondwana land. So in this, 1, 2, and 3, all of them. So this was a question, a direct question which was asked last year. Now, all those of you who are appearing for the exams this year, or all those who are actually preparing for the exams next year, what to extract when you are taking a look at PYQ? So when you are taking a look at the PYQ, obviously you need to get those concepts correct, first of all. Secondly, look at the area where UPSC has focused. UPSC has asked you a question from continental drift theory after a long period of time. That means questions associated with seafloor spreading, questions associated with the paleontological evidences, they automatically become a high frequency or a high yielding area in the coming year as well. Because as I told you, from 2022 onwards, there has been a concerted move by UPSC to ask you questions associated with this portion of geomorphology. That is from the portion of rocks, rock cycles, etc. So that is where it becomes very, very important. Okay. Now, see and observe the trend. In 2022-23, you had a direct question in the mains about the uh, primary rocks, that is igneous rocks, and the types of igneous rocks that you have. Then next year, you had a question associated with the P and S waves, which was asked in the prelims examination. That means geomorphology was in focus. Next year, you had a question associated with the permeability, porosity, and even the content. So, UPSC, which had ignored geomorphology for a long period of time, has been refocusing on geomorphology and climatology. That is something that you extract when you analyze the previous year question. Okay. Now, this is a statement based question. In the context of effect of water on rocks, chalk is known as a very permeable rock, whereas clay is known as quite an impermeable or least permeable rock. Now, statement 2. Chalk is porous and hence can absorb water. Statement 3. Clay is not at all porous. Okay. Which one of the following is correct in respect to the above statements? Both statement 2 and 3 are correct, and both of them explain statement 1. Both statement 2 and 3 are correct, but only one of them explains statement 1. Only one of the statements 2 and 3 is correct, and that explains statement 1. Neither statement 2 nor statement 3 is correct. Now, take a look at this. Okay. Do let me know what is the correct answer in this. Very good. It is not A here. Many of you are writing that A is the answer. A is not the answer here. So let us analyze each of these statements. In the context of the effect of water on rocks, chalk is very permeable. It allows the water to pass through. So that is permeable. So chalk is permeable. Clay is porous but impermeable, right? So clay is known as quite an impermeable. It does not allow the water to pass through. So statement 2, chalk is porous and hence can absorb water. This is correct. Okay, statement 2 is correct. Statement 3, chalk is not at all porous. This is incorrect. Clay is not at all porous. Clay is actually porous but impermeable. Okay, this is porous but impermeable. Okay, So that is associated with statement 3. So here, basically, the correct answer is only one of the statements 2 and 3 is correct, and that explains statement 1. Okay, so that is the case of the answer here. Clay is impermeable but porous. Chalk, both porous as well as permeable. Okay, many of them have committed mistake in this question as well. Now we come to the area of earthquakes and volcanoes. This is also a region where the probability of questions being asked in the prelims is very, very high. So, here, what is it that is required for us to understand? What are earthquakes and why this is important this year? Because if you are following current affairs, India has come out with the new zonation, earthquake zonation map. Okay, you have various different zones which have been demarcated, that is from zone 2 to zone 5, based upon the probability of seismicity happening in that area. So that is something where the seismic activities are again in news. So UPSC is not going to ask you in the prelims to draw that zonation obviously. It can ask you certain questions like what what is the zonation from zone 3 to zone 4, zone 1 to zone 5, and so on and so forth. So it can ask you a question associated like that, or it can ask you a basic question. Let's suppose a difference between magnitude and intensity of an earthquake. That kind of a question can also be asked. The difference between love wave and a Rayleigh wave. Okay, so those kind of questions can also be asked. Okay, now, first of all, when we talk about an earthquake, what is an earthquake? The massive release of energy in the interior of planet Earth, which leads to the shaking of the ground surface, that is known as an earthquake. Okay? Wherever you have massive release of energy because of any factor, be it a volcanic eruption, be it plate movement, any of those activities, if they lead to massive release of energy, which can end up shaking the Earth's surface, that is an earthquake. Okay. Now, whenever an earthquake or seismicity does occur, let's suppose there is a plate movement. Okay. Let's suppose there is a kind of a plate movement. And here, there is seismicity which is occurring here. So, or seismicity, let's assume, is occurring here in this region. Now, the region where the seismicity has originated, that is known as focus of the earthquake. Okay? But obviously, it is in the interior of planet Earth. It can have a varying depth. Maybe seismicity has occurred 60 kilometers below the surface, 100 kilometers below the surface, 200 kilometers below the surface. So, it can have a varying depth. Now, how do you demarcate it for a common population and common person like you and me? How do we understand where earthquake has occurred? So, for better mapping and for better depiction, you have the line or the point which is directly above the focus, that is known as epicenter of the earthquake. Okay, that is known as epicenter of the earthquake. Now, I know that many of you oftentimes get confused between intensity and magnitude. So, kindly pay attention for the next 3 to 4 minutes and you will never get confused. I will show you the entire Mercalli scale as well. Okay, so please pay attention for the next 4 to 5 minutes here. Now, when we consider the focus, focus, as I told you, can lie anywhere. Now, based upon the focus of the earthquake, you have the classification of the earthquake into three types. Okay, you have the three types based on the classification. So, you have the shallow focus earthquakes, where the focus lies up till a depth of, let's suppose, 60 to 80 kilometer. Epicenter will always be directly perpendicular above the focus. Epicenter will be directly above the focus. So shallow focus from the surface to, let's suppose, around 80 kilometers, 60 to 80 kilometers depth. That is shallow focus. Here, the impact will be very high. The damage caused will also be very, very high. Then you have intermediate focus earthquakes. Intermediate focus earthquakes. Now, this intermediate focus that can extend from around 100 kilometers, or let's assume 80 kilometers itself, to roughly around 300 kilometers depth. That is intermediate focus earthquake. And then you have the case of deep focus earthquake. That is basically 300 kilometer to 700 kilometer depth. Beyond 700 kilometer, you don't have the presence of the focus. Why? Because beyond 700 kilometer, you will never experience seismicity. Why? Because as you go to a depth beyond 700 kilometers, you are in almost the central portion of the mantle. Very good. So at that point of time, temperature is so high, pressure is so high, that rather than breaking, the materials will get deformed. They will not break. Materials will easily get deformed rather than breakage. So that is why, in the case of or beyond this depth, no focus or no seismicity beyond this. Seismicity beyond this. Okay? I hope that is clear. Now, think about it. And let's be patient, let's understand this. When we consider an earthquake with a focus of 10 kilometers, let's consider two different places. Focus at 10-kilometer depth, and this is a place A, and the focus at, let's suppose, 100-kilometer depth. This is the place B. Let's assume same amount of energy is released. Now, which will receive or experience more amount of damage, A or B? Always A will experience more damage, isn't it? Because the focus is closer to the surface. So A will always experience more destruction, more devastation, whereas B will not experience so much so. Also understand one thing. When we consider, let's suppose, the type of buildings in different places, let's assume that you have the region of A and B. Now in A, you have two buildings like this. And in B, you have lot of small buildings, interconnected houses, slums, everything. If an earthquake occurs, where will be a greater destruction? At B, more population is living there, isn't it? So, based upon the nature of the rocks, the depth of the focus, the type of houses that you have, population density that you have, the damage which will occur will be different. Now, when we did not have enough scientific power or enough scientific prowess to detect the energy released by an earthquake, earthquakes would be monitored based upon the damage caused on the surface. For example, if let's suppose even today you get to meet someone very old uh, in your vicinity or in your region, great grandparents or grandparents who are old, you ask them about a particular earthquake, maybe in Himachal Pradesh or in Bihar, they will always tell you based upon the damage, that no buildings were surviving, everything was destroyed, and so on. So, earthquakes would be distinguished from each other based upon how much damage it has caused. For example, we know that Nepal is frequented with earthquakes. One of the earliest records of the earthquakes, the written records of earthquakes in Nepal, they date back to the 13th century. And what does it describe? It tells us that the earthquake which occurred at that point of time wiped out one third of the Nepalese kingdom in the 13th century. So, again, how are we classifying or how are we describing the earthquake? We are describing the earthquake based upon the damage causing potential, how much damage was created. So, when you classify the earthquakes based upon the damage which is created, that is what is referred to as the intensity of an earthquake. That is based on damage causing potential, based upon damage caused. That is known as the intensity of an earthquake, right? It is measured based upon a scale that is known as Mercalli scale. Now, what is this Mercalli scale about? So, Mercalli scale, if I can show you, this is your Mercalli scale. It is what is known as the modified Mercalli scale, or that is MMS. So, here, look at it, what it indicates. Level 1, earthquake was not felt by uh, anyone except a very few. Very few people experienced that shaking, rest of them did not experience. So, it is the level 1 earthquake as per Mercalli scale. Level 2, felt only by a few persons who were at rest, especially on upper floors of the buildings, otherwise, they did not feel it. Let's suppose level 6, felt by all, many frightened and run indoors. Some heavy furniture also experience a movement. Few instances of damaged chimneys, fallen plaster, and so on. So, this is on the basis of the damage caused, you are classifying the earthquake. That is your Mercalli scale. Okay. So, that is the case of your intensity. But then we have just now discussed that damage can be different based upon the depth of the focus, based upon the case of the nature of the rocks, based upon the population density, the kind of housing which you have. For example, in Latur in Maharashtra, you had an earthquake in around 1992. Now, it was not of a very high energy earthquake, but because the population density was so clustered, loss of life was estimated to be close to around 5,000. So that means damage caused was much higher. You have 4 to 5 earthquakes which keep on occurring in Japan, but the damage caused is not so high. So, damage caused can be dependent on many things. So, if you actually have to measure the energy or classify the earthquake, measure the energy which is released. And when you measure the energy released during an earthquake, that is where you measure the magnitude. Magnitude measures the energy released during an earthquake. Released during an earthquake. Okay? That is your magnitude. Now, how is it measured? It is measured with a device, first of all, that is known as the seismograph, right? It is measured with a seismograph. Seismograph, and then matched up with the Richter scale. Now, seismograph is like an ECG machine. Okay, so here basically what happens is that you have a roll of paper which keeps on coming out of the machine, and the pen or the ink basically measures any vibrations which occur. So typically, when you consider a paper roll which comes out of a seismograph, it will have a marking somewhat like this. Whenever there are spikes, that means there is some seismicity which has occurred. Okay, so the shaking which has occurred, so clearly you can see this is the main seismic activity. Seismic activity. Okay, this is what is the shaking which has happened prior to the main seismic activity. This is what is known as foreshock. This is your foreshock. And this has happened after the seismic cycle. Adjustment of the rocks happen in this. This is what is your aftershock. For example, the Nepal earthquake of 2015 experienced aftershocks continuing up till almost a month after the earthquake also. So that is where you have these foreshocks and aftershocks. By the way, while we are discussing about the foreshocks and aftershocks, there is another phenomena which is experienced, and that is where the seismograph will give a reading somewhat like this. You don't have a distinct earthquake, but a series of shaking activities which happen. Very frequently, earthquakes they keep on occurring. These are known as earthquake swarms. Earthquake swarms. Where you have very high frequency of seismicity which occurs, very, very high frequency, generally is observed in areas where a volcanic eruption is about to happen, or in areas where a lot of water seepage has happened in the underlying rock systems. For example, you can consider the region of Iceland. Iceland last year experienced around 800 seismic activities within a month. No foreshock, no aftershock, but continued minor shaking. That was an earthquake swarm. And that was an indicator that you have a major seismic or a major volcanic eruption which is about to happen. That is what is known as an earthquake swarm. So, when we talk about the difference between the Mercalli scale and the Richter scale, so Mercalli scale represents the intensity and Richter scale represents the magnitude of an earthquake. The range of intensity, it is basically the modified Mercalli scale 1 to 12 and magnitude 1 to 10. Now, what does the magnitude actually measure? Magnitude measures the energy waves which are released, right? So, magnitude measures the energy waves which are released. Let's suppose the energy waves are released like this. Okay. So that is where the magnitude will actually measure this amount. That is amplitude of the energy released. This is a question that has been asked this year in a couple of candidates that we have been mentoring for interview. They have faced this question in the interview. Okay. So that becomes important. Amplitude of energy waves released. During an earthquake. Okay. And that is indicated by, that is what is measured as magnitude. Now, Richter scale in itself is logarithmic in nature. Okay. Logarithmic in nature. Means what? That when you have an earthquake of magnitude 6, right, and an earthquake of magnitude 5, so this is 10 times more powerful. More powerful. So that is what is indicated by logarithmic nature of it. It is 10 times more powerful. 10 times more amount of energy is released during this process. Okay. Now, Then when we consider the seismic waves, so seismic waves broadly are classified into two types. You have the body waves which travel through the interior of planet Earth, and then you have also got the surface waves, body waves and surface waves, right? Now, when we talk about body waves, they travel through the interior of planet Earth. So, where do they originate from? Origin is basically the region of focus. They originate from focus. And surface waves, where is their origin from? Their origin is from the region of epicenter. Okay. So that is the difference in the terms of origin of it. Okay. So body waves, they are of many types: P, S, P star S, PG, SG, and so on. But we will only consider P and S waves. Surface waves, they cause maximum amount of damage, right? And they are basically love wave and Rayleigh waves. Rayleigh waves. So that is the kind of classification that you have in between the surface waves and the case of body waves, right? Now, when we consider each of them, right? For example, when we consider, let's suppose P wave is a primary wave, right? So let's consider the case of P wave. So whenever you consider a P wave, now this is something which moves very fast. Immediately after earthquake, the P wave actually moves very, very fast. So whenever we talk about, let's suppose the P waves, so here what happens is, let's suppose this is the region of the focus and these are the particles which are present in the interior. So there's a kind of a movement where each of the particles, they vibrate in their own position, disturbing the next particle as well. And this is your direction of the wave motion. Direction of wave motion. And this is your direction of particle movement. Particle movement. Okay. Now, because let's consider this to be D1, let's consider this to be D2. Now, because direction of wave motion and direction of particle motion is the same, that means this wave will be able to travel very fast. So, travels the fastest. Reaches the surface fast. Why? Because D1, direction of particle motion, is same as the direction of the wave motion. Okay, that is why. And even if, let us assume that the particles were slightly far away from each other, like a liquid medium or a gaseous medium, there also, if the first particle is disturbed, it will disturb invariably the second particle also. It will disturb invariably the third particle also. It will disturb the fourth particle, because the direction of particle motion and the direction of wave motion is the same. That is why it can travel in solid and liquid as well, in all mediums. Because because D1 is same as D2. That is why. Okay? Because D1 is the same as D2 in this case. Then when you consider the S waves. Now S waves, there the movement of the particles is slightly different. There you will find that the particles, if they are situated like this, the wave motion, direction of the wave motion is this, of wave motion. Okay. Now each of the particles, they get disturbed like this. Each of the particles, they get disturbed in their own position. So they form a kind of a sinusoidal wave. So they will create a wave system somewhat like this. Okay. So here, obviously, the movement will be slower because when we consider the direction of particle movement, this was also a direct question asked in 2023 prelims. Direction of particle movement. Let's assume it to be D1 and this is your D2. So travels slowly because D1 is perpendicular to D2. Okay, that is why it travels slowly. And it is the same reason why it won't be able to travel through liquid and gaseous medium, can only travel through solids, only move through solids. Okay, solids. So that is the feature associated with the P and the S waves. So P waves are the first waves to hit the Earth's surface and S waves hit later on. It is when both of them hit, that is when the surface waves they get generated at the region of the epicenter. And it is this feature of P waves hitting first that is where you have the earthquake early warning systems which are generated. So, for example, in Japan, you have the earthquake early warning systems in existence. Now, that gets triggered as soon as the P waves hit the surface, it gets triggered and it then moves. So, S waves, they arrive after the P waves. Now, they travel at a speed of around 4.5 to 13 kilometer per second, whereas in S waves, the speeds are 1.7 times slower. Now, here, when you consider the P waves, they travel in a linear manner through compaction, expansion, and so on. S waves, they travel in a transversal direction. Okay, so that is the basic difference. When we consider surface waves, now they move only on the surface and they are responsible for maximum damage which is caused during an earthquake. Maximum damage. Now they are basically, depending upon how the surface tends to move, they are classified into love wave and Rayleigh wave. Okay, so what you need to know for your prelims is P waves is the fastest, followed by S wave, followed by love wave, and then followed by the Rayleigh waves. So that is basically the criteria for the classification of this surface waves as well. Surface waves in overall motion slower in speed as compared to the body waves. But then even within them, love wave is faster than the Rayleigh wave. What is the other difference? When we consider love wave, you have horizontal movement of the ground. Horizontal movement of the ground. Right? And when you consider the kind of Rayleigh wave, in that you have the vertical sinusoidal movement which is experienced on the ground. Vertical movement on the ground. Okay. So that is the basic difference. So you have two differences. Love wave, horizontal, Rayleigh wave, sinusoidal. Which is more destructive out of these two? Rayleigh waves, they are known to cause greater amount of damage because of the sinusoid that they create, right? The kind of wave motion that they generate. Many buildings, they are able to, for example, if you consider the building, if there is horizontal movement, the building can tolerate it. But if there is a kind of a vertical movement, no building can withstand it. That is why Rayleigh waves, if they are very massive, they can cause large amount of damage. So which is faster? Love wave is faster. Always remember that. Okay. Then we come to the concept of shadow zone. Now, what is a shadow zone and on what principle is it based upon? So basically, whenever an earthquake occurs, the body waves, they travel throughout the interior of planet Earth. And with the help of seismographs which are installed across the planet Earth, they can be detected in various parts of planet Earth. Okay. Now, due to the motion of these body waves, the scenario emerges where in certain areas they cannot be detected. The body waves cannot be detected. So those areas are known as shadow zones. So when we talk about shadow zones, those areas where always which regions with respect to the focus, position of the focus, okay, those areas where the body waves are not detected. Now why are they not detected? Because of a simple principle that you would have studied in your childhood days in general science also. If you consider any particular glass slab, and then you would have studied about light, that you put light or throw light on the glass slab, that ends up bending. And again, as it moves out, there is again another bending. We basically have we have studied that under refraction. Now here, what have we studied? That light as an energy, that tends to bend owing to the fact that you have change in medium, speed changes, right? So due to change in the density, due to change in density of materials, speed changes, isn't it? Speed of energy waves change. Now when the speed of energy waves change, that means what? There is a greater case of bending. Energy waves bend. Bend. Now, when we consider the interior of planet Earth, it is made out of different materials in different layers. So, obviously, there will be a change which will be experienced. So, if there is a focus which lies somewhere here, now body waves will hit the epicenter earliest. And then after that, as they move through materials of different density, they will experience bending. Okay. Now, it is because of this bending that they cannot be detected in certain areas. For example, when you consider the case of the S waves. Now, S waves cannot pass through liquid or gaseous medium. S waves can only pass through solid medium. So, when you consider the S waves, observe that they are bending. But as soon as they encounter the liquid outer core, there is no presence of S waves anymore. So in this entire zone, if you install the seismographs, you will not be able to detect the S waves at all. So that is the shadow zone of the S wave. Okay. Whereas in the case of P waves, they can move through liquids, gases, solids, all of them. So observe as they are moving through, as they are actually moving through, they will be passing through the liquid medium also. The speed increases as they move through the inner core, which is solid. However, they are not detected in these areas. Why? Because of the same bending effect and refraction effect, right? So that is why you don't have P waves detected in the zone 105 degree to 145 degree on either side as compared to the focus. Always with respect to the focus is what you will consider. Always remember that with respect to the focus. Okay. So here, when you consider these particular body waves, right? So shadow zone of S waves is larger, than the P waves, than that of P waves. And the reason being that S waves cannot travel through liquid. That is why shadow zone of S wave is much larger as compared to the shadow zone created of P waves. Okay. Then earthquakes, when they occur underwater, that is when they generate tsunamis. Giant waves in the oceans are created, and that is what generates tsunamis. Tsunamis are generated in whichever area earthquake has occurred or seismicity has occurred underwater in the Pacific, in the Indian Ocean, and so on. Okay. Now, it is basically the disturbance which is created due to the subduction or any kind of volcanic eruption which has induced seismicity, which has led to the formation or creation of tsunamis. Okay, so tsunamis generally occur where you have underwater seismicity. Underwater seismicity. That is earthquakes which occur underwater. So that is basically where you have the tsunamis. Okay. Now, if you consider these tsunamis, so let's suppose the seismicity has occurred here. Okay. It will disturb the water here because the ground is shaking. So as the ground is shaking, the water above it will also be disturbed. And that is where you have these waves which get generated. Okay. Here, the speed is very high. Speed is very high. Right. But then the wave height is not substantial. Wave height is low. Height is moderate. Whereas closer to the coastline, when it comes to the region where the depth is not substantial, that is when the height increases. Increases. Okay, and that is when large amount of damage is caused. So that is basically the case of tsunamis. Geographical distribution of earthquakes. Now kindly take a look at this map in greater detail. So this is basically a map indicating the plate boundaries and where are the regions where the seismicity occurs. You will observe that majority of the seismicity occurs in the region where you have the plate boundaries. Okay, so for example, observe here in the region associated with, or let me use another coloration here. So in the region associated with Africa, Eurasian region, that is the Mediterranean Himalayan region, there you have convergence which is happening, which is creating the seismicity. Then here you have the Indian Ocean in this region also, that is the Pacific Ring of Fire. Lot of seismicity has been continuing in these areas due to convergence. So seismicity can occur because of convergence of plates. Seismicity can occur because of event divergence of plates, and seismicity can also occur because of transform movement of the plates. Other than that, even volcanic eruption can lead to creation of seismicity. So any kind of activity, any kind of plate movement can lead to earthquakes as well. Okay. Now, this is the new earthquake zone and zonation of India. Overall, you will find that the classification of earthquake zones is from zone 2 to zone 5. That is the classification of the earthquake or the seismic zones, right? Now, here you have zone 5, that is the region of northeastern states, the region of Gujarat, and the region of Jammu Kashmir, Himachal, and some parts of Uttarakhand, along with Andaman Nicobar, right? Now, in each of these places, yes, we will cover both climatology and oceanography as well. It is not only restricted to geomorphology. We will move ahead with those areas as well. Okay. Now, basically, and don't worry, we will give breaks as well in between so that it is not very burdensome for you. Now, why each of these areas are prone to seismicity? When you consider the region of Gujarat, why is Gujarat prone to seismicity? Because it lies at a tri-junction of plates, right? So you have the Arabian plate, Arabian plate, Eurasian plate, and Indian plate. It is at the tri-junction of all of these. Indian plate. That is why, because it is at a tri-junction, that is why Gujarat is known for seismic activities. Okay? Then, when we consider the Himalayan region, there you have convergence, that is continental convergence, and compression resulting thereby. Continental convergence. Okay. Then, when you consider the region of Andaman Nicobar Island, now Andaman Nicobar Island, that experiences seismicity owing to the fact that it lies across what is known as the Indonesian Arc. Indonesian Arc is a zone of oceanic subduction. Zone of oceanic subduction. Oceanic subduction. Okay. And this is where you have the oceanic crust of the Indian plate which undergoes subduction. So this is a part of the Indonesian arc. Indonesian arc. That is why barren islands volcano are in the case of, this is zone 6 now. Yes, correct. This is your up till zone 6, correct. So when we consider the Indonesian arc, barren islands volcano is considered to be in the northernmost eruption of the Indonesian arc. Barren islands volcano is the northernmost eruption. Northernmost eruption of Indonesian arc. Okay. And there is an active subduction zone in this area. That is why you basically will find that to the west of Andaman Nicobar Islands, you have the presence of an Andaman trench as well. You have a trench-like feature as well, and that is immediately to the west of Andaman Nicobar Island groups. Okay. Then we come to the case of volcanoes, volcanic eruptions. So this is where Molten materials from the interior, they emerge and break through the surface. That is a volcanic eruption. Along with them, the eruption of molten materials, they actually lead to the expulsion of volcanic ash, debris, boulders, lapis, all of them. Okay, I will give you the classification of them as well. Along with that, you have ashes, pyroclastic materials, all of them are actually released. Now, they are classified on various parameters. Based upon the frequency of eruption, they are classified into active, dormant, and extinct. Active, if a volcano has erupted in the recent past and there is a probability of the volcano erupting again in the future, active. For example, barren islands. Barren islands is the case of active volcano. Mount Etna, right? That is also active volcano. Then when you consider Mount Pinatubo, that is also active volcano. Dormant, the eruption which has occurred long time in the past and it will erupt again, expected to erupt again in the near future. For example, some of the peaks of Mount Kilimanjaro. The eruption has happened 100,000 years ago, but there is the expectation that as Africa breaks, there can be further future eruptions as well in the region. Right? Extinct, eruption has happened long time in the past. There is no expectation of future eruptions happening in that area. So that is basically the generic classification. Now, the volcanic materials which are expelled. So some of the materials, they are slower, or in fact smaller than 2 millimeter in size. Okay, so when they are lesser than 2 millimeter in size, that is classified as volcanic ash. Those which are almost 6 to 7 centimeter in size, the small particles 6 to 7 centimeters in size, they are known as lapilli. And the ones which are larger than that, they are known as the volcanic bombs and volcanic blocks. Haile Gabbi has erupted recently, isn't it? So it cannot be put under the category of dormant. It will be active. It has emerged or erupted after a long period of time, after thousands of years. But now it will be considered to be active. Okay? It won't be. So if the eruption has happened recently, it won't be considered to be dormant. It will be considered to be active. Okay? Now, you also have the classification of volcanoes based upon the landforms that they create. So, according to the landforms that are created, they are classified into cinder cone, then composite volcanoes or stratovolcanoes, shield volcanoes, and lava domes. So, cinder cone, cinder associated with fire. That is why the term or the word cinder. And you have a conical structure, right? Hence the name cinder cone. So, cinder cone, that is a conical structure which exists. So, that is the cinder cone volcano due to eruption, right? Now, it can have basaltic lava, basaltic lava can erupt. Okay. I will provide you with a list also with the examples so that it is easier for you to revise. Now, it is there in the same PDF. PDF you can download from the Telegram channel. From my Telegram channel also you can download it, or from the Unacademy IAS English Telegram channel also you can take a look into that. Okay. Then you have the case of the composite volcanoes. Composite volcanoes, they are known as the stratovolcanoes. Stratovolcanoes. Why? Because they form layers. Form layers. They are amongst the larger of the volcanic landforms that you come across. Okay, that is the composite volcanoes. Example, you can have Mount Fuji. Mount Fuji can be an example of the same. Okay, then shield volcano. Shield volcano, basically you can have the case where basaltic lava, fluidic lava, right? So fluidic lava, which fluidic means flows very easily. So fluidic lava that is basaltic in nature, basaltic, that will tend to flow very easily. Okay, so that will tend to flow very easily. So that is where it creates a very large area of minimal relief feature, plain area. For example, Canadian Shield, right? Deccan Traps. All of this are shield volcanoes. Yes, low viscous. Okay, so that is the case of the fluidic lava. Now, when you have fluidic lava, it flows very easily. So that means what? You don't need an explosion here. So effusive, non-explosive eruption is generally associated with this. Non-explosive eruption is associated with this. Okay, example, Canadian shield, Deccan Traps, etc. Okay, so all of this are examples of shield volcano. Then lava domes, very viscous, felsic lava, not very great in height. They emerge there itself, right? Larsen Peak example is there. So here you can take a look at this, the table. This is only for your revision purposes. So when we consider a shield volcano, so generally it is broad, okay, in terms of gentle sloping mountain, and breadth is much larger as compared to the height. Hawaiian Islands, the Mauna Kea, Mauna Loa eruption that you have, magma is usually basaltic, quite eruption. Stratovolcanoes, composite volcanoes, now layers of lava flows, pyroclastic and hardened mud flow deposit. So magma is usually intermediate, a mixture between basaltic and felsic, long lifespan characterized by both explosive as well as non-explosive eruption. Mount Fuji, Mount Rainier. Mount Rainier, again, we have discussed in the mapping classes, present in the region around Washington state of US. You would recall from that, right? So Washington, then Mount Shasta, then Vesuvius, St. Helens, all of them are shield. Then when you consider lava dome, so here it is high in silica, felsic, very viscous, solidified lava that was thick and viscous when molten. Larsen Peak in California. Cinder cone, it can be basaltic, short lifespan, and pyroclastics, they also accumulate. Example, Sunset Crater, and you have Paricutin in Mexico as well. Okay. Then you have a kind of an eruption, which is basically known as the fissure eruption or fissure volcano, generally observed in the regions of divergent plate boundaries, right? Where you have the plate movement which are away from each other. So, in this particular case, large cracks are created on the Earth's surface, and volcanic materials they keep on erupting out of this. So, that is the case of a fissure eruption, mostly across divergent boundaries. Now, here, this is also known as the Icelandic kind of eruption because very common in Iceland. So that is why Icelandic eruption type. Okay, large cracks open up and you have continuous materials which keep on emerging. Now, which kind of materials? Fluidic and basaltic lava. Basaltic lava is ejected. Okay, and that is why it will again be non-explosive in nature. Non-explosive in nature in general characteristic. Then you have Another kind of, so example of this, you can take two examples. One is the famous Laki eruption of Iceland. Eruption, Iceland. And secondly, you also have the case of the Trevera eruption. Trevera eruption near New Zealand. Near New Zealand. Okay, near the region of the Tonga Islands. That is where you have the some divergence happening in the localized area as well. Then you have large landforms which are created due to the subsidence of the central portion of the volcano, and those are known as calderas. So when we consider calderas, how are they created and when are they created? So there are a series of events which take place for the formation of these calderas. So first of all, you have so much amount of explosive eruption that the ground weakens, the landform tends to weaken. And then when you have a massive explosive eruption which leads to the expulsion of the entire magma chamber, the magma chamber becomes empty, then the central portion simply undergoes a subduction process. So basically you have continued eruption and then the creation of a vacant magma chamber which leads to the subduction of the central portion. Then it is filled by seawater, also groundwater. So that is the case of caldera. So emptying of magma chamber, right? And then after that, you also have the case of explosive eruption, creating cracks, creating cracks. And as a consequence of this, you have the central portion caves in, and then filled by groundwater or seawater. By groundwater or seawater. Okay? So that creates a volcanic caldera in a region. Then, here you also have the case of mantle plumes. They are very different from a tarn lake. Tarn lake is basically created because of the glacial erosion. A glacial erosion where it erodes a certain region substantially, creates a depression, and the melt water accumulates, just like a cirque. So that is a tar lake. This is basically a larger mountain system which has been exploded. And then you have the surrounding seawater, etc., which basically fill in that region. So very, very different in terms of comparison also. So the only similar thing between them is both have water. That's it. Otherwise, they are not at all similar. They are very different in the process of formation. Then we come to the case of mantle plumes. Now, what are mantle plumes? The heat from the interior and the convection current from the interior that rises up oftentimes, whereby liquid or molten portion of the mantle, they keep on rising up and they rise up. And we discussed in the convection current theory what they do. So similarly, as they rise up, they can impact the surface substantially. They can lead to volcanic eruption also. And that is the case of a mantle plume. Okay. Now this mantle plume is the convection of magma in narrow columns in upward direction from the core mantle boundary, also from asthenosphere. Sometimes that can also get created. So that is what is known as mantle plume. Now it can convection current, give rise to convection current leading to plate movement. convection current leading to plate movement, right? And then it can also lead to series of volcanic eruptions, series of volcanic eruptions in the same place, right? In the same region. And that creates what we refer to as the volcanic hotspots. That creates volcanic hotspots. Okay. So that is what is known as the mantle plume, right? Now, it is basically the molten materials or very hot materials which emerge and then they can hit the surface, leading to the movement of the plates, the divergence, convergence, transform movement, all of them can be initiated. But if they create that volcanic eruption, now, in the same region, the volcano will continue to act for multiple hundreds and thousands of years and millions of years in the same region. So, those areas are known by the name of volcanic hotspots. Right? So, here you can have the mantle plume which supports the magma chamber, and you can have continued volcanic eruption. So, as the plates move above them, you can have a series of these mountain chains or these landforms or sea mounts which get created. So, example, Reunion Islands. Reunion Islands, right? Hawaiian Islands. These are regions of volcanic hotspot where volcanic eruption has been created or has been occurring for millions of years now. Reunion Islands, volcanic eruption has been occurring for almost 100 million years now. That has created the Deccan traps that we experience in India. So here you can see the example of the volcanic eruption or the hotspot in the region of Hawaii. But the same eruption at one point of time had also created the emergence of these islands, that is, the Suiko Islands that you see, the Midway Islands, all of them, they have been created due to the hotspot which lies here. So as the plates they move above them, they end up leaving a trail of these mountain chains. In fact, this indicates to you that at one point of time, this region A would have been present above Hawaii. So it would have moved north and then have moved westwards to create this kind of a landform, that is hotspot. Then we have the intrusive volcanic landforms. What are intrusive volcanic landforms? Position of mantle plume is fixed, yes. Mantle plume and convection current are not the same. Convection current is basically the entire cycle which is generated due to the movement of materials. Mantle plume can lead to formation of convection current. Without mantle plume also convection currents can exist in certain areas. Okay, but mantle plume can only be a part of the convection current. It cannot be the entire convection current. Okay, I hope that is understood, right? Now, intrusive volcanic landforms, when magma solidifies in the interior. Okay, solidification of magma in the interior. I hope we are aware about the difference between magma and lava also. I hope we are aware about that. Because when we consider magma, magma is the case of what? Molten materials in the interior. Lava is what? Lava is when these molten materials emerge on the surface. That is lava. Okay. So when solidification of magma happens in the interior, it is a slow process, and that is when you have the intrusive volcanic landforms. Now these intrusive volcanic landforms, they are classified on the basis of the shape in which they have solidified. Right? So they are classified into, for example, batholith. Batholith is when the entire magma chamber in itself solidifies. That is what leads to the formation of batholith. Entire magma chamber has solidified. Then you have the case of laccolith. So, if you consider a magma chamber, materials try to emerge, but then due to the hardened crust, they solidified like this. This is your laccolith. Okay? This is your magma chamber. Okay? Then, after that, you have lopolith. Lopolith is what? Lopolith is when the magma chamber had materials which tried to come out, but then after that, again, very hardened rock structure led to the solidification like this. That is your lopolith. Okay? Inverted dome. Yes, correct. Then you have phacolith. What is phacolith? Let's suppose the rocks are arranged in a kind of a layered format or a folded format. So molten materials, they try to emerge from the magma chamber, but as they were emerging, they solidified in the kind of manner like this, in the folds, right? This is your phacolith. If molten materials, so yes, wavy nature is how they have solidified. That is your phacolith. After that, you basically have sills and sheets. That is when you have horizontal solidification. Solidification. That is sills and sheet. And then you have when materials solidify in a vertical pipe-like manner, vertical pattern, that is known as dike. When they solidify in a vertical manner, that is what is known as a dike. Okay, so these are the various classifications that you come across for the entire intrusive landforms. So overall, when the entire magma chamber in itself solidifies, that is what leads to the formation of batholiths. Example, in Ranchi Plateau, you have the Ranchi batholith, which is in existence. That is your batholith, right? It gets exposed later on when the overlying layers, they are eroded and they are removed. Laccoliths, when you have the solidification, somewhat like this. That is your laccolith. Lopolith, flat top and a convex base. That is lopolith. Phacolith, when they basically solidify in the wavy manner, in the anticlines and synclines. That is the case of phacolith. And sills and sheets, when they solidify in horizontal layer, that is sills. If it is very thin, then it is a sheet. For example, this is the case of a sill. And when they solidify in vertical manner, that is what is referred to as dikes. Okay. Then the eruption and the kind of lava is also something which is determined by the silica content. That is the chemical property of the lava determines whether it will be fluidic or whether it will be very viscous. It will accumulate in a region. So if the silica content is very high, that is when you have felsic lava, it is viscous. It will not flow. Okay. So silica content overall, if it is 70%, it is felsic lava. Now, when you have this viscous lava which tries to come out, obviously lot of energy is required, lot of pressure is also required, and that eventually can lead to the explosive eruption. So generally associated with explosive eruptions. Gas content is also very high in those cases. When silica content is very low, mafic, right? In this non-explosive, shield volcanoes, fissure volcanoes, there you have silica content, which is around 50%. These are the various volcanic areas and volcanic zones which are present. Sheet is less thick, yes. Sheet is less thick. Sills are much more thicker, right? So that is the generic classification, right? Now, these are the general volcanic zones. Majority of the volcanoes you will find to be present in the zone of oceanic convergence. Other than that, in divergent areas also, volcanic eruptions can be found, but majorly in the regions of oceanic convergence. Now, you also come across a feature that is hot springs and geysers. What are these hot springs and geysers? So, when we talk about the case that you have when the groundwater reaches the surface, it provides hot springs at temperatures closer to the boiling point of the water, right? It can heat the nearby. So whenever you have hot rock material, either due to exposure to magma or even due to compression, if heat is produced in large quantity, like we have discussed in the case of Himalayas, in either of these cases, whenever you have the presence of groundwater near to boiling point when it comes to the surface, it is hot springs. And in certain areas, you have the steam which is produced, that is, when water gets in contact with magma, immediately it vaporizes, it releases as a large steam section or a steam column. Again, after that, some time period of 1 minute or 30 seconds, again after that water gets in contact, again releases as a steam column. Those are known as geysers. Okay, so this is generally where emission of steam and hot water occurs at intervals from the small vents. Okay, now let's take a look at some of the PYQs again. So consider the following statements. In a seismograph, P waves are recorded earlier than S waves. In P waves, the individual particles vibrate to and fro in the direction of wave propagation, whereas in S waves, the particle vibrate up and down at right angles to the direction of the wave propagation. Which is the correct answer in this? It should be easy now that you have revised this. Very good. First statement, in a seismograph, P waves are recorded earlier than S waves. Yes, the speed is around 4.5 to 13 kilometer per second. In P waves, the particle motion is the same as the direction of the wave motion, whereas in S waves, it is perpendicular. So both the statements are actually correct. So correct answer in this is going to be C, that is both 1 and 2. Now, here, weathering is something that we will study right now. Now, consider the following: pyroclastic debris, ash and dust, nitrogen compounds, sulfur compounds. How many of the above are produced or products of the volcanic eruption? That is, during a volcanic eruption, which of these are actually released? Correct? All of them? All four of them are actually released during a volcanic eruption. Again, a simple and an easy question. Now, the area associated with weathering. Now, when we say weathering of rocks, what do we mean by that? Weathering basically means that any existing rock, due to the physical forces, due to the chemical action, or even due to biological actions like activity of the plants, etc., they disintegrate in the same region. So, breaking down of rocks into smaller fragments, that is known as weathering. Now, weathering is broadly categorized into three types. You have physical weathering, you have the case of chemical weathering, and you have biological weathering. Isn't it? Now, when we say physical weathering, that is basically initiated whenever you have activities of heating, cooling, expansion, contraction, ice formation, etc. So then the rock disintegrates, that is physical weathering. Okay. For example, rock disintegration, granular disintegration, sheeting, all of this is physical weathering. Then chemical reaction, oxidation, solution, hydration, where you have some chemical reaction, water interacting with certain types of minerals present in the rocks and so on. That is chemical weathering. And then you have biological weathering. Let's suppose in the cracks of the rocks, you have the growth of certain plants. So the roots will keep on extending the cracks, and that is when it will disintegrate. So that is the case of physical, chemical, and biological weathering. So physical weathering, heating, cooling, expansion, compression. What are the types? One is the case of block disintegration. Now, what happens in the case of block disintegration and where is it experienced? So, in hot desert areas with intense temperature fluctuation, where the temperature ends up varying very frequently. So, for example, consider a larger rock. Continuous expansion and contraction means what? Near the region of the cracks, that is where the cracks will continue to expand. Especially in desert areas, the daytime temperature is very high, nighttime temperature is very low. So that is when it will end up breaking. Okay, so that is the case of physical weathering and block disintegration. Now, here you also have a case of granular disintegration. What is the meaning of granular disintegration? Understand that. Let's suppose you have a larger rock. This rock, like a sedimentary rock, has various different materials present. One material is present here, different kind of element is present here, and so on. Let's assume different types of materials are present. Now, when it is getting heated up, all the materials will expand at a different rate, all of them. So, larger materials will expand at a different rate, smaller materials will expand at a different rate, and so on. Depending upon what kind of materials they are, also the expansion and contraction will differ. So, that means in the areas of these joints, it will start to get weaker and weaker. It will start to get weaker and then it will eventually break away. So that is where the small grains, they start breaking, and that is where you have granular disintegration. Small particles, they break away. Then you have frost cracking, which is again a part of physical weathering. What is frost cracking? So let's suppose you have a larger rock. Now through a crack, water enters into this region. Now, when water enters into this region and the water then freezes, it will form ice. Ice tends to expand. So the cracks will get deeper, isn't it? That means more water will get into it. Let's suppose the water freezes again. Slowly and steadily, the crack will further deepen, leading to the complete breakage of these rocks. So that is a part of physical weathering, which is known as frost cracking. And then you have salt weathering also. So let's suppose in arid areas, even in coastal region where seawater is a common influence. So in that particular case, salt water, saline water, that gets in, right? Eventually the salt evaporates, but during the eventually the water evaporates, leaving the salt behind, and that is when the rocks and the cracks are expanded. There's huge amount of pressure which is exerted, and you have this honeycomb like structure which is created, observed even in the region of Gujarat and Rajasthan. So that is something which is observed, that when water evaporates, salt crystals are left behind. As they grow, they exert pressure on the other crack systems, and that is your salt weathering. Then you have the process of sheeting. What is sheeting? So, when the top, when you have any kind of rock, on top of it, you have multiple different materials which are kept. And suddenly, the materials from above are removed. In that particular case, the layer suddenly unloads itself and it peels away like that of an onion shell. That is your sheeting. So the rocks which are buried deep in the earth, they are under enormous pressure. And when overlying materials are eroded away, the pressure reduces. So think about it. So well, let's suppose you have a landform like this. It is putting a lot of pressure on the underlying rocks. But as soon as this region gets eroded and removed, then this is exposed and it starts to flake away. That is sheeting. Okay. Then you have chemical weathering. That is basically you have the case of chemical reaction which leads to weathering process. How salt weathering occur due to thermal action? See, that salt water, when it enters into the cracks and crevices of the rocks, evaporation has to occur, isn't it? Evaporation of the water has to occur, then the salt will keep on accumulating. Now, that evaporation is dictated by what? Rate of heating and cooling. So, that is why it is interlinked with each other. Okay. Now, unlike the mechanical weathering, here this changes the mineral composition of the rocks itself. So in hot and humid tropical regions with high amount of rainfall, that is where we will experience the case of chemical weathering. Okay. So it is also of various types. You have solution. For example, if let's suppose you have a rock which consists of materials like here you have calcium. Now, if there is rainfall in this area, calcium will keep on getting dissolved and will be removed, isn't it? So that is the case of solution. Calcium is dissolved and is removed. So here weathering has happened because of a chemical reaction where water has actually reacted with calcium and has formed the various solution. Then you have oxidation. So that is where oxygen from the atmosphere reacts with the minerals which are present in the rocks, right? And that creates these oxides on the surface which are weaker and which are prone to breakage. For example, when you consider basalt, basalt has got iron which is present. Easily it can experience iron oxide formation, something known as rusting, and that is when it can detach itself. So here, oxygen is the driving factor. Then you have hydration. Hydration, where too much of water absorption weakens the structure. And that is when it basically weakens the rocks. So absorption of too much of water through the pores leads to a kind of a small swelling and eventual breakage and soil formation. Then you have hydrolysis. So hydrogen ions of water. So for example, feldspar in granite reacts with carbonic acid plus water and that forms a clay mineral, that is kaolinite. So that again is a process of hydrolysis. Okay. Then you have carbonation, where in oxidation oxygen was reacting. In carbonation carbon dioxide reacts and forms the carbonic acid. Okay. H2, the bicarbonate and the carbonic acid that you have, and that eventually can dissociate again and lead to breakage. Then you have biological weathering. What is biological weathering? So let's suppose in the cracks of the rocks you have plants etc which start growing. Now these plants will have their roots which will deepen within the cracks. Rodents will also enter, and eventually the cracks will expand and lead to breakage. But this breakage is not happening because of expansion contraction. This breakage is not happening because of the case of uh, the either the case of when we consider any chemical process. This breakage is only happening because of biological processes. That is why it is known as biological weathering. Okay. Then we come to the case of landforms, the final portion in geomorphology, that is the case of landforms. Now, here for your prelims, you need to know which are the erosional and depositional landforms created because of fluvial action, fluvial landforms, that is, landforms created by the river action, landforms created due to the glacial action, landforms created due to the case of When we talk about the karst topography, underground water, karst, then landforms which have been created due to wind, aeolian, and created due to sea waves. Okay. So for each of them, you need to know which are the erosional and the depositional landform. Okay. Right. So fluvial landform, for example, you have erosional as well as depositional. Now, majority of the erosional landforms by the rivers, they are created in the young phase or the youthful stage of the river action. Valleys, gorges, potholes, plunge pools, all of them in the youthful stage. Youthful stage. Okay. Then incised and entrenched meanders, they are created in the mature stage. Mature stage. Okay. Whereas when we talk about depositional landforms, most of them created in the mature and old stage. Old stage. Whereas only one of them, that is alluvial fan, this is the only one which is created in the youthful stage. Okay. So these are the landforms created by the rivers in general. So let's take a look at each one of them. Starting with the valleys and the gorges. Gorges, just like valleys, they are very narrow, however. Very narrow with a very small bottom, narrow bottom. That is the characteristic feature of the gorges. Okay, do you guys need a break right now? Do let me know if we need a break, or we can have a break half an hour later as well. Do let me know. So if we take a break now, it will be around 10 minutes break. Okay, 15 minutes break. And then after that, we will come back. We will finish some portion and then we can have a dinner break. After landforms, perfect. Let's finish the portion of landforms. And then after that, I will give you a half an hour break so that you can have your dinner as well. Okay. So let's finish this portion of landforms and then you can have a half an hour break. Okay. Right. Now, so when we talk about the case of these gorges, gorges are very narrow valley like structure with steep side walls. That is the case of gorges. Okay. Created in the youthful stage. Valleys, however, broader bottom and gentler walls in general. Then you have potholes and plunge pools. Potholes basically are created across the river bed as you have various different rocks, larger boulders, if this is the river, as you have various different rocks and boulders which hit the ground, the river bed, that is when it creates a kind of a pothole. Okay, it is not very wide, it is something which is very narrow. Grand Canyon is not an example of a gorge, by the way. Grand Canyon is not an example of a gorge. The region of Grand Canyon you will find as an example associated with the incised meanders in those areas. Because, as we have discussed again in the mapping session, you have the Colorado Plateau, which is made out of sedimentary rocks, where upliftment of the land has happened. And the river Colorado continued to drain in the same area, creating those kind of canyon like structures. Right? We have discussed that in the mapping sessions. So this is where potholes get created. Now then, we also have the case of plunge pools. How plunge pools get created? So at the base of the waterfall, as the water falls in a region, it keeps on falling in the region and creating a kind of a depression. Okay. Now, as it creates a depression, this is what is referred to as a plunge pool. That is what we have as the case of a plunge pool. Okay. So in general, you will observe that you have a waterfall which is created like this. This is the base that you see. That is where you have a plunge pool. It is easier to understand with the help of animation. Then you have incised meander. Excuse me. What is an incised meander? So, in the mature stage of the river flow, as the river is moving, if the land experiences an upliftment due to the interior forces of planet Earth, endogenic forces of planet Earth, as the land experiences an upliftment, the river continues to flow in the same region that it has been flowing. It does not change, but it erodes any upliftment in its course. So that is when you have the surrounding land which gets uplifted while the main river maintains its own original course. That is what is referred to as an incised meander. Okay, so that is referred to as an incised meander. Example, you will find incised meander across even Subarnarekha, and you will find incised meander across the Rio Grande River. Rio Grande, Colorado River, in those areas in North America, you will find that. Okay, Colorado, Rio Grande, and even in the region of Chota Nagpur Plateau, Nagpur drainage. That is also where you will find this. Okay. Then you have alluvial fans. So basically, at the base of the mountains, when you have large amount of sediments, boulders, etc., which are brought by the streams, all of them are dumped at the base of the mountain. And that is what creates an alluvial fan. It is the only depositional feature to be created in the youthful stage of the river movement. Okay, so when you consider a mountainous area, if a river is coming down, bringing large rocks, boulders, etc., all of them will be deposited here. So that is your alluvial fan. And then the river will move into the plain region. Okay. Without raising the land, the water flow will also create erosion. Yes, correct, Harish. It will create erosion. That is true. But as the land is getting uplifted, river continues to move in its own place. The surrounding land continues to get uplifted further. Right? Can it be called as a Bhabar region? See, the lower extent of alluvial fans when they merge, that is what we call as the Bhabar region in the northern plains as well. Okay. Then you have an erosional cum depositional feature. Erosional cum depositional feature that is known as a meander. Wavy pattern which is drawn or which is basically formed by the river flow. That is what is referred to as a meander. So this is basically induced due to erosion in certain areas and then deposition in certain areas. Oftentimes what happens is when you have a very large meander formation, sometimes a portion gets cut off and the river starts flowing in a shorter way. Why? Because in this region, you will have deposits which get created. So that ends up creating features which are known as oxbow lakes. Creates features which are known as oxbow lakes. Okay. Now, these are depositional in nature. Depositional in nature. Example here. This is also your oxbow lake. Okay. Then after that, when a river drains, through a region, oftentimes in the late mature or the old stage, it is carrying so much amount of sediments that lot of these sediments, they will get deposited in the channel of the river flow itself. Lot of the sediments, they will get deposited in the channel of the river flow, and that is when you won't be able to distinguish which is the main stream of the river flow. So that is basically what is known as a braided channel. Braided channel, just like the braids of the hairdo. So that is where deposition of sediment within the main stream of the river itself. That is what is known as braided stream. And eventually, when the river is about to meet the sea, that is when the finest of the particles, they get deposited, and that leads to the formation of deltas. So deltas are very fertile stretches where the finest of the particle size, they get deposited. Those are actually known as deltas. Okay, so that is how you have the delta formation, which is very, very fertile. Then you have landforms which are developed by underground water. This is also what is known as karst topography. Topography. Now, this is basically because of the chemical erosion. It happens because of chemical erosion of the rocks. Rainwater, underground water, when they carry out chemical erosion of the rocks, that is when erosional structures like sinkholes, uvalas, caves, all of them are created, and they also basically solidify and accumulate to form stalactites, stalagmites, or pillar like structure. So, what tends to happen is that you have the water which interacts with those chemically active rocks where you have calcium, etc., and the water dissolves them, and that is when you basically will observe that they create that underground caves, caverns, and such kind of patterns. Okay, so here you have various different erosional structures. So initially, when you have water, let's suppose a rainwater which falls in this region, slowly and steadily you will have multiple channels which get created. A sinkhole can get created, right? You also have the formation of lapis. What are lapis? Corrugated surfaces which get created, as you can see, as those rocks or those materials which are soluble in water, they get dissolved and drained away. These outcrops, rocky outcrops, are left behind, and that is known as lapis. Okay, they have low ridges and pinnacles which are present, and the rainfall in the regions which are rich in limestone, that is where limestone will get deposited, and then you have these lapis which are left behind. Okay, then you have bowl shaped depression which is created, some of the sinkholes getting together creating a large bowl shaped depression. Those are known as dolines. Okay, those are known as dolines. Then multiple dolines, they get together, multiple sinkholes, they get together to form a kind of a valley sink, and that is known as an uvala. So uvala is basically where multiple of these doline structures will get together. Then you also have a polye. Polye is elongated basin, just like the case of an uvala, flat floor and steep slope. So much deeper than that of an uvala. Okay. So here, if you have a shallow valley-like shape, uvala, a much deeper with vertical side walls, that is a polje. Okay. Then sometimes the materials which have been eroded, chemical solution is formed. Now they start accumulating on the roof of the caves, and that is when they create the stalactites. The overhanging structure from the roof of the caves, that is what leads to formation of stalactites. Sometimes these materials, as they fall on the ground, there again they start accumulating into structures, and that is known as stalagmite. Sometimes the stalactite and the stalagmite can join together to form a column or a pillar. Okay, so what are the erosional structures that we have seen? Sinkhole, swallow hole, dolines. Dolines will combine to form uvalas if they have steep side walls, poliers, and then depositional structure if they are hanging from the wall or from the roof, stalactite. If they are protruding from the ground, stalagmite. If both of them join together, that is when you have the pillars or the columns. Then you have the landforms which are developed by the glacier, erosional and depositional landform. So glaciers, they basically have one of the largest erosional power that is observed in the nature. So when they erode a mountain in such a way that they create an amphitheater like structure, that is what is known as a cirque. Okay, they basically create a amphitheater. They erode or scoop out the mountain. That is a cirque. It is erosional. Now let's imagine in the same mountain you would have erosion from other side also, glacial erosion from other side also. Then what would be left behind is a narrow ridge like structure where erosion has occurred from both sides. That is known as an arete. Okay, that is known as an arete, where glacial erosion has occurred from both sides, leaving behind a narrow ridge-like structure. If, let's suppose, erosion is so significant that erosion has happened from all sides, leaving behind one isolated peak-like structure, that is what is known as a horn. Matterhorn in Switzerland is an example. Now, in the coastal area, the glaciers they erode and create valleys, which are then later on filled by seawater. Those are known as fjords, very common in the region of Norway, even in New Zealand. New Zealand. That is what is known as a fjord. So where glacier has created a kind of a U-shaped valley, which is then filled by seawater. So it will have saline water presence and formation. That is a fjord. Then we talk about the depositional structures. So when the glacier actually deposits materials when the speed reduces, so these are known as moraines. Depending upon where the deposition has happened, moraines are classified. For example, if the deposition has happened on the sides, it is known as lateral moraine. Lateral moraine. If the deposition has happened in between, in the center, that is what is referred to as medial moraine. Moraine. If the deposition has happened at the end of all the glacial melt, that is known as end moraine or terminal moraine. End moraine or terminal moraine. Okay. Then you also have the depositional features created by glacier. As the glacier moves, it ends up depositing this horizontal egg-like structure or an inverted spoon-like structure. That is what is referred to as drumlins. Okay. It is also what is referred to as the basket of eggs topography. Basket of eggs topography. Okay. So this is where multiple of these drumlins can exist together. Many of these drumlins can actually exist together in the same place. So this is where you have the glacier depositing some of the glacial till and tillite which is to be found. If the deposition happens in a long linear fashion, then it is known as eskers. deposition in a linear fashion. In a linear fashion. Okay, that is known as esker. Okay, then landforms developed by wind, aeolian landform. So you have various different types. For example, mushroom rocks. So mushroom rocks are erosional structure because when you consider any particular rock in the desert area, wind speed is very high in the desert, isn't it? Now that high wind speed means smaller particles, the smaller particles, they move here, they are moving here, or larger particles, they are moving here because they are heavier. Smaller particles, as they are lighter, they can be uplifted. Okay, but larger particles will move closer to the surface. So that is when they will continue to erode the rock. Eventually, the rock will be eroded from the bottom and polished from the top because smaller particles are at the top. Smaller particles are at the top and larger particles at the bottom. Particles at the bottom. That creates a mushroom type of structure. That is the case of mushroom table or mushroom rocks. Then you have yardangs. Yardangs are the rocky outcrops found in large numbers. Sometimes even in Thar Desert you will find them, but mostly in the region of Sahara you will find them. Now what happens is here the base rock gets exposed because the overlying sand gets eroded, so the base rocks get exposed. And then the continued wind motion means that you only have the softer rocks which get eroded and the harder rock structure gets left behind. And that leads to the formation of what we refer to as yardangs. So that is what is known as yardangs. Okay, hard rock structure is left behind. Generally, the shape is in the direction of the wind motion. In the desert, in the sand, you have different types of materials, fine particles, larger particles, both of them are present. When the wind will blow, the larger particle is heavier. It won't be carried away by the wind easily. But the smaller particles, being lighter, can easily be carried by the wind. So, there also, sometimes you have the creation of deflation hollows. Okay, deflation hollows get created. Now, this deflation hollow basically means that you have, let's suppose, a region which has got larger particles of sand and finer particles of sand. So, as the wind blows, the finer particles are eroded. So, you have a shape like this. The larger particles are left behind. Finer particles are eroded. That is what is known as deflation hollow. Okay. Now, all these particles which the wind is carrying, it will drop them somewhere, it will deposit them somewhere. And that is what leads to the formation of sand dunes. Dunes are nothing but accumulation of sand that you will observe. That is what is sand dune. Now, depending upon how the accumulation has happened, again based upon the shape, you have the various classification. That is, if let's suppose the wind direction is uniform, in the same uniform direction, the dunes, they get deposited parallel to each other. These are known as transverse dunes. Okay. However, when the wind direction is convergent, they converge, that is when you will have the longitudinal dunes which get created. If the wind is converging from all direction, accumulation leading to the formation of a star-shaped dune. Now, sometimes if you observe this dune, it acquires a substantial height and the central portion simply slips. The sand simply slips. When the sand slips, it creates a crescent shaped dune formation that is known as perchance. Okay, crescent shaped dune formation where the central portion has slipped, that is known as a barchan. So barchans are dunes where the central portion has experienced slippage. Then landforms developed by wave action. So the action of the various different waves that you observe, the sea waves in the coastal area. So in the coastal area, the sea water, it is saline in nature, reactive. So there will be some element of the case of chemical erosion also, and some case of physical erosion by the force of the waves also. Okay, so you have various different types of features created. For example, in the coastal area, sometimes the sand gets deposited parallel to the coastline and attached to the coastline. These are known as spits. Spits can sometimes be many kilometers long. Okay, so that is where deposition has happened attached to the coastline, closer to the coastline, and extending further into the sea. Then here you have the case of an island, let's suppose, and deposition which attaches the mainland to the island, that deposition is known as a tombolo. Okay, so spits and tombolos, these are depositional feature. Depositional feature. Tombolos basically will attach an island, will tie an island to the mainland. That is where this island is also known as an island which has been tied. Tied island. Okay. Then it creates, the sea waves can create caves, arches, and eventually they can also get degraded. So initially, let's suppose sea action, chemical action is happening, physical action is happening, there is a cave which gets created. If the action continues, erosion continues, water will flow from one end to another, and you have an arch which can get created. Then after that, you basically will observe the roof of the arch is not stable, it is overhanging, so it immediately falls down, leaving behind a structure that is known as a stack. Eventually, that stack will also get eroded and lead to the formation of a stump. Okay, so like that, these are some of the erosional and depositional features. Let's take a look at this question, and that will bring us to the end of geomorphology. Cirques, arêtes, horns, and drumlins represent which type of topography? A simple question, but this is the kind of question that you can expect in UPSC. It is the glacial landform, right? These are basically your glacial landforms. Okay. Now, after this, we will start with climatology. Evolution of atmosphere is where we will start. Before that, take a break. Take a break of 30 minutes, and then we will be back and we will continue with climatology. Okay. Okay, so now we continue from the portion of climatology. Now, climatology, as you would be aware, one of the very vital areas in your prelims preparation. A lot of questions are framed, and in the past couple of years, questions associated with the basic concepts of climatology. That is the behavior of the isotherms, the variation that you observe in the isotherms, and so on. Heating of land and water, what is the temperature difference thereby? That is something that UPSC has been targeting. Otherwise, UPSC is known to ask multiple concepts amalgamated or cohesive in one question. You can have a concept of a tropical cyclone, a concept of an ocean current included within the same portion. Now, one other area of climatology that you will find is very relevant is that of climate classification, that is the Köppen's classification, British type of climate, China type of climate, and so on. Now, that is something that we will cover today so that you can have a revision. But in case any of you want a detailed revision for that process as well, I will put a link to the video that we did, and that is a detailed aspect of the entire climatic classification that will be provided in the description. I will share that on the Telegram channel with you guys as well so that you can revise that for the climate classification. Now, having said that, in the portion of climatology, we first of all start with the basic concept of the atmosphere and heating and cooling. Now, when we consider atmosphere, what we see today, that is not the atmosphere which was always in existence. Okay, that atmosphere has changed over a period of time. So there have been distinct phases where the atmosphere has evolved itself. First of all, when the planet was created, at that point of time, you had a primitive form of atmosphere, what would also be regarded as the primordial atmosphere. And this would be dominant in hydrogen and helium. Okay, it would be dominant in hydrogen and helium. So that would be something which would be present in primordial atmosphere. Over a period of time, the solar charged particles from the sun, that is the solar winds, the solar flares, now all of them, they strip that hydrogen and helium to a large extent. Because remember what we discussed in geomagnetism, once you have the magnetosphere which is established, then your air particles are protected. But right when the planet was getting created, the magnetosphere was not so clearly established. That is why, due to the weaker magnetic forces around 4.5 billion years ago, these solar winds, they stripped away hydrogen and helium from the atmosphere. Then you had, during the phase of degasification that was marked by series of volcanic eruption. That is when newer gases were introduced. Which were the newer gases? You had ammonia, NH3, then you had carbon dioxide, then you had carbon monoxide, sulfur dioxide, methane, water vapor, etc. All of this was introduced into the atmosphere. Oxygen was present in very trace amount, very little amount, not in major amount even at this point of time. But the nitrogen which was emanated or emitted, that stayed in the atmosphere for a longer duration. That is why even today, nitrogen is the most dominant gas in the atmosphere. Because when we talk about nitrogen, that is N2, N2 has got triple bonds between the nitrogen atoms and the molecules. And it is a very stable state, very stable structure, doesn't react easily. Okay, so it is almost inert, inert in nature, non reactive in nature. That is why it does not form many compounds with the rocks. We have seen in the case of weathering that oxygen can lead to the formation of compounds, isn't it? Oxidation can happen. Carbon dioxide can lead to carbonation. There also a compound formation can happen. But when it comes to N2, it stays as it is. Then you had the planet evolution of life and the genesis of life. Now that is when when you had the growth and the sudden increase in the presence of mosses and lichens for the first time, that is also when oxygen quantity started to increase. So, this is when oxygen increased in the atmosphere, oxygen increased into the atmosphere, and that was because of the process of photosynthesis. Now, due to photosynthesis, the proportion of carbon dioxide reduced and the proportion of oxygen would increase, making life possible on planet Earth. This is where you should be prepared for a kind of a question that when you or when you talk about atmosphere, is oxygen or was oxygen always present in the atmosphere? Answer is no. Was nitrogen always present in atmosphere? Answer is no. The atmospheric structure has changed over a period of time. Now, these different gases which are present in the atmosphere, they play a substantial role in regulating the temperature. That is, they trap the heat which is emanated from the Earth's surface. So, the sun, because it is very, very hot, the sun releases immense amount of energy, and that huge amount of energy is released in the form of short waves. So, those are your short wave solar radiation. Solar radiation. They are high in energy, very high energy levels. Okay? Very high energy levels. So they will penetrate through the atmosphere directly. Okay? They will be penetrating through the atmosphere and they don't have much role to play in heating the atmosphere. On the other hand, when the ground surface starts getting heated up, that is when it also starts emanating some amount of energy in the form of long waves. Some of that escapes into the space. This is your long wave terrestrial radiation. Low in energy terrestrial radiation. This is the one which carries out heating of the atmosphere. Okay, it will heat up the molecules in the atmosphere. Now, it is this long wave which is trapped by the gases which we know as the greenhouse gases. Okay, you have the greenhouse gases. Now, these greenhouse gases like carbon dioxide, methane, water vapor, all these are your greenhouse gases, nitrogen oxides, sulfur dioxide. Now, these will reflect back the terrestrial radiation and continue to heat up the surface. Heats the surface. So, that is the overall process of the greenhouse effect. So, greenhouse effect ideally, is it beneficial for planet Earth or is it harmful for planet Earth? So, in its original state, it is always beneficial for planet Earth. It helps maintain the temperature even during night time. Otherwise, during night time, the temperature would have been very, very low, negative, minus 100, minus 150, etc. What you observe in the case of moon, for example. Daytime temperature is high, nighttime temperature is very low. So this helps maintain temperature on planet Earth. Okay? Planet Earth. So that is the case of this greenhouse effect. However, excessive amount of these greenhouse gases mean that almost all the heat is trapped and continues to heat the surface. Excessive amount of heat basically is trapped and it continues to heat on the surface. And that is when excessive greenhouse gases leads to global warming. Excess greenhouse gases lead to global warming. Okay? But primarily helps maintain the temperature and does not allow the temperature to basically fall below the freezing point in many areas. So it is a process. It is a process involving multiple different stages. So first of all, solar radiation reaches the Earth's surface. Some of it is reflected back from the surface, from the atmosphere itself. Now then the surface starts the heating up, solar energy is absorbed and the surface starts heating up. After that, once the surface starts heating up, then heat radiates from the surface back into the space. It is this heat which is responsible for heating of the atmosphere also. So the atmosphere gets heated from the ground surface and then moves upwards. Okay. Some of the heat is trapped by the greenhouse gases in the atmosphere, keeping the planet Earth warm enough to sustain life. Human activities such as industrialization, vehicular emission, they have increased the amount of greenhouse gases, they have increased the amount of heat which is absorbed, and that is why we are facing the issue of global warming. So these are the various different stages which explains the greenhouse effect. Now, atmosphere overall is composed of various different components or constituents. Each of them have their own distinct role that they play. For example, when we consider the gases, so the most dominant gas is nitrogen, which is present around 78% of the Earth's atmosphere is made out of nitrogen. Then you have oxygen, around 21%. Then after that, you don't have carbon dioxide, you have argon, which is close to around 1% is argon, then followed by carbon dioxide. It is this carbon dioxide's proportion which is increasing, which is leading to increased amount of heating as well. So what is the role played by gases? First of all, they provide life or sustain life, right? If there would be no oxygen, we would not be able to breathe. Respiration is enabled by these gases. If there would be no carbon dioxide, then no photosynthesis. Plants would not have been in existence. So they sustain life. Other than that, they warm or carry out greenhouse effect. Greenhouse effect. Okay. Then after that, when you consider water vapor, water vapor, which is present in the atmosphere, by the way, in case we are, this is again an area where UPSC has been asking questions and repeating the question. That is the proportion of water across the planet Earth. I hope we are very clear in that. If you consider the water across planet Earth, right, there, please understand 70% is salt water in the oceans, right? Oceans and seas, right? 30% is fresh water. I hope we are aware about that. Now, out of this 30% of fresh water, if you consider only the fresh water, around 69% is in ice caps and glaciers. Okay? Around 30% is in groundwater. Around 0.4% includes water vapor in the atmosphere, rivers, lakes, etc. Okay. So this is a question which UPSC has asked twice. That is, and that too in the past 10 years itself. That is, after the total amount of majority of the fresh water is in ice caps and glaciers. After that, where do you find large amount of fresh water? And many candidates, they end up marking rivers. It is not rivers, it is the case of groundwater. Okay, so lakes, ponds, rivers, water vapor in the atmosphere, all of that comprises only 0.4% of the water which is available. Okay, so here, when we consider water vapor in the atmosphere, you can imagine that it is in very less amount. But all the climatic actions, be it your rainfall, when we talk about, let's suppose, cyclones, any of those activities, right, tornadoes, all of them are created by the same water vapor. And it is oftentimes said that if, let's suppose, by some artificial measures or another, we were to condense all that water vapor in the atmosphere. Let's suppose we convert all the water vapor into liquid water droplets. It will cover the surface only with a thickness of around 1 inch, not even more than that. So, water vapor, prime role is climatic influences. Climatic influences. Which climatic influences are we talking about? Rainfall, hailstorm, cloudburst, all of that. And then they also are a greenhouse gas. So they also help in warming, right? So they are also greenhouse gas. Then you have dust particles. Dust particles also have couple of roles. First of all, they form hygroscopic nuclei, which allows the water particles to stick on them. So hygroscopic nuclei, which helps in cloud formation. In cloud formation. And when it helps in cloud formation, basically, it will be helpful in the case of rainfall. And secondly, they scatter light. Light. When they scatter light, allows us to see even in the darkest of the nights. Okay, so that is where it will allows visibility visibility at night by diffused light. Okay, so that is the role that the dust particle actually plays. So it is important for you to understand and know the contribution made by each and every aspect of this components or constituents of the atmosphere as well. Then there is another aspect where questions can be asked, and that is the case of the lapse rate. What is lapse rate? Lapse rate is the variation in temperature of the atmosphere as you move higher up in the altitude. Okay, so that is your lapse rate. So as you move higher up into the atmosphere, that is where the temperature ends up varying. Now, lapse rate is of three different types. You have positive lapse rate, negative lapse rate, and you also have what is your zero lapse rate. Now, what do they indicate? Positive lapse rate means reduction of temperature with height. Reduction of temperature with height. Okay, so as you move higher up into the atmosphere, the temperature tends to reduce. That is what is known as a positive lapse rate. It is observed in different layers. Troposphere, for example, mesosphere, you will experience positive lapse rate. Then you have the case of negative lapse rate. In this, temperature increases with height. Increases with height. So that is basically what you observe in the case of let's suppose a temperature inversion condition during winters, or in stratosphere. That is where you experience a negative lapse rate. And then you have zero lapse rate. That is no change in temperature. No change in temperature with change in altitude. So these are the three different types of lapse rate. Now in troposphere, you experience what is referred to as a positive lapse rate. Okay. Now here, what is this positive lapse rate in troposphere and why does it occur? So that means as you move higher up within the troposphere, the temperature reduces. Now, why is it that the temperature reduces as you move higher up in the troposphere? There are a few reasons associated with that. The first reason, as you move higher up in the troposphere, the density of gases reduce. That means the density of particles in general that starts to get lower. So when you have lesser particles at a greater height, means there is less retention of heat, right? So that is where retention, so reduced particles with height means lesser retention of heat. Lesser retention of heat. Greater number of particles, greater retention of heat. Lesser number of particles, lesser retention of heat. Then after that, you also have the case where the heating of the atmosphere happens from the ground surface. The ground surface is the source of heating, right? So as you move away from the source of heat, temperature decreases. So ground surface is the source of heat. Okay? Is the source of heat. Hence, as you move higher up, so the heating reduces and basically it becomes cooler. So this is the reason why you have a positive lapse rate which is experienced in the region of troposphere in general. Troposphere in general. Okay. Now, otherwise in stratosphere, you have the case of negative lapse rate because of the presence of ozone layer. Now, then you have another process in the atmosphere, that is the case of adiabatic process. Adiabatic process is the process of heating or cooling of the air without any source of heat, that is the ground surface or sun. The heating and the cooling primarily and in totality occurs only because of the change in volume. So let's suppose if you consider any air parcel, large sized air parcel, if it is compressed, that means the particles get closer to each other. And when the particles get closer to each other, more molecular collisions will happen. Every collision will produce some amount of heat, right? So compression ends up generating heat and expansion ends up reducing the amount of collisions, hence reducing the amount of heat. So this is where heating and cooling of the air, heating and cooling occurs only because of change in volume. Okay? Occurs only due to change in volume. Right? So, compression leads to heating always because there will be greater amount of collisions. Compression will lead to heating. And then expansion will lead to cooling. Will always lead to cooling. Now, where is this applicable, by the way? So, for example, let's suppose you consider a mountain system anywhere, Rockies or Himalayas for that matter. Now, in that particular case, when you have winds which are coming in, now these winds, they will get uplifted through the mountains. Now, as they go higher up in altitude, there is less density of air. So that is when the air can expand, right? So here, expansion of air takes place. Now, this expansion of air will lead to what? Cooling, right? And that can lead to condensation leading to cloud formation and rainfall, right? So that is where the side of the mountain which faces the wind, this is your windward side, the side of the mountain which faces the wind. Now that side will always experience occurrence of rains. Okay. After this, the air is naturally dry because all the moisture has been depleted in rainfall. And then as the air moves down, it is moving into the region of greater air density. Closer to the sea level, air density is always high. So as it moves to the region of greater air density, that is where compression occurs. And that compression leads to heating and warmer air, lack of rains. Lack of rains. That is why northern slope of Himalayas, northern slope of Alps, eastern slope of Western Ghats, all of these, they are generally dry. Okay, so this is where you have warm, dry winds, right? Dry winds. This is also known as the rain shadow zone or the leeward side. Leeward side, which is associated with the lack of rainfall. So this is your rain shadow zone. Okay. Now it is here when we talk about winds, like for example, you have in the case of the Rockies, you have a wind system which develops like this, that is known as Chinook, the local wind of similar phenomena. In the case of Alps, you have a similar phenomena, and the wind system that is generated is Fohn. Okay, so that is basically the kind of wind systems, the local winds that you will come across. Now, then we come across the structure of the atmosphere. Now, in the atmosphere, the density of the air particles that keeps on reducing as you move higher up. Ideally, the extent of the atmosphere is said to extend for thousands of kilometers above the surface, but obviously of very low density air. It is not something which can be considered to be breathable or considered to be habitable as well. Now, even for that matter, if you go beyond a height of 100 or 150 kilometers, that is where the proportion of nitrogen, oxygen, all of them, that also starts to change. Okay, so here, up till the region of mesosphere, up till the region of mesosphere, that is mesopause, the mixture or the proportion of nitrogen, oxygen, argon, carbon dioxide, that is still maintained. So this is what is also referred to as your homosphere. Homosphere, right? And beyond that, you can have pockets of nitrogen, pockets of oxygen, pockets where both of them are mixed together. And that is where beyond this, you have the case of heterosphere. Heterosphere. Okay, that is heterogeneous distribution of gases are to be found. Now, in this, all of these, basically you will observe that, for example, troposphere. Now, troposphere and stratosphere, they are separated by what is known as tropopause. So tropopause, stratopause and mesopause, all of them are indicator of zero lapse rate. All of these are indicator of zero lapse rate. Okay, they are indicator of zero lapse rate. Okay, now beyond the region of mesosphere, you will come across a series of charged particles. Now these charged particles, basically when they interact with the solar rays, they develop a greater amount of charge and they help in radio communication as well. So that is where you will find within the thermosphere a layer that is also referred to as ionosphere. Ionosphere. That is beyond the region of mesosphere, you will find the presence of ionosphere. Now, why you have zero lapse rate in all these areas? That is a good question. Because think about it, in troposphere, as you move higher up, so imagine with the help of this image, let's assume you consider this to be the ground surface, you consider this to be troposphere, and beyond that, you have stratosphere. Now, stratosphere is hotter. Why? Because in stratosphere, you have the presence of ozone layer. It absorbs all the ultraviolet rays of the sun. So stratosphere is hotter. Top of troposphere is very cold, around minus 60, minus 80 degrees Celsius. So you have heat from above and cold conditions from below. So that is why temperature does not change when you consider the region of tropopause. Okay. Temperature doesn't change in the region of tropopause. Similarly, when you talk about the stratopause, so stratosphere is hot, but mesosphere is cold. So again, heating and cooling maintains the temperature. So observe the case of the temperature changes also indicated by the red line here. So as you move up from the surface, in the troposphere, the temperature reduces. It can reach up to almost minus 60 degrees Celsius. Presence of ozone layer or ozonosphere in the stratosphere means that the temperature can then increase, reaching up till zero when you reach the stratopause. And then after that, again it reduces in the mesosphere, reaching almost minus 100 degrees Celsius by the time it crosses the mesopause. So that is why you will find this zero lapse rate which is prevalent in these areas. Now we come to some other aspects. By the way, in troposphere, the height of troposphere is different in different parts of the planet, right? Troposphere has got a greatest height in the region of equator, and the height reduces as one moves in the region of poles. Okay, and what is the reason behind that? So troposphere has got a greater height at the region of equator and reduced height at the region of poles. At the region of equator, the height can be around 16 to 18 kilometers. At the region of the poles, it can be around 8 kilometers. Why is it? There are three reasons associated. First of all, there is greater heating. Heating leads to expansion, right? Then at the region of equator, because you have heated air, the air starts to rise up vertically. As the air rises up vertically, there's a convection current which is generated. Upward portion of the convection current is present at the region of equator. So that is why you have the height which increases, convection current. Okay. Now, we have also seen that when we talk about the gravitational pull, gravitational pull is slightly lesser at equator and slightly higher at the region of the poles. So that also has an impact along with the centrifugal force. Planet Earth is a rotating object. It rotates on its axis continuously. So the centrifugal force acts in the outward direction, right? So that is basically where you will find that it extends outwards. So that is the case of this centrifugal force and force of gravity. Okay, both of them combined. So these are some of the reasons why at equator the height is greater. Now, after that, we know that the solar insolation, the solar energy which is received by the surface, per unit time. That is known as solar insolation. Now, solar insolation plays a greater role in the heating and cooling of the surface. Now, this solar insolation is not consistent across the planet Earth. It changes from one region to another and also changes from one season to another. There are these frequent changes which keep on happening. Now, what are the factors due to which the solar insolation experiences a change? First of all, angle of inclination of planet Earth. So, wherever you have direct rays of the sun, vertical rays of the sun, around the region of the lower latitude, around equator, greater amount of solar insolation is received. Revolution of Earth around the sun. So, as the planet moves around the region of the sun, at one point it is farthest away from the sun, and at one point it is closest, what is known as aphelion and perihelion. Right? So, during the condition of perihelion observed across around 4th of January, around 4th of January, that is when it is the closest, right? And aphelion around 4th of July, right? So that is when it is farthest away. So this also impacts the amount of insolation that you have. And the distance in these cases, at this point of time, distance is 147 million kilometers. At the 152 million kilometers. And this point of time, it is around 147 million kilometers. Okay, so that is the variation that you will observe. Then you have configuration of the land, that is the direction in which the land is facing, whether it is facing towards the sun or away from the sun. So the slope of the land, for example, in the tropics or beyond the tropics, you will find that the one which is facing the sun will always have a slightly warmer temperature as well. And then you have the factor of altitude. With increasing height, the amount of insolation increases. As you come closer to the sea level, insolation reduces. Okay? Increase in height, insolation increases. Insolation with increase in height. Okay? Because as you come closer to the sea level, the solar rays, they have to interact with lot of various different atmospheric particles, and that is when they end up losing the energy. Okay, so that is why as you are on the top of the mountain, insolation level is high. The amount of solar energy received at the top of the mountain is high. Temperature is low, but the insolation level is high. Why? The temperature is low in that case, despite high amount of solar energy. Why is it that at the top of the mountain, the temperature is low? That is because at the top of the mountain, the air is rarefied. The particles are very far away from each other, less density of air particles. Less density of air particles mean lesser retention of heat. So that is the case of the factor of altitude. Okay. Then you come across what is known as albedo. Albedo is what? The reflective quotient of any particular surface, property of the surface which absorbs or reflects solar rays. Okay, so albedo is the reflective feature of the surface. Of the surface. Okay, so for example, in any kind of surface, let's suppose any kind of surface, if it receives 100 units of solar rays, right? How much is reflected and how much is absorbed? That will be determined by the nature, the color of the surface. For example, in the case of the snow-clad mountains, almost 85% of it will be reflected. In the case of the swamp or darker surface, almost 80-90% will be absorbed, only 10% will be reflected. So let's suppose you consider Snow. In snow, 85% is reflected and 15% is absorbed. Right? So albedo will be 0.85. In this case will be 0.85. Albedo varies between 0 to 1. Between 0 to 1. 0 indicating no reflection, complete absorption. Reflection, complete absorption. Okay? And 1 indicates no absorption, complete reflection. Okay? So that is the case of albedo. Now it will indicate the temperature variation also. If albedo is high, that means that surface is absorbing less. So temperature will be low. Okay. So always consider if albedo is high, means reflection is more. Reflection is more. That means less heat retained. So surface is cooler, retained. So you have cooler surface. Okay. If let's suppose albedo is low, for example, black tarred roof, etc. Whenever albedo is low, that means hotter surface. That is why in urban areas, generally the temperature is higher because you have so much of concrete, asphalt, etc. That is something which absorbs greater amount of heat and the temperature increases. This is what is also referred to as the phenomena of an urban heat island. Okay, so that is what you have as urban heat island. Now, after this, albedo also is impacting polar melting, or what is causing increased rate of heating of the poles, that we refer to as Arctic amplification. Amplification. Okay. Now, how that is happening is when you consider the thicker ice will reflect greater amount of solar rays, will absorb very little. But when you consider thin ice or water, it will absorb greater amount of solar rays, isn't it? Now, what it initiates a kind of a self-feedback cycle. So, due to global warming leads to melting of ice. Now, this melting of ice basically means that you have albedo reduces, which means greater heat absorbed. Now, when you have greater amount of heat absorbed, that basically means temperature increases. And when the temperature increases, again it will fuel further melting of ice. So it is a self-feedback cycle which the Arctic is prone to, due to which the Arctic is experiencing increased rate of melting as compared to ever before. That is the case of Arctic amplification. That is, the region of Arctic is warming almost around twice the rate of rest of the world. That is your Arctic amplification. Then land and water, they don't get heated at the same rate. Land always gets heated at a faster rate and loses heat at a faster rate as well. Okay, so when you consider a region of land and ocean, let's suppose, okay, now when you have the solar rays which fall here, now in the case of land, all the heat is restricted to the surface of the land itself. The light of the sun and the energy of the sun cannot penetrate into the depth of the land. It is restricted to the surface. Whereas in the case of the oceans, it sometimes, or in most of the cases, it percolates, penetrates. So the time taken for the temperature to increase over the land is much slower. Temperature will increase almost immediately over the land areas. Whereas for the water body, it will take a longer period of time to experience a rise in temperature. So that is why land gains heat at a much faster pace. And during night time, when the land has to lose heat, terrestrial radiation, all the heat is restricted to the surface. Whereas in the case of the water, the heat is very well distributed through the interior also. So, water will take more time to lose heat. Land will lose heat almost immediately. So, we can say that land gains and loses heat at a faster rate as compared to the oceans. Now, what is the impact overall? Now, during day, you will observe that land is much warmer. Temperature of the land is higher. Whereas during night, land gets colder because it loses heat faster. Now, this is something which accumulates over the seasonal cycle as well. That is why during summer, land has accumulated heat, heated up very quickly. So, that is why during summer, land is experienced to be warmer. Whereas during winter, land is losing heat on a daily basis very fast. So, during winters, land is colder. Okay, it is this behavior which drives the land and the sea breeze, and also the behavior of the isotherms, the bending of the isotherms that you witness in various different areas. By the way, when is it that you will find a greater difference of temperature between land and oceans? During summer or during winter? When is it that you will generally find a greater difference of temperature between land and oceans? It is always going to be during winter months. Because during winter months, the land gets very and excessively cold, whereas the water is comparatively warmer. Okay, so this is again a PYQ that we are going to discuss. Now, when we consider the isotherms and the overall impact of heating and cooling and the change of the isotherms, so understand this. Here you can see the temperature or the thermal image during the month of July. July is when you have summer in the northern hemisphere and winter in the southern hemisphere. So you will observe that in the southern hemisphere, by the way, the temperature change is quite uniform, almost parallel to the latitude. That is owing to the dominance of oceans. Southern hemisphere is also known as the oceanic hemisphere. So you have the dominance of the oceans. And observe the northern hemisphere and the thermal image thereby. In the northern hemisphere, you will observe that the land areas, they are more heated up, and the water in the region is comparatively cooler, because during summer the land is hotter. So if I have to draw an isotherm, isotherm is what? Isotherm is basically the line, imaginary line joining places of equal temperature. So when you consider an isotherm, iso means similar, therm means temperature. So imaginary line joining places of same temperature, of same temperature, isn't it? Now observe the line, red line that we have drawn here. Now in this you will observe what? That as it moves from continents to oceans, it bends equatorwards. Why? Because the oceans at the same latitude, they are colder. So if you want to experience the same temperature, let's suppose the temperature here, whatever it is, if you want to experience that temperature, you want to go closer to the equator, right? Observe the isothermal map during the month of July. Now, this is the isothermal map during the month of July. So here you observe the 10 degrees Celsius isothermia. 10 degrees Celsius isotherm. Now it bends equatorwards as you come closer to the region of the ocean, right? So during summer, isotherms during summer, can I say that as land is much hotter as compared to oceans at the same latitude, compared to oceans in the same latitude. That means in order to experience that temperature of 10 degrees, you have to come to lower latitude. You have to come closer to the region of the equator. Okay. So here isotherms. So while crossing from continents to oceans, bend equatorwards, and vice versa. That is, while they move from ocean to continent, they will move polewards. Now observe the case of January. In the case of January, you will observe that basically you have colder conditions over land, right? Warmer conditions over the water. Why? Because during winters, land gets much colder as compared to water body. Water body is comparatively warmer, isn't it? Water body is comparatively warmer and land is much colder. So here, if you observe the isotherms, observe this minus 12.5 degrees Celsius isotherm, right? So let's imagine we consider any particular latitude. Now, in this latitude, if I am at this region A, if I am at this region B, now at A, I will be experiencing a temperature of how much? Minus 25 degrees Celsius, isn't it? Because the minus 25 degrees Celsius isotherm is passing over here, right? But in the same latitude over ocean, I am experiencing 0 degrees Celsius, much higher temperature. So if I have to experience minus 25 degrees Celsius over the ocean, in which direction do I go? Do I go towards equator or do I go towards poles? I will go towards the region of the poles. I will go towards the region of the poles. So that is why in the case of winter, the class will continue till we finish the portion of physical geography. Okay. As long as you guys are able to take this, we will continue the session till we finish. Oceanography, we will just do the ocean currents and tides, and then we will be completing the entirety of climatology. Okay. Let this be the only session for physical geography that you have to attend, because there will be so many different videos that will flood the market, that will flood the YouTube from now till the exams. You will be confused what to follow, what not to follow. Okay. So this should be the only session that you uh, attend for the entirety of physical geography, and the important areas for your prelims that should be covered. Okay, we are not covering rest of the portions which are not very important for prelims. Only those portions we are targeting which are very, very relevant for your prelims. Okay, I will give the breaks in between as well, so that you are able to keep the momentum up. So, for example, in another 45 minutes, I'll give you another 10 marks, 10 minutes of break. Okay. So, here, in the case of isotherms and the behavior of isotherms, what we can say is that it will bend while crossing from continents to oceans, from continents to oceans, they bend polewards. polewards. Why? Because continents are much colder, and to experience the similar amount of low temperature, you need to go closer to the poles in the oceans. Okay, so this isothermal behavior, I hope that is understood, right? Yes, that is correct. Now, after this, we basically move to the condition of temperature inversion. Now, under normal condition, what do we experience? Normal condition. So whenever you have normal condition, in the troposphere closest to the ground surface, you experience a case of a positive lapse rate, isn't it? You experience a case of a positive lapse rate. Let's suppose this is your troposphere. So here you have a positive lapse rate. That means the temperature reduces by almost 6.5 degrees Celsius with every increase in kilometer, right? 6.5 degrees Celsius on an average per kilometer. Is it fixed, by the way? Is it the case that it is fixed that it will be 6.5 degrees Celsius? No. That lapse rate is dependent on moisture content as well. If the air is humid, the lapse rate will be less, around 5 degrees Celsius per kilometer. If the air is dry, then the lapse rate will be around 10 degrees Celsius per kilometer. So it tends to vary. It is not going to be consistent. Please keep in mind, lapse rate is much higher when you consider dry air. Okay? Now, that means closer to the surface, you have warm air, and above, you have the presence of cold air. Isn't it? Warm air and cold air. Now, warm air has got a tendency to rise up, and cold air has got a tendency to sink. So that is where you have vertical mixing of air. Mixing of air. But due to certain circumstances, sometimes we experience a condition of negative lapse rate, whereby you have cold air at the bottom and warmer air above that. Cooler air at the bottom and warmer air above that. So whenever you achieve or observe this kind of a condition, cold air being heavier has a tendency to stay down. Warmer air being lighter has a tendency to stay up. So in this case, you have no mixing of air. Negative lapse rate is observed. Negative lapse rate and no mixing of air. Vertical mixing of air. When you don't have any vertical mixing of air, that is when pollutants stay in the same place for a longer duration and so on. This is what is referred to as a stable air condition. Condition of stable air. Okay, so that is the case of temperature inversion. Now, the types of temperature inversion. Depending upon why that inversion has happened, you have the different types of temperature inversion. Okay. So you have what is known as surface inversion because the surface cools down sufficiently and substantially. That is where you have surface inversion. Then after that, this is something which is experienced in India. Then you have the upper air inversion. Upper air inversion is of two types. Upper air inversion is thermal and it is mechanical as well. Thermal means when we talk about, let's suppose, the region of troposphere to stratosphere. Sphere to stratosphere. There is a negative lapse rate because stratosphere is warmer. And because there is a negative lapse rate, that is why you won't have air from troposphere actually entering into stratosphere because you have stable conditions in that area. Then mechanical, This is your subsidence inversion. Subsidence of air, sinking air in a particular region, that leads to adiabatic compression and warmer air is created. Then you have what is known as frontal inversion. In the case of the formation of fronts, that is frontal inversion. It is observed in mid-latitude regions where you have the mixing of the cold polar air with the warm tropical air. This is also observed in mid-latitude regions during winter latitude regions. Okay, and then you have what is known as valley inversion, especially during night time, when you have cold air from the mountain top that basically sinks into the valley bottom and uplifting the warm air above. That is the case of valley inversion. So these are your different types of temperature inversion that you come across. Surface inversion, created because the surface cools down all of a sudden. Now, as the surface cools down during winter months, so the surface cools down all of a sudden, the air in contact with the surface also cools down substantially. And that is why inversion occurs. So, for example, let's suppose at 5 p.m., if the temperature of the ground surface is 12 degrees Celsius, the air in contact will also be 12 degrees Celsius. Air above, let's suppose, is 7 degrees Celsius, above, let's suppose, 2 degrees Celsius. Now, at 3 a.m. in the morning, the ground temperature will be, let's suppose, 1 degree Celsius. Air in contact will also have 1 degree Celsius. But the air parcel here, it will not cool down to the same rate because it is not in contact with the surface, isn't it? So that is why it temperature will reduce. Maybe it will reduce to 4 degrees Celsius or 5 degrees Celsius, right? And then higher up that you go, so maybe 0 degrees Celsius or -1. So here you observe the case of a negative lapse rate observed in India, particularly during the winter months. That is the condition of a negative lapse rate. Then upper air and subsidence inversion, that is when you have a sinking air. This is what is known as mechanical inversion. Mechanical inversion. So let's suppose in a particular region, if you consider the ground surface mid-latitude during winter nights and winters in general. So ground temperature is low, very low temperature, isn't it? Now let's suppose there is anticyclonic condition created somewhere like this. That is, you have sinking air. Now when you have that sinking air, it will get adiabatically compressed. It is moving into the region of high air density. So it will undergo compression and it will get warmer. Adiabatic compression, and it will get warmer. So that is where the ground surface, because it is very cold in mid latitudes and you have a sinking air, so that is why it is something which causes again a case of negative lapse rate. Okay. So surface inversion is clear and mechanical inversion also, I hope, is clear. Surface inversion, again to repeat, caused why? Because of sudden cooling of the ground surface during the night. It is the night time. For example, in Delhi, in Chandigarh, what do you observe? Night time, 3 a.m., 4 a.m., the temperature of the ground basically becomes 1 degree Celsius, 2 degrees Celsius, isn't it? All the loss of heat happens by terrestrial radiation. So suddenly the temperature drops in the afternoon when the sunlight is available, 14 degree, 15 degrees Celsius. In these dry areas, the daily variation of temperature is also very high. So as a result of that, the ground becomes cold at night. When the ground becomes cold at night, so obviously the air in contact with it will also become cold at night, right? So that is the case of this surface inversion, and this is something which is experienced In the polar areas throughout the year, because the surface in the poles is very cold. Okay, experienced in polar areas. Prerak, is it understood now? Polar areas throughout the year. Okay. Now, that is the case of this surface inversion. Mechanical inversion, where you have the sinking air in a particular area getting heated up, you have the adiabatic compression. Now, adiabatic compression will warm up that air and automatically it will have a higher temperature, right? So, that is the mechanical inversion. Frontal inversion, in whichever region you have the cold air mass and the warm air mass which interact, that is the formation of a front. Let's suppose you have cold air and you have the condition of warm air. Now, what happens in this? Warm air will climb over the cold air, isn't it? So, in these areas, you basically have again got an inversion condition. Warmer air is above, colder air is below. So, that is the case of the frontal inversion. Observed again where? In the region of mid latitudes. Mid latitudes. Okay, that is the frontal inversion. Most common during winters in mid latitude. Then you have valley inversion. What is valley inversion? So during nights, when you consider, let's suppose, a valley and a mountain system. Now, during night, the air above the mountain will be cold, right? And valley will be comparatively warmer because heat will be retained closer to the sea level because of higher density of the particles. Higher density of particles mean that greater amount of heat will be retained. Now, cold air is heavier and warm air is lighter. So, this cold air begins to sink. And as it sinks, it simply uplifts the region of warm air. This warm air is lifted and you have cold air at the bottom. Okay, so that creates a kind of an inversion, which can also sometimes create fog like condition. That is what is valley inversion. However, if the valleys are not very narrow and if they have open ends, that allows for air movement to happen, what we refer to as air drainage. In that particular case, valley inversion does not occur. But otherwise, if you have narrow valleys, always prone to valley inversion. Okay, let's take a look at some of the PYQs. Normally, the temperature decreases with increase in height from the Earth's surface. We will discuss anabatic and katabatic as well. Don't worry. Normally, the temperature decreases with the increase in height from the Earth's surface because atmosphere can be heated upwards only from the Earth's surface. There is more moisture in the upper atmosphere. The air is less dense in the upper atmosphere. What is the correct answer? This is a direct question associated with lapse rate. So in this first statement, that is atmosphere can be heated upwards from the Earth's surface. This is the correct statement. Second, there is more moisture in the upper atmosphere. That is incorrect. Moisture level is highest closer to the surface. As you move higher up, the moisture level reduces. Third, the air is less dense in the upper atmosphere, means less retention of heat. This is also correct. So the correct answer is C, that is 1 and 3. Okay. Now, which of the following is or are the correct inferences from isothermal maps of the month of January? Isotherms deviate to the north over the ocean and to the south over the continents. Presence of cold ocean currents, Gulf Stream, North Atlantic drift make the North Atlantic Ocean colder and the isotherms bend towards north. So here, which of them are correct? So in this, the first statement, isotherms deviate to the north, that is polewards over the ocean, and to the south over the continents. This is a correct statement, isn't it? Now, Presence of cold ocean currents, that is Gulf Stream and North Atlantic drift. First of all, these are warm currents, these are not cold currents. Let's suppose we didn't know about whether they are warm currents or cold currents. Then what? Then here, that makes the North Atlantic Ocean colder and hence the isotherms bend towards the north. Right? No. That is where you have the North Atlantic Ocean, which is warmer. That is why the isotherms bend towards the north. Had the North Atlantic Ocean been colder, then the isotherms would have bended to the south. So this is incorrect. Correct answer is A. That is one only. Okay. Now, which of the, again, this question was repeated. So we have discussed this. Right. Take a look at this question. Temperature contrast between continents and oceans is greater during summer than in winter. The specific heat of water is more than that of the land surface. Which of the following is correct with respect to the above statements? First statement, continent is also moving. No, it is mentioned in the first statement that over the oceans it is moving north. It is over the continents it is moving north, over the oceans it is moving south. Yes, that is why the first statement is correct. Now, in this case, statement 1 and statement 2, temperature contrast between the continents and oceans is greater during the summer as compared to winter. That is incorrect. Contrast is always greater during winter. So once you know that first statement is incorrect, you have only one option, that is option D. That is, statement 2 is correct and statement 1 is incorrect. Then we come to the case of air circulation. Now, when we talk about winds in general, now winds across the world are driven by certain factors, right? So you have the pressure gradient force, the frictional force, Coriolis force, and the force of gravity, the gravitational force. These are the forces which determine the speed and the direction of the wind. Pressure gradient force is very important. It always ends up initiating the wind movement. Initiates the wind movement. Okay. Now, wind speed is proportional, always proportional, and directly proportional to the pressure gradient force. What is this pressure gradient, by the way? Difference between high pressure and low pressure. That is the pressure gradient force. What is the difference between high pressure and low pressure? So, greater the pressure gradient force, greater is the wind speed, always. Okay, and that will initiate the wind movement. Frictional force experienced due to the obstruction on the ground, mountains, plateaus, hills, trees, houses, everything that reduces the wind speed. So it is a kind of force of resistance which reduces the wind speed. And then you have the Coriolis force. Coriolis force due to the rotation of planet Earth, right? Due to rotation of planet Earth. Rotation of planet Earth. Okay. So that is where you will find that basically Coriolis force bends the winds to the right in the northern hemisphere and bends the winds to the left in the southern hemisphere. Okay, very quickly let us go through this. So pressure gradient force, a region of high pressure to the low pressure, winds will always blow from a high to a low. So that is your pressure gradient force. Now, in a particular region, pressure gradient force and its intensity can always be demarcated with the placement of the isobars as well. Okay, so they can be indicated with the placement of isobars, right? So how? So if, let's suppose, you have the isobars which are very close to each other, that means the pressure is changing rapidly. If the isobars are very far away from each other, means the pressure is consistent and the pressure gradient force is less. Okay. So if isobars are very close to each other, are very close to each other. That means what? You have the pressure gradient force is high because the pressure is changing rapidly, and vice versa means the pressure gradient force is low. So that means this will mean wind speed is also high, also very, very high. Okay, so that is the case of pressure gradient force. Then Coriolis force, it deflects the winds to the right in the northern hemisphere and deflects the winds to the left in the southern hemisphere. It is maximum at the region of the poles, right? Because the entire Coriolis force, it acts because of the different speed of rotation of different parts of planet Earth. Now, the rotational speed at poles is 0. So that is why there will be maximum amount of Coriolis force bending. At the equator, Coriolis force bending is 0. Okay. Now, it is perpendicular to the pressure gradient force, always near the ground surface. So if you consider how, let's suppose high pressure in the northern hemisphere and low pressure. Direction of pressure gradient forces, this Coriolis force will try to bend the winds to the rightward direction. How does it bend the wind to the rightward direction? It will have the direction like this, and then the final wind will be moving like this. So that is why Coriolis force is perpendicular to the pressure gradient force. Okay, so that is the case of the Coriolis force. Why does it occur? Because of the different speed of rotation in different parts of planet Earth. Speed of rotation of planet Earth is highest at the equator and is 0 at the region of the poles. So as you move from one region to another, you are actually moving from one speed of rotation to another speed of rotation, and that is how you experience the deflection, right? And you end up reaching somewhere else. So winds experience this, ocean currents, they also experience this Coriolis force. So that is something that they experience. Then you have the frictional force. Frictional force is nothing but the force of resistance. Force of resistance. Okay. Which is offered by the ground surface, which is offered by the trees, the mountains, the plateaus, and so on. That is why frictional force is always very high on the ground surface and the speed of the wind is low. But as you move, speed is very low. Let's suppose you move to an altitude of 1 to 3 kilometers. Then you will find speed is very high. Okay, speed is very high. In fact, even above oceans, you will not find any such resistance. That is where again speed is of the wind is very, very high. All of this is impacted due to the frictional force, right? Now, this is what is expected or experienced in the southern hemisphere, which is dominated by oceans. That is why wind speed in the southern hemisphere is higher. Wind speed in the southern hemisphere is very high. Okay, primarily because of the fact that when you consider the dominance of the oceans, no frictional force to such an extent. Now, in this southern hemisphere, that is why what you consider westerlies in the northern hemisphere, in the southern hemisphere, they are known by the name of roaring 40s, furious 50s, and shrieking 60s. That is because of the loud sound that they create because of the high speed that they have over the oceans, right? So you have the case of roaring 40s, that is in the 40-degree latitude, then furious 50s or fiery 50s, and shrieking 60s. That is basically the name high-speed westerlies. High-speed westerlies. Okay. Now we come to the case of the tricellular model of atmospheric circulation. So basically, at the region of equator, at the region of 0 degree, you have intense amount of heating of the surface. Now, heating of the surface means that the air also gets heated up. When the air gets heated up, this air tends to rise. Okay, because when the air gets heated up, it tends to rise up, it becomes lighter. Why does it become lighter? Whenever an air parcel gets heated up, it gets so much amount of energy that all the particles, after getting energized, they leave the system. So the air parcel becomes lighter in comparison and it starts to rise up. It rises up, hits the region of tropopause and diverges. Now it diverges. Now, due to Coriolis force, the air cannot move beyond 30-35 degrees because there is so much of bending in the upper atmosphere that the air cannot move further northwards. So the air accumulates and then sinks, creating a dynamic high pressure in the region of 30 degrees, what is known as the subtropical high pressure zone. Okay, the subtropical high pressure zone. From here, one parcel goes towards the equator, the low pressure, another portion moves towards the polar region. Now, in the region of the pole, because of very cold condition, you have sinking air. And this cold air comes and meets with this warm air from the tropics. They converge, they rise up, creating a dynamic low pressure. And that is when eventually they will create a tricellular model of circulation. So, this is the tricellular model because they have three cells. Right. Now, Hadley cell, that is the one at the lower latitude. Now, this Hadley cell is created why? Because of the increased heating at equator and the rise of air at the equator. So, this is what is also known as the thermal low pressure cell, which is driven by the thermal low pressure created at equatorial low. This is also where at the region of equator, this is also known as the thermal equator. Thermal equator. Now at this region, you have winds coming from tropics in both the hemispheres and then rising up. That is why this region is also referred to as the Intertropical Convergence Zone or ITCZ, because you have winds coming from both the tropics meeting and then rising up. Then here you have the case of a high pressure in the region of poles created due to very cold conditions and sinking air. So this is again a case of the polar high, and this is a thermal high pressure cell. High pressure cell. Ferrel cell, however, is created purely because of dynamic conditions. So this is a dynamic pressure cell. Pressure cell. Okay. Now this 30-degree north latitude or this 30-degree high pressure, subtropical high as it is known as, it is also known as horse latitudes. Horse latitudes. Okay. It is a dynamic high pressure which shifts north and south with various seasons. This is also, by the way, referred to as the doldrums. Okay. Then this is your subpolar low pressure. Polar low pressure. Now this horse latitude, because of sinking air, will never experience the cloud formation or rainfall. So this is where you have dry conditions. Dry conditions. That is why majority of the deserts across the world, they lie across this subtropical high pressure belt. majority of the deserts across the world, right? All of them, they lie across this subtropical high pressure belt. Okay. Now, these pressure zones, they shift north and south with the insolation change or with the change in the position of the sun. For example, in January, you observe that the low pressure equatorial trough or the equatorial low pressure or the ITCZ largely remains at equator, but observe over Australia it bends southwards, right? Now, you have the high pressure, subtropical high pressure. You have the Hawaiian high, you have the Azores high. Azores Island, which is situated close to Portugal. So that is Azores Island. So Azores High, Hawaiian High, then you have the Siberian High. These are the high pressures which are created during January. And then the subpolar low around Aleutian Islands, you have Aleutian low pressure. Around Iceland, you have what is known as the Icelandic low. These are your pressure systems. So if a question is asked that Aleutian low pressure is created due to what condition? Meeting of the polar air and the tropical air. Okay. Similarly, you will observe that during the northern summer, all of them, they bend north. The ITCZ bends north, and this is the prime driver of the monsoonal systems over India as well. Okay. Now we will come to the local winds. Before that, if you need a break, I can give you 15 minutes break and then we will be back. Okay. So do one thing, take 15 minutes break and then we will be back and we will then complete it. Okay, so now we talk about the local winds. Local winds, when it comes to prelims, is relevant in case you want to know the type of questions which can be framed. It can be match the following kind of a question, which can also be framed from this, where you can have a question about whether a wind is cold or warm, or also the region based local winds, which region is associated with which local wind. So here I have provided in the text also with the various local winds, so you can go ahead with the revision of that as well. Now local winds, they are basically temporary in nature. Unlike the permanent wind systems, they are temporary in nature, and these local winds, they also are seasonal in many of the cases. So when we classify these local winds, so this local wind is classified as the daily local winds, daily winds, which are observed on a daily basis. Okay, that is the case of the daily winds. For example, the land and sea breeze, and you also have the anabatic and the katabatic winds and katabatic winds. Okay, then you have some of the seasonal local winds, and when we consider the seasonal local winds, they can be, for example, chinook, that we have already seen, taken a look into, the winds moving in the leeward side of the Rockies. Then you also have the case of Fohn, Sirocco, Mistral, Lu. All of these are the seasonal local winds. Okay, so that is the basic classification of these local winds. Let us take a look at some of the daily local winds, for example, the land and the sea breeze. Now, there the winds come into existence primarily because of differential rate of heating and cooling of land and water. During the daytime, the land gets hotter. So during the daytime, the land develops a region of low pressure, whereas water body, which is comparatively cooler during the daytime, that develops a condition of high pressure. So you will observe that the wind movement is always going to be from high pressure to low pressure. So winds are originating from the sea and moving over to the land area. That is why during daytime, you will observe the development of a sea breeze. Whereas during night time, the condition reverts. Land loses heat very quickly, so land becomes colder, it becomes a region of high pressure. Water body comparatively is warmer, so water body develops a low pressure. So here you have the wind movement from land to the sea. So during night time, you will basically observe the case of the land breeze. Okay, so during daytime, sea breeze, and during nighttime, land breeze. It helps moderate the temperature over the coastal region. That is why in the coastal territory, you do not experience extremity of temperatures, right? You don't experience very hot climate or very cold climate in the coastal areas. Then, in the case of the mountains and the valleys, now here again, during daytime, what happens? That during daytime, the mountain tops, due to higher amount of insolation, they end up indicating the presence of low pressure. They end up indicating the presence of low pressure. Whereas valleys are comparatively cooler during daytime because of reduced amount of solar insolation. So these are the regions of high pressure. Okay, so the wind movement is observed from the region of low pressure to the high pressure. Now, these winds originate from the valleys and go to the mountain top. That is why they are known as valley breeze. Always, winds are named after their place or position of origin. That is the case of all these winds. During night time, so this is during daytime. Daytime, you have the valley breeze. During night time, the mountain tops get very cold. So here you have high pressure, and valley is comparatively warmer. So you have low pressure. So that is where during night you will experience the presence of mountain breeze. During nights. Okay, so this is the basic difference between the mountain breeze and the valley breeze that you experience. These are also known as the anabatic and the katabatic wind systems. Then you have the seasonal local winds, for example, Lu. During the summer season and the summer afternoon, you will generally find the wind movement coming from the western part of India, that is from the Thar Desert, even further from the region of Sistan, Balochistan area of Iran and Pakistan. You have these winds which move from west to east and they increase the temperature. These are warm advectional winds. Okay, so these are warm advectional winds which increases the temperature, and it always creates heat wave conditions in the northern part of the country and central part of the country. So it is hot and dry wind which blows very strongly over the northern plains of India and Pakistan during summer afternoon. It increases the temperature to 45 to 50 degrees Celsius and can also induce the presence of heat waves. These are very dry as well. Okay. Then you have Chinook. Chinook and Phone, they are very similar. Now, what happens is when you consider the Rockies which are present in North America, they have a western and the eastern slope. Now, across the eastern slope, that is, across the leeward side, as the wind subsides and moves closer to the foothill, that is when it experiences warming effect. Why? Because of adiabatic compression. Adiabatic compression. Okay. So that is why it experiences a kind of warming effect. And thereby, what it does, it starts melting the snow. Okay. So that is why Chinook is known as a snow eater, because it melts the snow. It is not as if it is as warm as a Lu. Temperature of this wind is around 5 to 10 degrees Celsius itself, but it is sufficient to melt the snow in this region. Okay. Now, similarly, in the case of Alps, also you have the northern slope of Alps. Now, there you have the local wind, which is known as Phone. Okay, so that is what is referred to as phone here. So when we consider phone, so in that particular case, you have the southern and the northern slope of Alps. Okay, you have the northern slope. Now, across the northern slope, particularly in the region around Switzerland, because if you consider Alps, some portion of Alps you will find in the region of Italy, some portion of Alps in the region of Switzerland, and in France as well. So, in the region of Switzerland, that is where across the northern slope you have a leeward wind movement, and that is what is referred to as phone. Okay. Now, what it does, it again creates a warmer condition where otherwise every other region is very, very cold. So it creates a kind of a warmer condition. And that is where it acts like a climatic oasis, a perfect climatic condition. Now, the prevention of snow in that also means that certain crops also benefit. So early sowing of wheat, ripening of grapes, and checking, and they don't allow frost formation during the autumnal months as well. So that is Phone, which is again warm and dry wind, just like Chinook. The only difference, Chinook is observed across the Rocky Mountains, whereas Phone is observed across the Alps. Okay, that is the basic difference. Then you have a cold local wind, which is experienced over Europe, Western Europe, particularly during the winter months, that is Mistral. Now, during the winter months, we have seen that the land gets very cold. Water is comparatively warmer. Now, because the land gets very cold, that is where you have development of high pressure. Water basically is very, very cold. And the land is very, very cold. It develops high pressure. And Mediterranean is comparatively warmer, so it creates a low pressure. So you have these local winds, cold winds, moving over the region of Spain and France. In the region of Spain and France. It reduces the temperature further in the region of Spain and France, and that is your Mistral. So, more common during winter season because of development of high pressure over Europe and low pressure over the Mediterranean. When we talk about the region of North America, Siberia, in Asia, and Eurasia, in all these areas, you don't have an east to west mountain range. So what happens is that the polar winds, they can come further south. Presently in the news stories also you would have seen the discussion and the mention about the polar vortex conditions which get created. So that is where, when you have these conditions in these higher areas or higher latitude areas of Canada, in the higher latitude areas of Siberia, you have the cold polar winds which are laden with snow particles, right? So they appear in a white powdery state and they basically carry these particles, reducing the temperature, lowering the visibility as well, and they are oftentimes disastrous. And that is what is known as blizzard. So these blizzards, they are known to claim multiple lives during the winter season as they blow across these Canadian and the Siberian region. So violent, stormy, cold and powdery wind with dry snow and prevalent in North and South Polar region, Siberia, Canada, and even in the region of US. Another local wind that originates from North Africa, that is Sirocco. So basically, from the region of North Africa, it picks up the red sand because that region is rich in iron. That is why you will find the presence of red sand. Then, as it moves over the region of Mediterranean, it picks up moisture also. So now this wind which has originated over North Africa, so if you consider North Africa, from here it has picked up red sand, then it moves over Mediterranean, that is where it picks up moisture, and then when it moves to the southern part of Italian coastline and French coastline, that is southern part of Europe, it will bring rainfall in that area. But the rainfall will have these red sand particles as well. And that is what is referred to as blood rain. Okay, so that is what is referred to as blood rain. So that is associated with the local wind, that is Sirocco. What is the nature of the wind? Warm, dry, and dusty. Similarly, you have a lot of these local winds across various parts of the world. What I advise you, take a look at the region and whether they are warm or cold. Here you will find in detail the mention of each and every local wind, which is classified as per the continents. So it is easier for you to cover all of them as well. But the major ones we have discussed, this is where you just need to look at the regions where they are to be observed and whether they are warm or cold winds. Okay. Now we come to the case of the humidity, clouds, and precipitation. Local winds end up on a daily basis and regenerate or are persistent throughout the season. Depends. If you consider land breeze and sea breeze or anabatic and katabatic winds, they are generated on a daily basis. But if you consider Lu, they will be present during the daytime, every day during the almost every other day during the summer season in the northern plains, right? So that is where they can get regenerated as well. Okay. Now, we come to the case of humidity and precipitation. When we consider humidity, humidity is what? Humidity is the amount of moisture content which is present in any air parcel. Total amount of moisture content, right? If you consider any air parcel, what is the moisture content in that air parcel? That is your humidity. Okay. Now, any particular air parcel will have a certain carrying capacity. That is the total limit or the total amount of moisture that it can carry, isn't it? So, this is where humidity is something which is determined by the local conditions as well. So, when we talk about, let's suppose, the various different particles in the air, it is in the gaps in between that you will have moisture or water vapor which is embedded, right? So, greater the space available, more moisture can be held. Now, if let's suppose I heat this air, that means what? More particle spaces will be available because the particles will run away. So that means more moisture can be accommodated. So that is where humidity is something which is the measure of the moisture content. Measure of moisture content. Okay. Now, furthermore, when we discuss about the case of the carrying capacity of the air, carrying capacity of the air means what? Total amount of moisture that the air can withstand or hold. Total moisture content that air can hold. Parcel can hold at any temperature. Okay. Now, carrying capacity is dependent on temperature. So, if let's suppose the temperature increases, that means more moisture can be accommodated in the air parcels because the particles will be further spaced apart. So carrying capacity increases with the increase of temperature, and carrying capacity will reduce if the temperature also tends to reduce. So always remember that in any air parcel, carrying capacity is directly proportional to the amount or the temperature which is experienced. Now, how do you measure the moisture content in an air parcel, by the way? There are multiple ways to do it. First is when you measure the weight of the water vapor in per volume of air, right? For example, if let's suppose the volume of this air is 1 meter cube, what is the weight of the air parcel? So, if the weight of the what weight of the water vapor? Weight of the water vapor, if let's suppose is 8 grams, then the moisture can be expressed in 8 gram per meter cube. So here what you are doing is you are measuring the weight of moisture per volume of air. That is what is known as absolute humidity. Okay, this is what is referred to as absolute humidity. In absolute humidity, you basically measure the weight of water vapor per unit volume of air parcel. Now, as you move from equator to the region of the poles, the temperature reduces. So, anyways, the carrying capacity will reduce. The air, when it gets very cold, will not be able to accommodate 8 grams. Maybe it will be able to accommodate only 2 grams. So, that is why we say that absolute humidity decreases as one moves from equator to the region of the poles. So, absolute humidity expressed in gram per meter cube. But then this is something which is very variable. With the rise in temperature, it changes because the volume can change and so on. So that is why the climatologists, they actually measure what is known as specific humidity. In specific humidity, what do? So you basically take 1 kg of air. 1 kg of air. Now, how do you consider 1 kg of air? The weight of the air molecules. That is what constitutes 1 kg of air. So in that 1 kg of air, what is the weight of the water vapor? Okay, let's assume the weight is 8 grams in 1 kg. So specific humidity will be 8 grams per kg, right? 1 kg is also 1000 grams. So 8 grams per 1000 grams. So that is something which is expressed 8 parts per 1000 also. That is also how you express specific humidity. It is unitless. Then you have what is referred to as relative humidity. What is relative humidity? So at any temperature, what is the overall capacity that the air has to carry moisture? And in comparison to that, what is the moisture that it is actually holding? That is relative, right? For example, take an analogy. Let's suppose you have a capacity to study 16 hours. You are studying 4 hours. So, as relative to your overall capacity, your overall efficiency is less, isn't it? Similarly, when we talk about relative humidity, that is, if at any particular temperature, what is the carrying capacity and what is the vapor present. So expressed in vapor present to the carrying capacity at any temperature to the carrying capacity, okay, into 100. That is something which will give you relative humidity. Now this relative humidity is also impacted by temperature. How? Let's suppose the temperature increases. If the temperature increases, the carrying capacity will also increase, isn't it? The carrying capacity will also increase. That means the value of relative, because if the denominator increases, the value of relative humidity will reduce. So we can say that relative humidity is inversely proportional to the temperature. Okay. Always, if the temperature lowers down or dips, relative humidity increases, and vice versa is also correct. Then we come to the case of the cloud formation. Now, cloud formation is associated with the process of condensation. The process of condensation. Okay. Now, why does the cloud formation take place? So let's suppose from the ground surface, due to evaporation or rising air, water vapor actually moves up. As the air rises up, it expands, it cools down, adiabatic expansion, right? Now, it will reach a point of saturation or carrying capacity. And if it rises further more, or if it cools down further more, what will happen? Condensation will start to happen. Condensation will start to happen. And this condensation, if it happens at a point lower than freezing point, it will be in the form of ice particles. If it is at a temperature higher than freezing point, in the form of liquid droplets. And that is what leads to cloud formation. Okay. Eventually, these ice particles, they become large, they become heavy, and then they start to fall. They start to drop. And that is what you experience in the form of raindrops. Because as these ice particles they start to fall, they experience some warming effect due to air friction. And that is where the ice particles they melt into liquid water droplets and you experience rainfall. However, in certain areas, you also experience snowfall. In India, you experience snowfall in the region of Jammu and Kashmir, Ladakh, Himachal Pradesh, Uttarakhand, Sikkim, parts of northern West Bengal, Arunachal Pradesh. These are the areas where you experience snowfall. Now, why do you experience snowfall? In those cases, ground temperature is less than zero, very low temperature. So as the ground temperature is below freezing point, air is also very cold. So in this case, let's suppose the ice particles, they start falling. They will melt into liquid water droplets. And then again, as they come in contact with the colder air, they will refreeze again. And as they refreeze again, you will experience snowfall. So you have refreezing of water droplets, water droplets. And why does that happen? Because of very low temperature on the ground surface. That is what you experience as snowfall. Okay. Now, these clouds are of various different categories. So, broadly, they are classified on the basis of the altitude. This is not frost, by the way. Frost is different. Snowfall is different. Frost is when you have the uh, presence or the dew formation on the ground surface, which is below freezing point. Then you don't have liquid dew formation, you have solid ice formation on the ground surface. So, when the air attached to the ground surface that reaches saturation below freezing point, then frost formation happens. Okay. Otherwise, if the saturation temperature of the air near the ground surface is reached at 10 degree 15 degrees, dew formation happens. Okay. So frost is nothing but the frozen dew. Now, the clouds are basically classified based upon their rain causing ability and also based upon their height. So the clouds with the greatest altitude, they are known as cirrus kind of clouds. Cirrus clouds. Okay. Now these cirrus clouds, they basically are feathery, wispy formations and they don't bring rainfall. Even if sometimes some condensation will happen, it will re-evaporate before reaching the ground surface itself. So it won't cause, not associated with rainfall at all. Now, if let's suppose the clouds are formed in accumulated format, vertical development is there, then it is known as cumulus. Okay, if you have horizontal development of the clouds, that is known as stratus. So at each level, you have cirrostratus, cirrocumulus. Then at mid altitude, you have altocumulus as well as altostratus. And at lower altitude, you have stratocumulus, stratus, and cumulus. What is stratocumulus? A mixture of both of them. So stratocumulus will be having horizontal extent and some vertical expansion as well. That is the case of stratocumulus. Okay. However, maximum rain is caused by the clouds which are of various layers, which span across multiple layers and are of great height. Those are associated with the term nimbus. So if they are accumulated with a vertical development, you have what is known as cumulonimbus. Cumulonimbus associated with darker clouds, very heavy rainfall, thunder, lightning events, and so on. However, if you basically have the layered formation stretching across large areas, that is what is nimbostratus. Light, moderate rainfall for a longer duration. All the clouds, they will reflect sunlight. All the clouds. If you consider the heat budget of planet Earth, 27% of the sunlight is reflected from top of the clouds because the clouds, they basically are whitish in appearance from above. Okay. In the case of cirrus, some amount of light is actually passed through in the case of cirrus. And that is why you will be able to observe beautiful rainbows and the yellowish tinge before sunrise and after sunset. That is because of refraction, which is caused in the minute droplets. Okay. Now, then you have some of the climatic events like cloudburst. What is a cloudburst? So cloudburst is when the clouds they become so unsustainably large that they are unable to withstand or withhold their own weight. So everything is dropped by the clouds almost immediately. That is a cloudburst. Now cloudbursts majorly across mountains and hills and hills. That is across the windward side. Now, what happens is if you consider a mountain or a hill, now there, moist winds as they are coming, they are pushed up, they cool down, and when they cool down, they carry out condensation. So, they will lead to the formation of clouds. More winds come in, so the clouds they grow larger. More winds come in, clouds get larger and larger. The clouds they keep on becoming unsustainably large. Let's suppose the wind movement stops even for a brief duration. Then all that cloud rains down and you have very intense and very heavy rainfall which is caused. So, Indian Meteorological Department talks about rainfall of 10 centimeter or more in 1 hour. Just to give you the context, annual average rainfall in India is roughly around 120 to 140 centimeter annual rainfall. So, if in 1 hour you have 10 centimeter or more of rainfall in a small area of 10 by 10 kilometers square, so that is considered to be a cloudburst. It can initiate landslides, other form of mass movement, flash floods, etc. It can occur over plain regions as well. In certain cases, in rare cases, they can also occur over plains. Rare cases over plains. And why is it so? Because of intense low pressure. Intense low pressure that creates violent updraft. Updraft is the upward movement of the wind. Updraft. And that makes the cloud unsustainably large. Okay? Now, then another such climatic factor is the case of hailstorm. Which cloud is responsible for Earth's cooling? It is comparatively the lower clouds. Lower level of clouds will be more responsible for Earth's cooling because they are of greater density. They will reflect greater amount of solar rays. High level clouds such as cirrus, they allow the solar rays to pass through, but they don't allow the terrestrial radiation to move through. That is why cirrus clouds are associated with the warming effect, whereas lower level clouds, that is cumulus, stratus, then nimbostratus, they are associated with reflection of solar rays itself in greater proportion, and they are associated with cooling impact. Okay. Now, I hope that is clear. Then you have a condition which is known as hailstorm. Now, hailstorm is what? Oftentimes, during summer afternoon, you would have experienced that very dense cloud cover is there, and along with strong winds and rainfall, you have large chunks of ice also which starts to fall. That is what is referred to as a hailstone, and the entire event is known as a hailstorm. So, hailstorms are created when you have certain conditions and criteria which are fulfilled. What are those criteria? First is intense low pressure. Intense low pressure which creates a violent updraft. Updraft. And then you also need cumulonimbus clouds. Nimbus clouds. Okay, that is when you experience hailstorms. So, for example, let's suppose you consider a very dense and thick cumulonimbus cloud cover. let's suppose. Now, in that particular case, when you have, let's suppose, a larger ice particle which starts to fall, okay, and it will eventually fall as rainfall. But then you have such strong updraft or vertical movement of the air because of intense low pressure, that this ice particle is further thrown back up. It refreezes and increases in its size. Refreezes and increases in size. Its size increases, it becomes heavier still, it starts to fall. Again, it is thrown up by the air movement. And that is when the size keeps on becoming larger and larger. It accumulates more materials and freezes. Eventually, the size becomes so large that now even the air cannot hold it together. And that is when they fall as hailstones. Okay, this is where you have the hailstones. So, these hailstones, they cause lot of damage in terms of crops, in terms of property, and also in terms of the population that you will find. Okay. If the winds are dry but they move up, then instead of cloud burst, they will cause tornado. Hurricane is different, tornado is different. Hurricane cannot be caused because of dry winds ever. Please understand that. Hurricane is a tropical cyclone. A tropical cyclone will be created only over the region of the oceans. We will study about tropical cyclones or revised tropical cyclones again. So that is where hurricanes will never be caused by dry air. Even in the case of tornado, you need the presence of moist air along with the presence of cold air mass. So that is where even tornadoes cannot be created. If dry air starts rising up, you won't have any cloud formation in that particular case. Okay, dry air will cool down. So that is where in dry air, it will reach, some moisture will be there, it will reach up till the level of cirrus, and then you will have cirrus formation. Okay, take a look at this particular PYQ. Which of the following statements is or are correct associated with the clouds? Cirrus clouds are composed of ice crystals. Cirrus clouds have a flat base and appear as rising domes. Cumulus clouds are white and thin and form a delicate patch and give fibrous and feathery appearance. Cumulus clouds are classified as high clouds. So, in this, the correct answer is going to be cirrus clouds are composed of ice crystals, right? Cirrus clouds have a flat base and appear as rising domes? No. Flat base and rising domes is associated with stratocumulus. Okay, stratocumulus. Then cumulus clouds are white and thin and form delicate patches and give feathery and wispy appearance. This is the case of cirrus, not cumulus. Cumulus clouds are classified as high clouds? No, they are low clouds. They are classified as low clouds. Okay? They are not classified as high clouds. Now, even when we talk about the case of rainfall, which is caused by these clouds, rainfall also is classified depending upon why it is caused or how it is caused. For example, in the region of equator, around the equatorial areas, you will experience that every day in the afternoon, due to evaporation, you have the formation of cumulonimbus cloud formation. So it is the rising air parcel which creates a convection cycle, and that is where you have everyday rainfall in the afternoon. So you have daily rains, afternoon rains associated with thunder and lightning. Associated with thunder and lightning. Okay, that is the case of the convectional rainfall, generally observed in the coastal areas, in equatorial regions, in maritime regions, in islands. That is where you will experience convectional rainfall, cumulonimbus clouds. Then you have orographic rainfall. We have discussed in the case of the mountains, when the winds come in and they rise up on the windward side, they will cool down, lead to the cloud formation, and that will cause rainfall. So, for example, the rainfall caused due to the Himalayan barriers and so on, that is what is orographic or relief rainfall. And then in the mid latitude areas, where you have the cold air and the warm air, right? Let's suppose when you consider warm air, as the warm air climbs up, it will condense here because of being in contact with the cold air. And this will cause rainfall. So this is known as the frontal rainfall, creation of rainfall or occurrence of rainfall due to formation of a front. That is known as frontal rainfall. Then this is where the condensation has happened at a greater height in the troposphere. When condensation happens near the ground surface itself, that is, when the air reaches saturation near the ground surface itself, that is when you come across the formation of fog or mist. Okay, so in this, the air cools down closer to the ground surface, and that is where it reaches saturation and undergoes condensation. Okay, so here basically in the case of frontal, depends on which kind of front, that is the what determines the type of clouds. We will cover it shortly. So here, fog is when the air near the ground surface cools down and basically undergoes condensation. That is fog. Now, its classification is dependent on how or why that air has cooled down. So, you have the classification as radiation fog, advection fog, upslope fog, steam fog, and valley fog. Right? So, when we consider the case of radiation fog, now, in this, just as is the case with the surface inversion. So, let's suppose you consider the ground surface. During the winter nights, the ground cools down quite substantially. As the ground cools down, the air also loses temperature. Air cools down and then condenses, undergoes condensation. Okay. So that is the case where you can say that radiation fog has been created. Okay. It is generally observed when? In long winter nights. Long winter nights where generally you don't have a lot of winds, that is when radiation fog is experienced. Early next morning, when the sun shines, the ground is heated up and then the air also heats up. So the radiation fog dissipates from ground upwards. Then you have what is known as the advection fog. That is, in regions where, let's suppose, you have a cold surface, okay, and you have warm air or warm wind which drains or moves into this area. This warm wind also cools down, and that is where fog formation occurs. That is the case of advection because you have horizontal movement of the wind which is leading to advection process. Then you have the upslope fog. As you consider the case of gradients, mountains, hills, etc., as the wind rises up ever so slowly, it undergoes cooling, and that is where fog formation happens in the upslope or the uphill region. That is the case of upslope fog. You have steam fog. This is one of the most unique and interesting kind of fog formation that you will come across. What is that steam fog? So let's suppose you consider a water body, sometimes even reservoirs and lakes in those also. So during morning, early morning, late at night and early morning, Which will be colder, land or water? Land is colder, isn't it? Land is colder. Water is comparatively warmer. Now, that means you will have cold winds coming from land to water. In the meanwhile, water is also experiencing evaporation, continued rates of evaporation. Okay. In the meanwhile, this cold wind coming from the land area that will interact with the water vapor, and the water vapor will condense where it is. Water vapor will condense after getting in touch or getting in contact with the cold wind. So this gives an appearance as rising steam, but in fact, it is the condensed water vapor. Condensed water vapor due to influence of cold winds. Okay? Of cold wind. And this is what is referred to as the case of steam fog. Right? So that is the case of the steam fog. And then you also have the valley fog. Valley fog, in the case of when you consider steam fog, can be experienced in winter months, sometimes in summer also, but in winter months also, right? Now, valley fog. So during nights, just like the valley inversion, during night. Now, when you have the cold wind from the mountain which starts to sink, right? The cold wind from the mountain which starts to sink into the valley bottom, the warm air is lifted upwards. Now, this warm air gets in contact with the cold air and the cold wind. And that is when condensation happens, which creates almost zero visibility in the valleys early in the morning and late at night. So that is the case of this valley fog. Okay. Now, this low pressure and high pressure in a region can create rising air parcel, can also create or influence sinking air parcel in an area. So that is where wherever you have rising air parcel, there you have the cyclonic conditions, and sinking air parcel, you have the anticyclonic conditions. Cyclonic conditions is created because of intense low pressure on the ground. Intense low pressure on the ground. Okay. When you have very intense low pressure on the ground, that means you will have the air which rises up. Air comes from all directions and it tends to simply rise up. Whereas when you have intense high pressure on the ground, you have sinking air. So, anticyclonic conditions are associated with clear sky and lack of rainfall. Lack of rains. Whereas cyclonic conditions, intense rainfall, stormy conditions, floods which can be caused, and so on. Now, whether it is cyclonic or anticyclonic condition, wind circulation varies. And that is determined by the Coriolis force. How? Let me give you an example. When we consider, let's suppose, northern hemisphere, and let's suppose we are considering cyclonic circulation. Cyclonic circulation. So in this case, you have intense low pressure on the ground surface. That means winds will be attracted from all different sides. But because we are in northern hemisphere, the winds will bend to the right, isn't it? So if you are an individual standing at the center of this low pressure, what is the direction of winds that you observe? You observe a wind motion, which is what? Anti-clockwise. So that is where you observe anti-clockwise circulation in the northern hemisphere during cyclones. But the same thing, if you consider southern hemisphere, again cyclones. Now in that particular case, if you have a low pressure, then winds are attracted from all different directions. Now these winds, they will be bending to the left. We are in the southern hemisphere. They will be bending to the left. So what is the circulation that you observe around the low pressure? It is clockwise. Okay, so that is why you will observe that cyclonic circulation in the northern hemisphere is associated with anti-clockwise, and in the southern hemisphere with clockwise circulation. And the exact opposite is also true when we talk about anticyclone conditions in the northern hemisphere. Simple logic of Coriolis force can be applied here. Now let's take a look at the cyclonic circulations, the type of cyclones. Now when we consider cyclones, cyclones are formed because of intense low pressure on the ground surface. That is how you have the formation and the presence of cyclones. Now they are of two types depending upon where they get created. If they get created in mid latitudes, they are temperate cyclones. If they get created within the tropics, they are your tropical cyclones. Okay. Now these temperate cyclones, they are created because of what? Dynamic pressure condition. That is frontal formation. Frontal formation. Dynamic low pressure. Low pressure. Whereas tropical cyclones, they are created due to intense heating. Intense heating. Right? So they are created due to thermal low pressure. Okay? Temperate cyclones, they influence a much larger area and they are present for a much larger duration as well. Tropical cyclones, they impact a comparatively small area for a smaller duration, but destruction caused is very high. The wind speed is very high in a tropical cyclone because of thermal low pressure conditions. Now, temperate cyclone, they are created due to the distortion of a front. Wherever you have a front and that gets distorted, that is when you have the temperate cyclones which get created. Okay, so here, that is why these are also what are referred to as frontal cyclones. Frontal cyclones. And because oftentimes when you talk about the fronts, so these fronts are created in a wavy pattern. So that is why also known as wave cyclones. Now, they will occur when? When you have a greater difference of temperature between the polar air and the warm tropical air. That is, when you consider the different fronts. So, more frontogenesis when it will occur, only then cyclones will be created. And in which season you have a greater temperature difference? Winter. So, that is why most common in winter. Common in winter. Okay. That is when they are very, very common in general, right? And then here, their movement is impacted by the permanent wind system. So when you are in mid latitude, that is when the permanent winds, they will carry it from west to east, right? So that is where you have the westerlies, impacted by westerlies, impacted by westerlies, and hence move from west to east. From west to east. Okay. Now, Here, this is the write up of the same aspect. Temperate cyclone experienced whenever frontogenesis is very common. They are known as extratropical cyclone, wave cyclone, or even a frontal depression. They are active above mid latitudes between 35 to 65-degree latitude in both the hemispheres, and direction of movement is from west to east, and more pronounced during the winter months when you will have greater frequency of frontogenesis. Now, how these temperate cyclones are created? Very quickly, if we take a look into it. So, initially, you have a frontal formation, a stationary front. A stationary front gets created. Now, in the case of the stationary front, you have cold air which is coming and warm air which is also coming. Now, if it stays like this itself, cold air does not move, warm air does not move, then cyclone formation will not occur. Frontolysis will occur. If let's suppose stationary front is present or existent in a region for let's suppose 21 days or 25 days, then mixing of air will happen and you will have frontolysis. But sometimes what happens is that cold air will enter into the region of the warm air and warm air will enter into the region of cold air. Distortion of the front starts to happen. Whenever the distortion of the front starts to happen, cold air tries to penetrate southward, warm air tries to penetrate northwards. We are talking about northern hemisphere here. Now, in the region where the cold air will penetrate, that is where you will have the formation of a cold front. This is where you have the formation of a cold front. Now, what happens when you have a cold front? In the case of a cold front, the cold air advances aggressively and the warm air is lifted up from the ground. And that is when the warm air will form, because there is a vertical rise, it will form cumulonimbus clouds. Cumulonimbus cloud formation. So, in the region of the cold front, you will have heavy rainfall along with thunder and lightning. That is associated with the region of the cold front. Heavy rainfall with thunder and lightning. Whereas on the other side, you observe that the warm air is progressing. That is where you have the warm front. Now, what happens in the case of the warm front? In the case of the warm front, you will observe that the cold air stays where it is, warm air comes and rises up. Now it is rising up in a very disciplined horizontal fashion. So that is where it will form stratus, nimbostratus kind of clouds. Stratus and nimbostratus. So continued moderate rainfall. But what you can associate in this entirety of the region is that air is rising. Even in cold front, air is rising. Even in warm front, air is rising. So that ends up creating intense low pressure on the ground surface, which attracts more cold air and more warm air. So that intensification process will lead to formation of that cyclonic circulation, where the air will rise up in a circular spiral pattern over the region of the low pressure. As you can observe, both across the warm and the cold front, the cold air starts covering the ground surface. And that is where you have the front which begins to close down. And that is the case of occlusion. So, this is where the cyclone begins to close down around the low pressure. Eventually, the entire front will close, and you will have the dissipation of the cyclone. That is, the occluded front will be created when on the ground surface you only have the presence of cold air. Okay, so now you know the type of clouds associated with the different frontal formation as well. Now, when we talk about tropical cyclone which impacts India. Now, tropical cyclone is created due to intense heating of the water body, right? Now, it is something which occurs in different parts of the world and is known by different names. For example, in Western Pacific, known by typhoons and South China Sea. Then Northern Australia, known by the name Willy Willies. Then in Indian Ocean, Bay of Bengal, etc. that is where it is known as cyclones. In the region around America, it is known by hurricanes. Now, these cyclones, they require certain pre-existing conditions to be fulfilled. Only then cyclone formation will occur. Otherwise, simply the air will rise up, lead to the formation of clouds and cause rainfall. But for the cyclonic circulation, what do you need? Large sea surface with temperature higher than 27 degrees Celsius. Large sea surface. So, why? Because you need moist air mass. Unless and until you don't have a moist air mass, you don't have condensation cycle which occurs. So, you need moist air mass. Then, presence of Coriolis force. Only then you have circulation. That is why tropical cyclones, they never get created at the region of equator, or neither will they cross equator, because at equator Coriolis force is zero. Small variation in the wind speed at the ground surface and higher up also, that means very low level of wind shear, and a pre-existing weak low pressure which can then intensify into a cyclone. Okay, so these are the necessary preconditions which need to be fulfilled. And what and how the process actually happens? You have the sea surface, intense low pressure attracts moist winds. Now these moist winds, they are also hot, and because they are in tropical region, they have come to the region which is heated. They start rising up in a spiral manner. As they rise up, they will condense along the spiral. And when they condense, they will be releasing what is known as the latent heat of condensation. So that latent heat of condensation will be released, which will raise the temperature. And this rising air parcel will ensure you have a sinking air here as well. You have the sinking air. Okay. And that is where the further sinking air will push the heat to the ground surface. It intensifies the low pressure. Intensifies the low pressure. Okay, so that is where it continues to intensify as long as it is over the water body. Now, this portion where you have the sinking air, you don't have a cloud formation. That is known as the eye of the cyclone. And the sides, they are known as the eye wall. Eye wall. And this is your eye of the cyclone in general. Okay. This is the case of a tropical cyclone. As long as a tropical cyclone stays over the water body, it gets much more intensified and much more stronger. Now, how do you name this tropical cyclone? So the process involves two organizations, that is RSMC, Regional Specialized Meteorological Center, and TCWC, Tropical Cyclone Warning Center. So Tropical Cyclone Warning Center, it basically observes any particular region which gets heated up, any particular water body which gets heated up. It alerts the respective RSMC, Regional Specialized Meteorological Center. So you have 6 RSMCs across the world. So you have RSMC New Delhi, which is situated in the Indian Meteorological Department office. You have RSMC Reunion for the Southern Indian Ocean, RSMC Nadi or Nandi, which is situated in Southern Pacific, RSMC Tokyo for South China Sea and Western Pacific, RSMC Honolulu for the region of the Eastern Pacific, and RSMC Miami associated with the hurricanes. Now, once the RSMC gets an alert that a cyclone is occurring, it picks a name from the list which is submitted by all the countries. So here you see in the Northern Indian Ocean, the 13 countries, each of them have submitted 13 names, and that name is arranged. For example, India has provided these names which are arranged in the row in front of that. One by one, the name is picked up. So, for example, you will observe that the name which is picked up is Detwa, the next Arnab, then the next will be Murasu, Akwan, like that one by one, the name is picked up, and then the cyclone is actually named. Okay, so this is the process of naming and the basic difference between the tropical and the temperate cyclone. Now, then we come across to some other concept associated with the atmospheric phenomena. That is the case of a Walker circulation. Now, what is a Walker circulation? Walker circulation is basically the east to west circulation which you experience across the region of the Pacific. So, when you consider the Pacific Ocean, let's suppose the equator. So, at that point of time, basically it experiences trade winds. Okay. Will latent heat never penetrate through the eye wall and then collapse? No. Latent heat is released when condensation will happen. Where is condensation happening? Across the eye wall. So that is why latent heat will be released in the eye itself, isn't it? Now, correct, Devendra. So latent heat is released inwards towards the eye, right? And bomb cyclone, sudden intensification of the cyclone where the pressure drops by more than 24 millibars within one day, sudden intensification of that low pressure, that is what is referred to as a bomb cyclone, mostly experienced with the case of temperate cyclones, sometimes with tropical as well, but mostly associated with temperate cyclones. Now, when we consider the region of equator, particularly the Pacific is very vast, very large. So here, what happens is that these trade winds, they will be carrying the surface water along with them as well. Surface water is the warmest layer of the water. Now that warm surface water will be accumulated somewhere in the western part of Pacific, right? You have the warm water which gets accumulated. In the meanwhile, due to upwelling, that is subsurface water which emerges up, you have the cold water which is present in the region of eastern Pacific. So that creates a temporary high pressure here, and you have the creation of low pressure here. So you have an east to west circulation in the region of the Western Pacific, that is Australia coastline, Indonesia, etc. You have the east to west circulation, which causes lot of rainfall. And here you have the case of sinking air. So that is what is known as the Walker cell or the Walker circulation, after the name of Gilbert Walker. So in this particular case, Australia coastline, Indonesia coastline will receive plenty of rainfall, whereas the Peruvian coastline will end up remaining dry because of high pressure condition. Okay, so this is the entire cycle. So trade winds blow from a general direction of east to west. Now the winds blowing over the vast Pacific, they gain a high speed because the frictional force is very low. Now they tend to drag the surface water along with them. Now the surface waters are warmer due to high solar insolation, and that is when warmer waters accumulate, creating a low pressure. So this is the circulation associated with Walker circulation. Now this Walker circulation can intensify over a period of time. How? So let's suppose you have these trade winds, they are moving from high pressure to low pressure. They will keep on carrying warm water on the surface. Eventually, the wind speed will also increase because more warm water, more cold water means the difference of pressure increases or the pressure gradient increases. So, as a result of that, you will experience that the winds get stronger and the entire Walker cell intensifies. So, observe here, you have the upwelling or the colder water spreading all across the region of Central Pacific as well. This is known as the cooling phase of the Pacific. Cooling phase of Pacific. And that is what is associated with the La Nina cycle. La Nina cycle is associated with higher amount of rainfall in India during monsoon. Okay, so that is the case of La Nina cycle. So this is where you have the trade winds which intensify, more warm water, more downwelling, and here you have more upwelling which is created. High pressure over Peru is intensified and low pressure over Australian coastline is also intensified. Now the reversal of this entire circulation is what is known as El Nino. Now why does it happen? So it is the trade winds which are supporting and accumulating the warm water. If the trade winds themselves weaken, right? So, weakening of trade winds, why does it happen, by the way? Weakening of trade winds, that occurs due to heating of the Pacific. Heating of Pacific. Now, when you have weakening of trade winds, means what? That the accumulated warm water flows back. Accumulated warm water flows back. Right? Now, when the accumulated warm water flows back, that means what? Warm water will come to Central and Eastern Pacific. Warm water comes to Eastern Pacific. Eastern Pacific. And that is where you will experience the formation or the creation of low pressure. Formation of low pressure. Okay. So here, what you are experiencing is that because the trade winds have weakened, the warm water accumulates here. Now, this is the region of low pressure. That means the winds will be coming towards this low pressure and then rising up. Right. Leading to cloud formation here. Rainfall across the Peruvian coastline, which was dry in other conditions. And now, as the winds are coming here, there is a kind of upwelling action and colder water which is pushed here. So a high pressure, comparative high pressure. So that means the Walker cell that we had seen, that completely gets reversed. And that is the condition of El Nino associated with dry conditions in India during the monsoon months. So basically, La Nina, intensification of Walker cell. El Nino is the reversal of Walker cell. Okay. During El Nino, Australia is very dry, experiences forest fires and bushfires. During La Nina, Australia is flooded, but during El Nino, it is very, very dry. As you can see, the warm water tends to flow back. Okay. Now, El Nino impacts the monsoons, causes reduced rainfall. However, in certain cases, the conditions of Indian Ocean dipole tends to dilute the impact of El Nino. Now, what is this Indian Ocean dipole, by the way? Indian Ocean dipole is the difference of temperature that you experience in the between the Somali coastline and the Indonesian coastline. That is the western coast of Indian Ocean and eastern coast of Indian Ocean. Okay. Continuous intensification of Walker will eventually lead to La Nina. Correct. What's the cause of strengthening or weakening of the trade winds? The trade winds, they are supported from what? From the subtropical high pressure belt, which is a dynamic high pressure. High pressure is created because of the sinking air. But let's suppose the water gets heated up. That means what? The air will try to rise up, but you have the sinking air creating the high pressure. Now, when the air starts to rise up, what will be the overall intensity of the subtropical high pressure? It will get diluted, it will cancel out each other. If there is no subtropical high pressure, will there be trade winds? No. Trade winds are actually provided by the subtropical high pressure systems. So that is where you won't have these trade winds experienced at all. So that is where the heating of the Pacific weakens or temporarily disrupts the trade wind system. Okay. Now, then here, when we talk about the Indian Ocean dipole is basically temperature difference between the eastern and the western extent of the Indian Ocean. That is Indian Ocean dipole. It is of three types. You have the case of positive, positive, neutral, and negative. Now, what is positive? In this, western part is slightly warmer. That is positive. It is good for Indian monsoon. For Indian monsoon. Okay. Then neutral, that is where you have low pressure or warming in the Indonesian coastline. Not good for Indian monsoon. Okay. Negative, intensification of neutral. Intensification of neutral. So that is positive, neutral, and negative. Negative is very bad for Indian monsoon. Indian monsoon. Okay. So that is the case of Indian Ocean dipole. It can counteract the impact of Enzo cycles or El Nino La Nina conditions as well. Okay. So under the neutral phase, you will observe that you have the warm water across the Indonesian coastline. So you have the low pressure which is created here. And this is different, by the way, from the Walker circulation. Okay. So here, lot of rains across Indonesia, Philippines, but sinking air in this region. So dry condition across the Arabian Sea and Somali coastline. Then negative phase, just like the Walker cycle intensifies into La Nina, here the neutral circulation intensifies into the negative phase of Indian Ocean dipole. The region of the low pressure further increases, more upwelling and high pressure in the region of Western Indian Ocean. Then the positive phase, absolute reversal. This is where you have warmer water in the region of Arabian Sea and the Somali coastline. Now, how this warmer water or colder water is created, by the way? The warmer water region is created because of intense heating. Okay, because of intense heating, solar insolation, lack of mixing of ocean currents, that is what creates this pool of warmer water. Indian Ocean dipole will impact the climate across Somalia also, Indonesia also, Australia also, as well as India also. Okay, it will impact all these areas. Then you have the moving circulation system, which is known as Madden-Julian oscillation. Now, this is the case of the moving high pressure and low pressure system across the region of the tropics, that is around equator and between Tropic of Cancer and Tropic of Capricorn. Now, this entire cycle of a low pressure, that is rising air, and then you have the sinking air as well. Okay, which creates the condition of high pressure. This entire cycle moves across the planet Earth. Wherever you have this low pressure, high rainfall. Wherever you have this high pressure, no rainfall. That is why Madden-Julian oscillation is said to have two phases. A phase of enhanced rainfall where you have low pressure, and then you have a phase of suppressed rainfall where you have sinking air, that is the case of high pressure. And this entire thing moves in a direction of west to east. The entire circulation continues to move from west to east. It completes the entire cycle of planet Earth in a duration of 45 to 60 days. Now, if let's suppose during monsoon season, the low pressure comes over India more frequently, more rainfall in India during monsoons. So, during monsoon, shorter cycle of MJO is beneficial for monsoonal rainfall. Then, one of the other important climatic factors is the jet stream. Jet streams are high altitude wind systems. These are also what are known as the geostrophic winds. Geostrophic winds, the ones which move parallel to the latitude. Move parallel to the latitude. Okay? That is geostrophic winds. These are high altitude wind systems which move at a speed of 250 to sometimes even 350 kilometer per hour at an elevation close to the region of tropopause, but they can also dip to the level around 6 kilometers or 7 kilometers from the ground surface. So that is the case of these jet streams. Now, where are they created? They are formed or created in those areas where you have difference of temperature in the air parcel at an altitude. So they are created in the region at around subpolar low, that is where you have the polar jet stream, and you have the subtropical jet stream. So you basically have two jet streams in each hemispheres, right? So you have four primary and permanent jet streams. They also move north and south with the shifting of the pressure belt. Now, out of this, polar jet stream is stronger because the difference of temperature is more persistent and prominent throughout the year. So that is the case of the entire jet stream circulation. Let's take a look at this PYQ. La Nina is suspected to have caused recent floods in Australia. How is La Nina different from El Nino? So La Nina is characterized by unusually cold ocean temperature in equatorial Indian Ocean, whereas El Nino is characterized by unusually warm ocean temperature in equatorial Pacific Ocean. Second statement, El Nino has adverse effect on southwest monsoon of India, but La Nina has no effect on monsoonal climate. So in this, the first statement is incorrect. Why? Because it is not across Indian Ocean, it is across the Pacific Ocean. So the first statement is incorrect. Second statement, adverse effect on southwest monsoon, but La Nina has no effect. No, La Nina is beneficial for rainfall in India. So both of them are incorrect. So the correct answer in this is going to be D. Okay. Now, consider the following statements. Jet streams occur in the northern hemisphere only. Incorrect. Jet streams occur in both the hemispheres. Only some cyclones develop an eye. This is correct. All the tropical cyclones will develop an eye, but some temperate cyclones might not develop an eye. The temperature inside the eye of the cyclone is nearly 10 degrees Celsius less than the surrounding. This is incorrect. Temperature inside the eye of the cyclone is higher because of latent heat of condensation which is released. So in this, the correct answer is going to be C. That is 2 only. Okay. Now, another simple question. It is a PYQ again. Consider the following statements. The winds which blow between 30 north and 60 south latitudes throughout the year is known as westerlies. This is, and the second, moist air masses that cause winter rains in the northwestern region of India are a part of westerlies. So the first statement is incorrect. Why? There is no wind system between 30-degree north and 60-degree south. There is wind system between 30-degree north and 60-degree north, or 30-degree south and 60-degree south. So the first statement is incorrect. Second statement is correct. So correct answer is B, 2 only. Okay. Now let's go across the Indian climate very quickly. Indian climate, we will talk about the monsoon and the case of western disturbances. So when we talk about monsoons, there are different factors which influence the monsoonal rainfall in India. First of all, you have the heating of the land. During the summer months, the land gets heated up very intensively, which creates a low pressure. When this low pressure condition is created, that is when the ITCZ migrates north or moves northward. Now, when the ITCZ moves northward, this attracts winds from the southern high pressure zone. And the wind direction is southwest to northeast. That is why these are known as southwest monsoons. Okay. Monsoon basically means reversal of the wind system. A complete reversal of the wind system that you have. That is what is regarded as monsoon. Now, after this, these winds they come over to India and they basically cause rainfall, starting with the Kerala coastline, then across the western coast, then you have the northeastern region, then you have the winds moving from east to west here. One portion of the winds goes here and causes rainfall. One portion even enters between the region of the Narmada Rift Valley and causes rainfall in central India. So that is how the rains they tend to progress. Okay. Now, this monsoonal rainfall will not occur, onset of monsoon will not occur as long as you have the presence of a jet stream. That is the subtropical westerly jet stream. Now, subtropical westerly jet stream has got a distinct southern branch which appears over India during the winter months. Slowly and steadily, it thins out. But as long as you have this jet stream, there is no movement of winds which are allowed on the surface. The moment the jet stream disappears, at that point of time itself, you basically will come across the monsoonal onset and you have increased amount of rainfall which is then observed. Okay, so that is the case of the subtropical westerly jet stream. Simultaneously, you have the creation of the tropical easterly jet as well. This is created because of heating of the Tibetan highland. Heating of Tibet. Right. Now, Tibet is a high altitude plateau, the highest plateau across the world. Right. So, that is where, when you consider the region of Tibet, yes, correct, Devendra, the traffic signal analogy. So, over the region of Tibet, you will find that you have intense low pressure. Even if the temperature is, let's suppose, 15 degrees Celsius, it is very low for a very high for a region which is 5 kilometers above the sea level. Average altitude of Tibet is around 5 kilometers above sea level, right? So 5 kilometers above sea level, if you consider a dry lapse rate, it should be negative, but here it is 15 degrees Celsius. So you have very intense low pressure. That is when the air rises up, it hits the tropopause very soon, and it diverges into various sections. We are not interested in all the sections. One section, it comes southwards from Tibet, follows the Kolkata and the western axis, Kolkata to the western axis towards Africa, crosses equator, and then sinks in the region of the Mascarene high pressure. This is 0 degree. This is your Mascarene high. Okay. And that is when this high pressure then drives the wind systems and strengthens the monsoonal rainfall. Now, this portion of upper altitude wind is known as tropical easterly jet. Okay. So, westerly jet, subtropical westerly jet stream, it prevents any movement of wind across the ground surface. Okay. Now, then that is the case of tropical easterly jet created due to the heating of the Tibetan highland. This can intensifies Indian monsoon. Okay, it will always end up intensifying Indian monsoon. Without this also monsoon will occur, rainfall will occur, but it is like a booster, if you can associate with that analogy. It boosts it. Okay, so imagine that air is rising up from here, it diverges in various different directions. One of them, it comes like this, crosses the equator and then sinks here. After that, it generates a surface wind, the surface wind. And that is the same surface wind which comes to India and brings rainfall. So this high altitude wind, that is known as the tropical easterly jet. Okay. Now, in India, majority of the rainfall is caused because of the impact of the mountains or the orographic system that we have. That is why western part of Western Ghats, when we talk about the northeastern stretches, they are the ones, even Andaman Nicobar, they will experience very high amount of rainfall. Amount of rainfall reduces as one moves from south to north. As one moves from south to north, amount of rainfall reduces. As one moves from east to west, amount of rainfall reduces because you are moving away from the source of moisture. Now, during the winter months, what you experience is the case that over the region of Mediterranean, you have warmer air, and over the region of Central Asia and Europe, you have colder air. So this warm and cold air that mixes together and forms a kind of a frontal depression over the region of Mediterranean. And then carried by the westerlies and even the jet stream, this frontal depression comes and hits the region of Himalayas. In Himalayas, it will cause snowfall, lowering the temperature, and rainfall in Punjab, Haryana, Delhi, Rajasthan, then Uttar Pradesh, Bihar, in all these areas. So it causes intense winter. That is coming from the western side. That is why it is also known as western disturbances. Which months? So from the month of November, December, January, February, declines in March, sometimes even in April. Early sowing of wheat is facilitated. In local lingo, that is in northwestern part of the country, it is also known as Mahavat. Okay? Now, here, consider the following statements about the phenomena of El Nino and its effect on Indian monsoon. So when we consider El Nino and monsoon, so it occurs in the region of South Pacific and hence has no impact on the monsoon. Incorrect. It leads to increased rainfall over Indian subcontinent during the monsoon season. Again incorrect. Its impact can be neutralized by Indian Ocean dipole and Madden-Julian oscillation. That is correct. Correct answer is 3 only. Now, which of the following correctly describes the phenomena of western disturbance? They are the aggravated monsoon winds blowing from west to east. They originate over the Mediterranean Sea and are carried to India by winds. Their effect can be felt mostly during the months of July to September. They can bring rains only over the hilly tracts of Himachal Pradesh. So here, correct answer is that they originate over Mediterranean and they are brought over to India by westerlies and even the jet streams. Now you have the portion of climatic classification. Now, as I told you, you have a detailed video also. The link will be provided in the description. But here, very briefly, if we cover the case of the climate classification, please understand, don't fall into the trap of learning the codes, the Köppen codes. Please don't learn the Köppen codes. UPSC has not been asking question about the Köppen codes. Okay, so you need to know what are equatorial climate, what is British climate, and so on. Right? Don't worry, another half an hour and we will be done with the session. Thank you for all the patience. But I hope that this session is fruitful And I hope that all of you have managed to revise substantial amount. So think about it. We have covered entirety of geomorphology, and we have also managed to cover the entirety of climatology in as much detail and depth as is required for the prelims examination. The If you are thorough with this session, if you are thorough with what has been covered in the session, rest assured you will not face a problem from now till the prelims examination. Just a brush up of test series and MCQs, and you will be good to go. So that is where the aim of the session is, that regardless of howsoever time it takes, none of you should suffer because you have simply delayed the preparation of physical geography. Okay. Oceanography, also the ocean currents and tides, which are important, very briefly, we will cover. Okay. Now, Köppen's classification, you have to go through certain types of climate. Now, Köppen classification is based on what? Is based on vegetation cover, where you have the vegetation cover, right? So, okay, right. So we continue. Thank you for the patience, by the way. And we will be wrapping it up in another 30-35 minutes. Okay. And that will be completing the entirety of it. Now, Köppen classification is based on the vegetation cover across the world. Wherever you have vegetation, so vegetation is dependent on rainfall and temperature. In any area, if the temperature is very high, obviously coniferous forest won't grow. If the temperature is very low, very cold, then trees like mango trees, evergreen trees, they won't grow. Right. So it is dependent on vegetation. From that, you basically have the description of rainfall and temperature. That is the Köppen's classification overall. Now it is divided A, B, C, D, and E type, and you have a separate H type representing highland type of climate. Easy to remember. If you want to recall this, if you consider the entirety of planet Earth, around the equator, you will have A type, high amount of rainfall. As you move higher away, subtropical high pressure, that is where you will find B type, desert areas. B type, desert areas. As you move further away, you will have C type, the coastal continents, China type, Mediterranean type, British type. Further away, D type, Siberia, Canada, D type. And then the poles, that is the E type. So closer to the equator, A type, further away, B type, and like that, you have the classification. Okay. Now, H is basically the region of highland, where you have elevated area or a plateau region, that is the H type. Okay. So there you have in general lower temperature as compared to average or as compared to normal. Furthermore, rainfall is also classified. So if you have rainfall throughout the year, F is used. If you have rainfall only during monsoon, M is used. If you have the condition where winter is dry, W is used. If you have the condition summer is dry, S is used. Right? So you have, for example, AF, AW, AM, and so on. Right? So, this is the overall Köppen's classification. Closer to the equator, you will find the presence of A type. Slightly away, B type. Slightly away, C type. Slightly away, D type. Then you have E type. Okay? Now, when you consider A type is of three categories. That is AF, equatorial climate. In equatorial climate, rainfall occurs throughout the year. So, and the average rainfall is high. So, you have convectional rainfall which occurs throughout the year in this case. So, for example, the Amazon rainforest, the Congo rainforest, the rainforest across Indonesia, Philippines, then the islands. So, that is the AF type. Then you have the case of monsoonal climate. Monsoonal climate, rainfall occurs, but typically during the monsoon months, right? So, monsoon months in India, when do we experience monsoon? During summer season. So, overall rainfall is high, But all that rainfall is concentrated during the monsoon months itself. So that is the monsoonal climate, tropical monsoonal climate. That is AM type. So here you can observe, for example, Mangalore in India, that all the rainfall is dominant, particularly during the monsoon months. Okay, so India, then when you consider certain regions of Africa, that is the monsoonal climate. In general, what do we actually mean by monsoon is nothing but the seasonal reversal of winds. That is what is meant by monsoon. Then you have the AW, that is the savanna type of climate or tropical wet and dry climate. This is also known as savanna. Okay, so you have tropical grasslands which are created in this particular case, right? So here you have very brief wet season and long dry season, small wet season. So you have tropical grasslands. Okay, now in this you will find that you have large amount of activities by herbivores, carnivores, and so on. They are of various different types. For example, in Kenya, you have Masai Mara; in Tanzania, Serengeti; in Brazil, Campos; in the region of Venezuela, you have Llanos. All of this is because of the tropical grassland. That is the case of savanna. Now, because the dry season is so large and so prolonged, you have water scarcity. So the trees cannot grow. You have these grasses which are there. And then whenever the grasses they dry up, obviously they will dry up prior to the rainfall. When the rainfall occurs associated with thunder and lightning, they can cause wildfires as well. So these limit the growth of grasses in the region. Okay. Now, the AW type, for example, the Sahel region in Africa, you have the Campos in Brazil, Llanos in Venezuela. In India also, in central India, for example, in Telangana, Vidarbha region, there also you will find AW type of climatic condition. B type is the case of desert, subtropical high pressure region, sinking air high pressure region, so you don't have rainfall in this particular case. So here also B type has got further subclassification. So you have the case of B type having the subclassification. First of all, when you consider it, it is of two types. That is BW and BS, right? So when you consider dry deserts, that basically comes into the category of BW. Okay, dry deserts, BW, and steppe or semi arid areas, that is BS. Now, even in dry desert, you can have hot deserts and cold deserts. Hot deserts, for example, Sahara, Thar, Daste Lut, Daste Kavir, Rubal Khali. These are hot deserts. So, in this case, average annual temperature is greater than 18 degrees Celsius. So, that is when you will use BWH. And Gobi Desert is a cold desert. Central Asian deserts are cold deserts. So BWK. Okay. So BW, desert type of climate covering 12% of the Earth's surface. And you have hot represented by H and cold represented by K. And then you have the semi arid that is represented by BS. So in that case, you have steppes, some amount of temperate grasslands which prevail. Then the group C type of climate, that is the case of the moderate climate, temperate climate. Now, this is observed generally in coastal areas, and you have the various name. For example, here it is known as Gulf type of climate. Rainfall throughout the year. So it will be CF. And because the temperature is also higher, CFA. Then Western Europe, that is British type of climate. Rainfall throughout the year because of westerlies, that is marine west coast or CFB. Then you have the natal type of climate. Then you have Mediterranean type of climate, CS. And then eventually you have the China type of climate. Okay. UPSC will ask you a question associated with this classification. So, in case you still have a doubt, do ensure you watch a detailed video. I will put the link also. But revise just the case of what is the rainfall, what is the condition. That is something you should be clear about. So, CFA or the Gulf type of climate, rainfall throughout the year across the region around Gulf of Mexico. So, eastern parts in the subtropical latitude due to the impact of the trade winds also. No dry season, rainfall throughout the year, right? Annual range of rainfall 75 to 100 centimeter. That is the region of CFA. Okay. Then after that, when you consider marine west coast climate or CFB, this is also known as the British type of climate. British type of climate. British type of climate basically means that due to westerlies and the frontal cyclones, you experience rainfall on a daily basis, every day. So that does not allow the temperature to reach any extremity. You have moderate marine influence. That is why marine west coast climate. So rainfall which is experienced throughout the year, but overall rainfall is around 250 centimeter per year, not more than that. Then CS or Mediterranean type of climate, good for growing orchard cultivation, citrus fruits, etc. Here the summer is dry, winter is when you receive rainfall. Why? Because of two factors. First of all, during the summer, in this region, you have the subtropical high pressure belt. So, high pressure, no rainfall. But then during the winter, the high pressure belt shifts to the south. So here you have the westerlies which become onshore and they cause rains. Other than that, we have also studied that during winter in this region, you have the formation of a frontal cyclone or a frontal depression. And that also creates a lot of rainfall in the area. So that is Mediterranean type of climate. Winter rains associated with the onshore winds, shifting of pressure belts, and the frontal cyclones. Then you have the CW, humid subtropical, or what is also known as the China type of climate. Here, winter is dry. Summer, you receive rainfall. Why? Because the ITCZ shifts north during the summer season. And that is where you receive rainfall. So that is the case of China type. Okay. So annual rainfall 60 centimeter to 150 centimeter. Then as you go into the region of Siberia, Canada, you have the D type. Okay. So those are the areas where you have the D type. Now in the coastal areas here, you can have DF because there is rainfall throughout the year, precipitation or snowfall throughout the year. That is DF. But other than that, generally just know about the D type. So here you have coniferous forest. Coniferous forest in general, boreal vegetation in general. And then you have the E type, which is the polar climate. Polar climate is again subclassified into two types, that is EF and ET. So, in the coastal areas of Greenland, in the northern coast of Eurasia and North America, you will have partial melting during the summer. So, during the summer, you can have tundra vegetation which grows. So, in the coastal areas of Greenland, Eurasia, Canada, you will have tundra vegetation, mosses and lichens which will grow during the summer season. But then, when you go to the interior of Greenland, Antarctica, in those areas, you will have permanent frozen ice throughout the year, right? So, Antarctica, for example, that is EF. Okay. Now, here, this is the overall classification and the list that you can use for revision. What you should revise is this and this portion. That is the feature associated. Let's take a look at some of the questions. Consider the following description. Annual and daily range of temperature is low. That means temperature variation is not there, consistent temperature. That can be true for equatorial climate also, that is AF. It can be true for wherever you have daily rainfall, right? Precipitation occurs throughout the year. Precipitation varies between 50 centimeter to 250 centimeter. In equatorial climate, rainfall is something which occurs at a level of around 700 centimeter, 400 centimeter per year. So this will occur obviously in the region of mid latitudes. So the correct answer for this is marine west coast climate. Okay. Now, seasonal reversal of winds is the typical character of monsoon climate. This was a question which is oftentimes repeated. Seasonal reversal of winds is a characteristic of what? Climate is extreme, rainfall is very less, and the people used to be nomadic herders. Above statement best describes which of the case, that is basically what you can consider as African savanna as well. Which one of the following is the characteristic climate of tropical savanna region? Rainfall throughout the year, rainfall in winter only, an extremely short dry season, a definite dry and wet season. So, rainfall throughout the year? Obviously not. Rainfall during summer? Not in winter. Extremely short dry season? No, dry season is very long. So, the correct answer is D. Each day is more or less the same. The morning is clear and bright with a sea breeze. As the sun climbs high in the sky, heat mounts up, dark clouds form, and then rain comes with thunder and lightning. But the rain is soon over. Which type of climate is this? This is the case of equatorial climate. Okay, that is where each day you have convectional rainfall. Okay, now coming to the last topic of tides and ocean currents. So when we consider the entirety of the area of oceanography, these are some of the areas which are important for your exams. Now, what are tides? Tides are basically the vertical movement that you observe in the case of oceans and seas. Okay, vertical variation in the height of the oceans and the seas, that is what is referred to as tide. Right now, this is the daily variation which occurs. Why does it occur? It occurs because of two different forces. One is the gravitational pull, other is the centrifugal force. Gravitational pull by both sun and the moon, by the way, along with the centrifugal force as the planet moves across the sun and even across its axis. So that is the case where the gravitational pull by the moon has a greater impact because moon is much more closer to earth as compared to the sun. Now, what is important for you to understand is the classification of tides. The classification of tides, when you consider classification, is of two categories. One is based on position of sun and moon. Sun and moon. Secondly, you have the case of based on frequency, once a day or twice a day. Frequency. So based on this, you basically have spring tide and neap tide. Tide and neap tide. Right? And here you have the diurnal and semi-diurnal. Diurnal and diurnal. Okay. That is the basic classification that you will get. Now here, when we talk about spring tide and neap tide, so whenever the earth, the sun and the moon, they are across the same plane, that is when you have the lunar effect and the solar effect, which tends to accumulate. So the high tides are higher than normal, and low tides obviously will be lower than normal. By the way, this position when the earth, sun and the moon are perfectly aligned, that position is known as the position of syzygy. When the earth, sun and the moon, they are perfectly aligned in the same plane, that is syzygy. When the moon is in between the earth and the sun, that is basically the position of conjunction. And when the moon is opposing to the earth, that is opposition. Okay. So here, this is known as the spring tide, where, as you can see, the solar tide and the lunar tide, they add on to each other. So in this particular case, what happens? High tide is higher than normal. Higher than normal. Right? And low tide is lower than normal. This is important because many of the guys, they miss out on this factor of low tide, and it was asked in UPSC once. So in the prelims, is lower than normal. Okay. Now, when we say syzygy is when the earth, the moon and the sun, they are basically across the similar plane or the same plane. That is what is referred to as syzygy. Then, by the way, moon takes how many days to complete one movement across the planet Earth? It takes roughly around 28 days. So, spring tide is something which occurs every 14 days. Every 14 days, you will experience the occurrence of spring tide. Meanwhile, when you observe that when the moon is perpendicular to Earth and the sun, that position is known as the position of quadrature. Now, in this, the lunar tide and the solar tide, they tend to cancel out each other. That is why this is known as the neap tide. In this case, high tides are lower than normal. What about the low tides in this case? What will be the height of the low tides? High tides are lower than normal. And when we talk about low tides, they are higher as compared to average. Higher than average. This is a position that I want you to be very confident in about the case of the low tides. Because if the high tides are lower, obviously less water will be extracted from the low tides as well. So neap tides, every 7 days after a spring tide, you will experience the occurrence of a neap tide. In the neap tide, the tides, they tend to cancel out each other. Okay. Then diurnal and semi-diurnal. So whenever you have in 24 hours, two high tides and two low tides each day, right? That is known as semi-diurnal. Example, in Bay of Bengal, Arabian Sea, etc. Two high tides and two low tides every day, right? That is known as semi-diurnal. But in regions such as Gulf of Mexico, due to the location, etc., you have only one high tide and one low tide each day. That is what is known as diurnal tide. So based upon the frequency, semi-diurnal, that is twice a day. Diurnal, only once a day. Now coming to the topic of ocean currents. Now ocean currents, they are classified as warm currents, cold currents, surface currents, deep water currents. Surface currents, the ocean currents that you will take a look into it very briefly. And warm currents, if they are warmer in comparison to the surrounding water, warm currents. If they are colder in comparison to the surrounding water, cold currents. In general, whenever you have ocean currents coming from higher latitude to lower latitude, it is cold current. Whenever you have currents coming from lower latitude to higher latitude, it is warm current. Now, there are various factors which influence ocean current, starting with the heating by the sun. Now, whenever you have heating by the sun, in the lower latitude, water swells up, right? Water height increases due to thermal expansion. There is a height gradient of around 8 centimeter, which is gained. After that, the winds, like the trade winds, the westerlies, etc., they carry that water and provide a direction. That direction is then influenced by the Coriolis force, where in the northern hemisphere, the ocean currents they bend to the right, and in the southern hemisphere, the ocean currents they bend to the left. Then these are also directed by the shape of the coastline. And even when you have mid-oceanic ridges somewhere underneath the ocean, that also impacts the ocean currents. Let's take a look at the ocean currents in the Atlantic, and the same pattern is repeated in Pacific and Indian Ocean as well. So overall, when you consider the region of Atlantic, understand it carefully. Once you understand this, it will be easily retained. So for example, when you have the water in the lower latitude or equatorial region which is heated and expands, then the trade winds, the trade winds, they will carry it in a direction of east to west. You have the north and the south equatorial current. Now, water will accumulate here, isn't it? It will be directed due to the shape of the coastline, but some water will accumulate. And due to the rotation of planet Earth from west to east, that is when some of that water will start to flow back in the form of counter equatorial current. So you have north equatorial and south equatorial current with meet. If they would not have met, counter equatorial current is not generated. So they meet. And after that, the north equatorial current, here it is directed towards the Antilles Island. Remember again in the mapping session, we had discussed about the Greater Antilles and the Lesser Antilles. That is the Caribbean islands. Now here it gets divided around the region of the Caribbean islands. So you basically have the case where they meet. One enters into Gulf of Mexico through the Yucatan Peninsula and the Yucatan Channel. After that, the Antilles current and the Florida current meets to form the strongest warm water current in the world, that is the Gulf Stream. Now, from the region of the Labrador Sea, you have the cold ocean current, that is Labrador current, which meets. Meeting of warm and cold ocean current always creates ideal ground for the planktons to grow, and always is a very ideal fishing ground. Wherever warm and cold ocean currents meet, that is very ideal fishing ground. So this Gulf Stream meets with the Labrador current and creates a very ideal fishing ground. Then after that, carried by the westerlies, it is the North Atlantic drift, which creates warmer condition in the northern part of the Atlantic and ensures it is navigable throughout the year. Now, due to Coriolis force, it will be bending to the right. Now, North Atlantic drift, basically because of the shape of the coastline and also because of the bottom relief, that gets divided into multiple subparts: Norwegian current, Irminger current, Rennell current, and so on. But here, basically, it will also bend to the right near the region of Bay of Biscay. This is the region of the Bay of Biscay. And it will bend to the right. Now, it is bringing water from the higher latitude to the lower latitude. So higher latitude to lower latitude, cold water will be brought about. So it is a cold current known as the Canary current after the Canary Islands, which are situated in the western coast of Africa. So that cold Canary current fills the entire circulation. Whereas in the southern hemisphere, you will observe that it bends leftwards. You have the Brazil current. Meanwhile, across the entirety of Southern Ocean across the world, you have, because of the westerlies, the movement of what is known as west wind drift. Now, west wind drift that slightly bends leftwards around the Falkland Islands, and you have the Falkland current, right? Then, after that, again it bends leftwards in the region across the Namib Desert, western coast of South Africa, and that is the cold Venezuela current. So, you have this circulation in the Atlantic. In the Pacific, also, same logic is followed. That is, you have the North Equatorial Current, South Equatorial Current created by the trade winds. Now, that water tends to accumulate here. Some of that will flow back as counter equatorial current. Then, just like there you had the Gulf Stream, here you have the Kuroshio. And through the Tsushima channel, you have the Tsushima current. Right. Now, this Kuroshio meets with the Oyashio. There you had Labrador current in Atlantic. Here you have Oyashio, which is a cold ocean current. And then after that, carried by the westerlies, it moves as the North Pacific current. It is because of the obstruction of the coastline, it is divided. One moves from lower latitude to higher latitude, warm Alaska current moving through the Alexander Islands, Aleutian Islands, and so on. Another one from higher latitude to lower latitude, cold California current, creating deserts, Sonoran, Mojave, and even the Chihuahuan. That is the cold California current. In the southern Pacific Ocean, you have the East Australia current, just like the Brazil current there, west wind drift, and there you had the Venezuela current. Here you have the cold Peru current or the Humboldt current. In the Indian Ocean, however, southern Indian Ocean, it is the same. Northern Indian Ocean, there is a variation. Why? Because northern Indian Ocean, unlike the Pacific and the Atlantic, is not open. It is closed by the landmass. Now, once it is closed by the landmass, means what? It will be impacted by the wind movement. So, during the months of advancing monsoon, what happens is you have the winds which are like this, southwest to northeast. So observe, water circulation is also like that. Okay. Whereas in the southern hemisphere, you have the Leuven current, which brings water from Pacific to the Indian Ocean, allows for mixing of water. You have the South Equatorial current, Mozambique, Agulhas, same west wind drift, and here you have the West Australia cold current, which is responsible for the creation of Victorian desert. Now observe, during the month of retreating monsoon and northeast monsoon, that is when the wind direction is like this. That is when in the northern Indian Ocean, the oceanic circulation becomes counterclockwise. This time, because you have accumulation of water in this portion by the South Equatorial current also and northeast monsoon as well, that is why only in these months you have counter equatorial current in the Indian Ocean. In these months, you don't have counter equatorial current because you don't have that accumulation, and the remaining portion remains the same. Okay, what kind of question can be expected out of this? Which of these represent the warm ocean currents? Gulf Stream, Canary Current, Kuroshio, and California. Which of them? So it is a simple question. I don't think anyone should get it wrong. So Gulf Stream is a warm ocean current. Canary Current is a cold ocean current, right? Kuroshio Current, again a warm ocean current. California Current is a cold ocean current. So the correct answer in this will be A, that is 1 and 3 only. Okay. Then consider the following statements. In the tropical zone, the western section of the oceans are warmer than the eastern sections due to the influence of the trade winds. In the temperate zone, westerlies make the eastern section of the oceans warmer than the western sections. Now, this was a very straightforward and simple question. So, this is based on the concept of upwelling and downwelling. So when you consider the west coast and let's suppose the east coast of an ocean, if let's suppose you have the onshore winds, the trade winds, let's suppose, they will accumulate the warm water across the western coast and they will lead to downwelling, increase in the sea surface temperature. So that is why in the tropical zone, western section of the oceans are warmer because of downwelling. Downwelling is always associated with increase in sea surface temperature. Okay. Then similar phenomena happens across the eastern section of the oceans in the temperate region. That is where you have the westerlies that push the winds across the oceans from west to east direction, and you have downwelling in the eastern section. So here both 1 and 2 are correct. In the South Atlantic and Southeastern Pacific regions in tropical latitude, cyclones do not originate. What is the reason? Sea surface temperatures are low. No. Intertropical convergence zone seldom occurs. Coriolis force is too weak. No. Absence of land in these areas. Absence of land would have led to the formation of tropical cyclones, isn't it? So here, ITCZ seldom crosses into South Pacific and South Atlantic. Then, tides occur in the ocean and seas due to which of the following? Let me know the answer. This, at least everybody should get it correct. Gravitational force of the sun, gravitational force of the moon, centrifugal force of planet Earth. So in this, all the three are important for the formation of tides. Okay. The most important fishing grounds of the world are found in the regions where warm and cold atmospheric currents meet, rivers drain out large amount of fresh water into the sea, warm and cold ocean currents meet, continental shelf is undulating. So, fishing ground associated with the meeting of warm and cold ocean currents. What explains the eastward flow of the equatorial counter current? Earth's rotation on its axis, convergence of the two equatorial currents, difference in salinity of water, occurrence of the belt of calm near the equator. What is responsible for the equatorial counter current? It is convergence of the two equatorial currents, which will lead to the development of a counter current. Okay, so that basically brings us to the end of the session, and I hope you would have understood, liked, and benefited from this entire endeavor. And this video, it is basically something which will help you tremendously in the examination. Is it even possible for cyclone to exist without an eye? Absolutely, yes. In temperate regions, it can exist. You can have multiple rise of air across the warm front and the cold front, and you might not have an eye. Okay. So overall, I would suggest to you, I will provide you the PDF also, but I want you to revise this, and in a period of time, just keep on revising this, revisiting this, and that is more than sufficient for your prelims examination. Wishing you all the very best. And in case you have liked the session, don't forget to click on the like, share, and the subscribe button and let us know about your experience in the comment section below. We'll meet again. Till then, take care of yourself, relax, goodbye, and have a good night.